Hello, everyone. I'm Teodora Felicia Sandru from the MDPI Conference Department, and I will be your host today. I would like to welcome everyone to the first international online conference on the journal Philosophies. This is the fourth day of this conference, and we are now in the morning session. The topic of today's discussion is Intelligence Beyond Anthropomorphization, Widening the Perspective. This virtual conference is hosted online from 10 to 14 of June 2025 and is organized by MDPI and the journal Philosophies. Participants in this conference are cordially invited to contribute a full manuscript to the conference's special issue published in Philosophies with a 20% discount on the publication fee. I would like to thank the event chairs, Professor Dr. Marcin Schroeder and Professor Dr. Gordana Godi-Krnkovic. We would like to express our gratitude to the conference committee members for their contributions to making this event possible, as well as to the speakers and, of course, our attendees. The presentations are followed by a short question time, and if you have any questions for our speakers, please feel free to post them in the Q&A box at the bottom of your screen. We are honored to have with us the event chairs of this conference. And let me introduce now Professor Dr. Schroeder, Professor Emeritus at Akita International University, Akita, Japan. He will chair this morning part of the discussion. And please, Professor Schroeder, the floor is yours.
Thank you very much for the introduction, and hello to everyone. Welcome to the fourth day, and we will start our first event. It will be oral presentation by Professor Jian Wang from Xi'an Jiaotong University, Xi'an, China. The title of the presentation is A Framework for the Ethical Design and Accountability Attribution of Military Robot Systems. Professor Wang, please take the stage.
Thank you. Okay, so I can see my presentation. Nice to meet you again. Now, the title of my presentation is a framework for the ethical design of military robot systems, and another considerations on accountability attribution. So I'm Jian Wang from the Xi'an Jiaotong University. So with the rapid development of technology in the new century, the military field has undergone revolutionary changes. The unmanned nature of military operations has become an inevitable trend in development of future military equipment, and military robots are gradually becoming the main combat force in military operations. So these robots, which already possess many advantages over human soldiers, are gradually replacing flesh and blood human soldiers on the stage of history. Military robots with high autonomy are gradually replacing, for example,
Sorry,
a few minutes. So my title, as I said, speak again, a framework for the ethical design of military robots systems and a consideration on accountability's attribution. Yes. So with the development of technology, the military field has undergone revolutionary changes. The unmanned nature of military operations had become an inevitable trend in development of future military equipment. And the military robots, are gradually becoming the main combat force in military operations. These robots, which already possess many advantages, are gradually replacing flesh and blood human soldiers. So military robots with higher autonomy are gradually replacing, for example, tanks as a core weapons of the new century. We can see already in the past few years. So it is essential to explore certain profound issues related to military robots from a philosophical perspective. And this research and the use of military robots are not merely abstract questions, but also concrete ethical issues. So, what are military robots? Military robots are automated machines designed to replace human soldiers in combat operations. They are controlled by algorithmic programs and can simulate certain combat functions of soldiers through these algorithms. They primarily come in three forms, for example, autonomous, semi-autonomous, and remotely controlled. Their applications include first, directly replacing human soldiers in military operations. Second, conducting reconnaissance or patrols in enemy territory. Third, perform 3D works, what are 3D works? It means they are dirty, they are difficult, they are dangerous. Additionally, military robots can be utilized for command and control assistance, logistics and transportation support, and so on. So they have a lot of advantages, such as first, they reduce soldier casualties. Second, they reduce fiscal expenditures. Third, they can enhance combat capabilities. Fourth, they can lower the environmental costs. But however, we also facing the moral dilemma of military robots. At the current stage, engineers have been able to algorithmize some simple ethical rules and embedded them into programs. But these ethical rules can guide robots to make choices that comply with ethical norms, thereby preventing robots from violating human moral standard when operating without human control. So we can first we can imagine a thought experiment to discuss the moral choices. The military robot version of the trolley problem. A military robot is deployed to combat Zoom to rescue a hostage. During the rescue operation, it encounters 4 local shepherds. At this point, the military robot cannot definitely choose whether these 4 individuals are disguised terrorists. So facing with the dilemma, the military robot must make a decision whether it is permissible or moral to acceptable moral to kill 4 people who may be civilians in order to save 1 hostage, or whether it is permissible or morally acceptable to spare 4 local residents who may be terrorists. So thereby causing the death of 1 hostage. We do not know how the military robot will choose, but we assume there are only these 2 options. Now let us use this experiment as our testing scenarios to consider the design of an ethical model for military robots. So the second part, we talk about moral judgments. Moral judgments are the product, or we think moral judgments are the product of evolutionary pressure for cooperative behavior in self-interested organisms. So according to the famous John Nash, the best strategy for a player is when other players are also using their best strategies and cannot he cannot improve his own returns. This is called Nash equilibrium. We can model the cooperation problems as a prisoner dilemma. Whenever an outcome arises that improves the situation for at least one player without worsening the situation for another player. So this is called Pareto improvement. In the prisoner dilemma, the result of a Nash equilibrium in non-zero sum game is a universal Pareto improvement. So the clear structure of the prisoner dilemma offers prospects for designing computer programs that can compete against each other. In the military version, the philosopher Axelrod describes the strategy of this prisoner dilemma game in his book, The Evolution of Cooperation. There are two simplest pure strategies are to always de facto or always cooperation. That one cooperation is chosen at the outside the program will enter or cooperate state, regardless of what other players do. Or if one party chooses to defect, the program will enter a defection state, regardless of what other players do. So how to apply this in the dilemma? Ideally, we would like a set of internally consistent principles that not only align with the moral grammar we have evolved in normal cooperative problem, but also extended to dilemma. So we will discuss Rawls. Rawls can contractualist theory, which meets all these criteria while successfully extending to non-cooperative dilemma situation. So in his book, famous book, Rawls enjoys the veil of ignorance method to obscure the individual's subjective preference, leaving only observable objective characteristics. The state in which individuals find themselves at this point is what Rawls refers to as the original position. The original position means anonymity, forced cooperation. So Rawls expressed the notion of contractualism as a principle of justice. Social and economical inequalities should be arranged in such a way that the least advantage receives greatest benefit. He called it the difference principle. So we can understand this difference principle as the maximize the minimum value principle, which is called by Derek Levin. Since we do not know which rule we will be assigned from the initial position, so the maximum principle requires us to maximize the minimum benefit for all players. This is often described as making the worst of person as well of as possible, meaning that a decision is only reasonable if it benefits the persist members of a society. So in non-zero sum cooperative dilemma games, the max-min principle can be used to test moral theories. It always produces a universal Pareto improvement and Nash equilibrium conditions. So we can talk about it in two cases. First, in the classical prisoner dilemma game. Second, in the disasterful prisoner dilemma game. So because of time, we will focus on the second. So in the disasterful prisoner dilemma game, based on the max-min principle, which aims to maximize the benefits of the least advantaged party, the players will still choose either mutual sacrifice or mutual defection and cooperate behavior. Multi-sequence or is merely an ideal state of a Pareto optimality. So the final choice remains multi-defection, so which achieves a Pareto improvement or represent a Nash equilibrium. So we think this max-min algorithm can be generated by two basic process referred to as mean and as max. The mean means find the minimum value in each operation. Max means combine this minimum value and select the largest minimum value. The mean and max are sufficient for simple operations with no identical minimum values. However, for data with identical minimum value, we need to add more content. So the simplest we can explain it. Just simplest situations, two data points with identical minimum value, such as 3,5 and 3,6. Although the minimum value in both cases are equal, it is clear that it's 3. Yes, it's that a rational player in their original state will simply delete 3 and override this identical minimum value 3 and move on to next smallest value 5. Assuming we have an equal chance of becoming the next player, we are equally interested in maximize the minimum value. However, this process has two parts. Need further clearance. So, first, consider a simple example involving 2 actions and 4 participants, as shown in the figure below. So, we saw this figure. We see the figure, a simple data set. Yeah, assign values to the 2 actions for 4 players and mark the minimum values. Even if the total value of A1 is greater than that of A2, max-min will choose A2 because the minimum value of A2 is greater than that of A1. We can see that it's 3 is greater than 2, of course. The simple part is what should we do if all the same minimum value have been covered and there are no more value in either data set? So such as in 8,6,3 and 3,8,6 two sets. The solution to this problem seems clear because they are same set. They are the same sets. So when the goods are arranged in 2 possible behaviors that are completely identical, a rational person would randomize. So simply flipping a coin to decide between them. Let's consider another case. Consider the data set A1 equals 3, -8, -8, and A2 equals -8, 2, 8. So the minimum value of A1 and A2 are the same, but there are 2 minimum values in A1 and only 1 in A2. So what should we do in this case? So should we cover all identical minimum value? This program we call the max-min plus, or only the first identical minimum value. So this plan or this program is we call the lax-min. So in figure 2, we see that max-min plus follows this program. We will choose A1. But while we follow lax-min program, we will choose A2. So should we use max-min plus or lax-min? This is crucial for resolve the trolley dilemma. So in the classical trolley dilemma, we can significantly reduce one person's survival rate to increase the survival rates of many others, and vice versa. According to the playoff table in figure 3, these 2 choices will produce completely different outcomes. Max-min plus covers all minimum values. So in this case, we should randomize. but follow a lex mean. Lex mean, however, only covers a single minimum value, resulting in the standard utilitarian solution. So when the value of suffering is equal, it prefers the suffering of a few over the suffering of many, as shown in the figure 3. In figure 3. So it's now appear that the max mean plus principle does not always yield a Pareto optimal solution for cooperation problem, whereas the lex mean principle does. So for example, in the simple choice between the two sets of data, 1, 2, 2, and 1, 1, 2, covering all relevant minimum would result in no data remaining for comparison. However, the first set is clearly a Pareto improvement over the second one. So on the other hand, if we only cover the first instance of the same minimum, this process will always produce a Pareto optimal solution or cooperative behavior. Therefore, the lex mean principle is the method we use to address minimum value relationships. This is our choice. So in the last part, it's a summary. We have seen that as an important technological invention, modern military robots have become a decisive factor in the outcome of wars. While the use of military robots on the battlefield does indeed offer certain benefits, but it raises serious ethical dilemma and issues of accountabilities. Some scholars have attempted to address these dilemmas, but our analysis suggests that contractualism offers a better solution. So benefits should be distributed based on the location of a primary goods, such as life, health, opportunities, and basic resource, and decisions should be made according to the lex mean principle. So this decision-making approach is also effective when faced with the military robots version of the trolley problem. So a subsequent question is, if a military robot commits an accidental killing during combat or operation, who should be held responsible? The academic community has not yet provided an answer to this question, but there is a natural view holds that at the current stage, it's not feasible to treat the robot itself as the responsible party. So responsibilities must be borne by humans. So therefore, we should at least ensure that military robots are used under human supervision and cannot independently make majority decisions with severe consequences. So that's all of my presentation. Thank you very much for listening.
Thank you very much. This is very thought-provoking presentation. First, I would like to see if there are questions. If there are no questions, Gordana has questions.
Yes, thank you, Professor Wang, for a very interesting and important lecture. I myself am researching on responsibility in autonomous systems. And me and my collaborators identified one problem with human supervision. And we don't know the answer, but we find it important. And that is that AI are so much faster than we. So to supervise what they are doing, you must use other AI. We are not able to follow them. So I would like to know, how do you see it?
Yeah, so actually, the title of my paper includes two parts. The second part is talking. My plan is to talk about the accountability attribution. Yes, it's very difficult. So I didn't finish it, this paper. So I still think about that because I found some scholars already talk about some solvation. Yes, so some plans to solve this problem. For example, they want to use a kind of model of accountability attribution or this. Sorry, I found because I read it in Chinese, so I still to translate it in English. So actually, it's a kind of hierarchical system model of accountability. So sorry, I can't
I
explain.
think that was what we also proposed. We proposed distributed responsibility and functional responsibility, but to control in every moment what they are doing on the battlefield, you need other systems who are very quick. And then
Yes,
you
I
get this
agree with you.
regression of, yeah.
Thank you. I agree with you very much. Yeah.
Thank you.
Okay, I don't see other questions, so I will ask my question. I will start from about 40 years ago. The world was at the point of possible total catastrophe. Yeah, Soviet army detected, later it turned out falsely, that missiles were launched from America. And there was one guy, I don't remember his name, I think Ivan Petrovich, who was in command and who had to make decision to launch counterattack or not. Fortunately, he decided not. But there was a movie about him, and in the movie, they were showing actors seeing in imagination nuclear mushrooms and thinking. And I've seen an interview with this guy, and he said, I didn't have time to think about nuclear mushrooms. I had to make decision in a couple of seconds. So I cannot say how I decided. I just decided. So here is there is this there are many theories of thinking, and Kahneman's approach is human beings have this rational way of thinking, and intuitive. Intuitive is very fast but rigid, habitual, and rational is slow but more flexible. My question is, okay, when I look at what is very often done, and I don't criticize, but basically what you presented is this rational side. But question is, can we find a way to put into AI this intuitive side, which is much faster? And to end my question, I would refer to another example, which is like in Japan, there is a very famous historical person, Musashi Maru, who was a samurai fighter, and who was saying, if you think you can die, you are already dead. You cannot think means you cannot rationalize because it is too slow. So once again, my question is, do you see possibility to implement in artificial intelligence this intuitive way of reacting?
Yeah, it's a very important problems. I can connect it to the topic of agency. So because so we are humans, though they are robots. But how to think about the robots like humans to the view of making decision. Like what you said about the intuition. We can train ourselves. Can we train AI? Can we train AI? If they can make decisions very fast, can we can we think they already have the intuition, the way of intuitive way? So maybe it can so we think and in my opinion it's a functionalism. So yes, so that's my opinion, but yeah, maybe too optimal or too
Optimistic.
yeah.
Gordana, I can see your hand.
Yes, I have an article, very new one, together with Professor Gianfranco Basti and my PhD student Tobias Holstein. We have been addressing exactly Marcin's problem, and the proposition is to train, exactly as Professor Wang says, to train the AI to train on human data, train those neural networks, this the first intuitive level, and then have another machine which has propositional logic and very advanced logic to control the first one. So that's a proposal. I put the article in the chat, but we are totally open for discussion because it took us more than 1 year to get it published. And we discussed with very many reviewers and specialists and so on. This is unsettled question, but it is a proposal how to get this fast thinking into robots.
Okay. Thank you. I'm very would like to see that paper in your website. Yes, thank you.
Thank you.
Okay, we still have 2 minutes, so I'm just looking if there are no questions in the queue. Okay. So like using still we have a couple of like 2 minutes. One thing is what Gordana said was very important is I'm just fantasizing, but I could use the expression ethical training for AI systems. Yeah? We are ethically trained from our childhood, and we develop something like very fast reactions. So I agree that training on data could simulate this process. The thing is now, what will be the data which would be fed? Because we know that right now, AI systems like LLMs, when they are trained on data, they can be very often biased. They can be unethical. So the thing is what data should be used for training to develop optimal solution for accountability for AI. Yeah. What do you think about that?
Actually, I am one of my colleagues. One of my colleagues. I didn't. I actually I didn't think about your question. But one of my colleague he wrote a paper on how to solve the problem you asked in a kind way of embodied robots or embodied intelligence. So I didn't read too much. So, but I think it's interesting. Yeah.
Okay, thank you very much.
Thank
So
you.
we are approaching the end of our first presentation. Right now, we are moving to the second presentation by, I don't know, should I address you as Professor Feisun or colleague?
No, I'm
Feisun?
PhD student.
Okay. So our colleague Feisun, who is from Computer Science and Engineering Division of Mälardens University, Sweden. And her presentation has the title Axiology and the Evolution of Ethics in the age of AI. Please go ahead.
Hey everyone, I am Faison from Mälardalens University in Sweden, and I'm very happy to present here today. And I will start my presentation with a scenario case. So, an AI diagnostic system has identified a potential genetic disorder in a patient. To confirm the diagnostic with 95% accuracy, it needs to access and cross-reference the patient's family medical histories stored across multiple databases. But doing so would expose sensitive genetic information about relatives who never consented to this use. The system must pursue maximum diagnostic accuracy or protect family privacy. How do we make this choice? The scenarios like this one are playing out in hospitals, banks, insurance companies, and tech platforms, etc. around the world every day. Today, I will present how we can navigate those ethical dilemmas through axiology and the evolution of ethics in the age of AI, integrating ethical theories via multi-criteria decision analysis. So today's journey begins by examining the ethical imperative in AI, followed by a look at the limitation of siloed ethical approaches. From there, we will establish axiology as our foundation, then navigate the multi-criteria decision analysis workflow. To ground this framework, we will explore a conceptual healthcare case study showing different stakeholders' voices, wrapped up by discussing ethical trade-offs, highlighting the benefits of this framework, and outlining direction for our future research. We are living through a remarkable paradox. AI reshaped society faster than our ethical framework can adapt. Right now, AI systems are making decisions about loan approval, medical diagnosis, criminal sentencing, and educational opportunities. Yet, our ethical guidance often lags years behind those technological capabilities. The urge gaps are everywhere. We see tensions between privacy and accuracy. Do we protect individual data or maximize system performance? Between autonomy and control, how much decision-making do we delegate to machines? And between the efficiency and fairness, do we optimize for speed or ensure the equitable outcomes? Those aren't abstract philosophical puzzles. A predictive policing algorithm in Chicago must balance crime prevention effectiveness against the potential racial bias. A medical AI in rural Sweden must weigh diagnostic accuracy against data protection under GDPR. Those decisions are happening now in different domains. We need innovative, adaptable ethical approaches that can keep pace with the technological change. So this highlights a core challenge. Traditional ethical approaches, when used isolation, often fall short. Deontology focuses on the rules and the duties, give us valuable insights about, such as transparency and fairness, as absolute principles. But it becomes rigid when rules conflict. When transparency clashes with privacy protection, deontology offers no guidance for choosing between the competing duties. Utilitarianism prioritized outcomes, the greatest good for the greatest number. This works well for optimizing overall system performance. However, it may systematically overlook minority harm. If 95% benefit and 5% are harmed, utilitarian calculus might proceed, but is that ethical acceptable? Virtue ethics centers on moral characters and human dignity, asking what kind of moral agents we want our AI system to be. However, virtues like compassion or wisdom are notoriously difficult to quantify for algorithmic implementation. Each approach offers valuable insights, but none alone can handle the complexity of real-world AI ethics. To handle those conflicts, an integrated approach is needed. So, before diving into our frameworks, we need solid ground. The foundation is axiology, the philosophical study of value. Axiology asks not just what we should do, but what's worth protecting and why. It supports ethical pluralism, help us to balance competing priorities without defaulting to single value dominance. Instead of efficiency at all costs or privacy above everything, it creates space for trade-offs between privacy and efficiency based on case. It is also contextual sensitivity, allowing different domains to apply different values. So healthcare AI might prioritize patient safety and privacy, while educational AI might emphasize fairness and transparency. The same ethical framework can yield different priorities based on the scenario. Besides this, it can connect different ethical approaches and movements. Especially in our research, axiology bridges two major movements in AI ethics: the digital humanism, which insists that technology must serve human dignity, autonomy, and democratic agency. It pushes back against reducing people to the data point. The 2019 Vienna Manifesto on Digital Humanism united European scholars and technologists to address AI's societal impacts. Responsible AI focuses on the transparency, accountability, and the governance alignment. The EU AI Act requires a high-risk AI system to be transparent, auditable, and under human oversight. Axiology provides the value foundation that bridges both the philosophical grounding and the governance alignments we need to move forward. Now let's look at how this foundation becomes operational. The framework is built in 3 levels. Foundation layer, digital humanism and responsible AI principle keep us human-focused and policy aligned. Value layer, here is where axiology shines. We separate intrinsic values, the things value in themselves, like dignity and fairness. Also, instrumental values, the things values as means to ends, like accuracy and scalability. This distinction helps us understand when we are trading off fundamental human values against the technical performance metrics. We might accept efficiency loss to preserve privacy and fairness. The decision layer, multi-criteria decision analysis, translates values into action. It is a method used to evaluate and prioritize multi-competing criteria to make informed and balanced decisions. We assign weights, scores alternatives, and calculate ethical profiles. We are not automating ethics. We are making trade-offs explicit, documented, and discussable. So don't worry about a complex formula today. I will use a simple weighted scoring model that is very intuitive and practical. Now let's look at how this works from values to evaluation. Our MCDA workflows has 4 steps. Step 1, to select relevant ethical criteria. It is to incorporate diverse perspectives to define relevant values for ethical AI evaluation. This isn't a top-down imposition, but a collaborative process involving stakeholders from different backgrounds and with different priorities. Step 2, Score options on each criteria. Here uses a simple 1 to 4 scale to evaluate how well each AI alternative performs on each criteria. This isn't about pretending to be overly precise. It's about clearly showing and comparing the value judgments we often make without realizing it. The step 3, assign weights. Here is where values becomes operational. We assign weights based on stakeholders' perspectives and context. For example, accuracy might get 0.3, dignity might get 0.25. Those weights just reflect our value priorities for this specific user case. Step 4 is calculate ethical scores. We multiply each score by its weight and sum to get a total ethical score. But remember, this number isn't a final answer. It is a method for systematically evaluating and balancing different values. Let me illustrate how this framework applies in a real-world inspired scenario. A hospital is choosing between 2 AI diagnostic systems. It highlights critical trade-off between accuracy and patient privacy. Alternative A is an accuracy-focused system. Prioritize diagnostic accuracy through full data integration. So here the accuracy scales to 4 and the privacy is 2. Alternative B is a privacy-focused system. Prioritize patient privacy through consent-driven limited data use. Accuracy scales to 3 and the privacy is to 4. And also we involve 3 key stakeholder perspectives. Physicians, especially in the emergency care, often says accuracy saves life. Speed and reliability are critical. Patient advocates emphasize that data control builds trust. They warn that without strong privacy, people may avoid care. Public health professionals take a balanced view. We must serve diverse communities, so both accuracy and privacy matters. Those perspectives help us assign different weights to each value based on the context. This slide shows how to choose the system according to the stakeholders' perspective and the contexts. Each setting gives different weights to accuracy and privacy. In routine outpatient care, both values matter equally, so we assign 0.5 to each. Here, the privacy-focused system wins. In an emergency department, where lives are at stake, accuracy is weighted more at 0.7, so accuracy-focused system wins. In the community health, where trust and patient control are key, privacy is prioritized, and the privacy-focused system wins by a wider margin. This shows that there's no one-size-fits-all solution. The right AI choice depends on the context and what value matters most in that setting. In different contexts, the weights and results could differ. The framework doesn't prescribe the right answer, but provides a structured approach to deliberate about what's right for the specific context and value. In design AI system, especially in high stakes area like healthcare, education, or justice, ethical trade-offs are not just common. They are inevitable. This framework helps us to surface those hidden tensions, like privacy versus performance or fairness versus efficiency, instead of letting them stay buried in the code or assumptions. More importantly, it facilitates open, structured deliberation. We are not aiming for a single right answer, but for decisions that are context-aware and ethical justified. Finally, this approach empowers a broad range of voices, not just developers, but also the policymakers, ethicists, and affected community to shape AI system in more transparent and accountability ways. To wrap this up, this framework brings ethical clarity to AI design by combining axiology, which is a study of value, and also with the MCDA, a structured decision-making method. It helps break the silos between traditional ethical theories like deontology, utilitarianism, and virtue ethics. Rather than picking one, it helps us integrate them through a shared value-based reasoning. It also moves us from vague ideas to actionable steps, turning big visions like digital humanisms or responsible AI into criteria we can actually evaluate and design for. Most importantly, it makes ethical choices more inclusive and transparent. By making trade-offs visible, it invites meaningful inputs from stakeholders or not just the technical teams. So moving forward, our next research step is to transition from conceptual models like the one previously I showed to applying this framework in real-world AI development and deployments. This will allow us to test it in situations where competing values on the complex context truly challenges in its effectiveness. And thank you very much for your attention, and thank you for your inputs and insights.
Thank you very much, Faye. I don't see Marcin. He is chairing the session, but I can co-chair for the moment. So I would like to see if there is any question from the audience. I don't see any questions. Theodora, do you see questions anywhere?
No, there
Okay.
are no questions.
There are no questions at the moment. Professor Wang, are you here? I would like to connect those two presentations. Okay, we don't have Professor Wang. Let me start with a comment or question to Faye. How do you see the possible application of your approach to military applications?
I think it's kind of, as I said, it's not to force an agreement. It's based on the situation. So I think it could also work, but as I said today, I only show the simplest MCDA method because it's a lot of much complicated one with much more calculations. So I think they could find a method to use because I really think this framework is very dynamic.
Thank you. Marcin is here, so
Yeah,
please.
I'm back. Today is Friday, 13th. In Europe, it is bad day. It turns out that in Japan, it also could be. So sorry for...
We didn't find any questions in the chat or questions and answers. Professor Wang is here. Okay.
Sorry, because there are some noise, so I didn't. Yeah. So actually, I didn't have a very good problem for you, Sun Fei. Yeah. So, but I take a look at one of your presentation. You talk about the how to calculate the accuracy of and the patient's privacy. You use values, numbers, and
Yes.
kind of a computational way. So actually, I don't understand if it's actually if it's possible for you to first you to get the first hand data which is accurate. This is the first question, and the second question is even if your model is very efficient, so, but but is it possible to put your motion into practice? Because for example, in China, in Chinese hospital, I think this is it's kind of a very difficult, complex situation, and the relationship between doctor or between hospital and the patient is complex. Is very how to sensitive. So how to apply your model, your plan, your program into practice. I think you should also think about the scenery as a practical scenery. So my second question is how to get those data of the theory of the Chinese hospital situation, some sense into your program, into your computation. So that's my question. Thank
So the goal of this framework isn't to force agreement. It's just to make those differences visible. And we can talk about it openly. As you see the data, they are subjective, to be honest, because we assign the weights involves its judgment. As I said, we have different scenarios, we have different stakeholders. And the purpose of this system, we're gonna be openly and transparently to hear those advices from those stakeholders. As I said, we do not want to design an AI system, just listen to the technician people, because they may not know the scenarios in real world scenarios. But the people, let's see in the emergency room, they know what they need. And I think their voices much more important for those technicians to design, deploy the system, AI system. I think that is the purpose. I said those numbers are not just, we test it, we get data set. It's subjective. It's from the people's opinions, and who involves this voice are very important. And we wanted to our AI system to be openly transparency. So only the people's voice get in, and then can make this entire system more trustworthy. So it's different. It's ethical framework, value choose. So you couldn't just exactly, I want this one 0.45. So it's kind of trade-off. We're gonna hear different voices. That's hope I can answer your question. So of course, this is just conceptual scenario, and what we use is the simplest, just accuracy and privacy. In the real world scenario, the situation much complicated. That's why our next research is to apply this one, to see how it works, and if we need to change somehow to make it fit the real world scenario better.
Yeah, thank you.
Thank you.
I have a question because I was off connection. I don't know exactly, but I can only like refer to the discussion now. So in this case, when you are saying that these weights will depend on a practical outcome, this looks like that we have to consider some kind of network, yeah, and it will be some form, not neural network, but some kind of process which is similar to what is happening in neural networks. Yeah, that in this case we are adjusting weights, and this way we get some possibly improvement, or if we go in the wrong way, we will get worse results. But in this case, my question is, should we consider some kind of hierarchy within this network? Yeah, so multi-layer. Yeah.
But as I did a presentation, and it's not top-down. It's like in the hospital, as a head of hospital, he might not know different departments. They need a different kind of AI priority. So what we want is we want it, and also we want the entire system to be transparent and trustworthy. And then we need to hear the voices from different, like as I said, please.
Maybe I can help Martin explain Martin's question. Let's say in the case where you have experts who have opinions, and you have different sorts of public who also are stakeholders and have opinions and their weights. So can you imagine that scientists who know 10 times more than the general public have higher weights than the general public? Or
Yeah, yes, that's for sure. But the design is based on context to find a compromise. We do not say you must have this one. But if experts' opinion is openly transparent, so others, I don't like this one, or I'm totally agree. But after I hear your explanation, I might change my mind. And also, at least the other people are gonna think, okay, this system could work because they have reasoning. So we try to show everything publicly, transparent. As I said, my working is about responsible AI. And responsible AI is, you need to let people to see it and trust it. We think explainability is limited. So another way to let people to trust it, to believe it, is transparent. So this system can make the value, the value, you choose those value very clearly. So when you know it, see it, you're gonna much believe in this AI system. I think that's the purpose.
Yeah, this is like a good. But what do you think about hierarchy? Not in the operational way, but the thing is, for instance, ethical considerations, which would provide some kind of input into values which we are putting into the network.
Yes, we believe so. And also, as I said, the foundation of our framework is based on digital humanisms and responsible AI. So it means which we're gonna focus on the humans. So the value gonna be on the human focused, and also responsible AI to make it responsible, transparent, and also compliance with the laws. The EU AI Act gonna apply in August. So we want both compliance with our values and the policy.
Okay. Okay, thank you very much.
Thank you.
I lost a lot, but at least even these few minutes gave me a lot of good thinking and value. Thank you.
Yes, because we are also trying to do our research. So next step, we want to apply it in the real world scenario so we can test it. So we want to just want a framework. We want to test it, see how it works. That's our next research.
Are there any other questions? I wish I had good connection all the time, and then I probably would have more questions.
We are looking forward to see your articles in the future, because she is going to apply it to real world cases.
This will be very interesting to see how it works in practice.
Yes, it's also what we try to do. But we think it might be a lot of issues, but we'll see. Hopefully, because we want to apply it in different scenarios if I have enough time in my PhD study, like education, healthcare, and then we can see in different context how we're going to choose and kind of weight our values. Oh, I have 1 minute. 1 minute. I think maybe next time I should present a little bit calm and a little bit slower. So.
No, like what I could see was very good and very clear. So.
Thank you. It's my first conference presentation, so a little bit nervous.
Oh, but you did a very good job. So.
Thank you very much.
Well done. We are happy to have representatives of all stages of researcher, from the beginning until the very old people. So.
Yeah, so maybe in the future I can present again with my case study.
Yeah, it will be interesting.
We're gonna have a series.
Okay, So
Thank
thank you
you.
very much. Thank you for answering our questions and to everyone for asking questions. And we'll be moving to the next talk. This time will be by Professor Attila Egrinagi from Akita International University, Akita, Japan. And his talk has title Thought Structures and Their Morphisms.
Okay, thank
Please,
you.
Attila, go ahead.
Just a moment. Let me make it full screen and share it. Okay, so thank you very much for this opportunity. And I think this work will fit into the picture of AI as like, is the AI really thinking, or what do we call thinking? What do we call explanation? What is understanding? But to be sure, I'm more interested in the human understanding because I'm happen to be one of those. So hence this topic. And this is a joint work with Professor Miklós Hoffman from Hungary, a former colleague. And well, let me start. And let's start with a puzzle. Okay, I think many of you know this puzzle, but it's a very old, and it's probably the oldest chess puzzle. So you just have to get from this configuration on the left to the right, and then while you use the L shape, the knight jump. And of course, you cannot have two knights at the same time in the same squares. So the question is it possible? So can you jump around with these knights that you swap the white and the black knights? And it's like, sure, if you haven't seen this, I give you a moment of thinking, but it is difficult enough to solve it in your head. Okay, the way I do it usually with high school students that I give them the board and the 3D printed chess knights, so they have time. They can play around. Okay, and even if when they have the board, it takes a few minutes before someone says that, oh yeah, sure, it can be done. And then I ask, it's like, how many moves? And then it's like, yeah, people get confused with counting. Okay, so that's the point here. You have a non-trivial challenge, and I will make it absolutely trivial, and you will see the solution. So yeah, this is not about this puzzle. So I actually just reveal the solution. So mathematics makes things easy. You just switch the representation. And what is the problem? The problem is that this L-shaped jump by the chess knight is a bit complicated. So you don't want to keep track of that. So we just number the squares, and then it's like you can write down, okay, here is the first attempt in the middle. You have the graph. And then when you do this, you realize that, oh yeah, this is not useful at all. What's the problem? Well, because you number the squares and the numbers are in order, and you use the properties of the numbers that are totally irrelevant. Okay, so then you realize that, well, okay, what's the neighboring relationship? That's what counts. Then you write it down, and then you put in the graph. Now we are on the right. You put the let's say the black knight and the white knight, and then you see it's like, oh, they just have to move 4 each, and then it's just a rotation. So every piece has 4 moves, 16 in total. Okay, that's very trivial now. 16 in total. But see, what you have here is that you have 2 domains of operations. One domain is the actual chess position on the actual chessboard, and the other one is the graph, the mathematical representation. And that's like, what's the connection? That the operations are compatible. It doesn't matter whether you do it on the chessboard and then you see that is what's happening in the graph, or you just do it on the graph and then it's like trace it on the chessboard. Of course, doing it on the graph is a lot easier. That's the point. So you use the easier domain, the operation there, to understand the more difficult domain. So yeah, this is, I mean, of course, if you are trained in mathematics, you say that, well, sure, yeah, that's called a morphism. It's a structure preserving map between two structures. And then it's like everyone knows this, even as well, you are learning in school a bit of algebra and geometry, and you realize that numbers are points on a line, or just a logarithm. This famous equality for logarithm. This is actually just like the formula of the morphism in general. And if you are a mathematician, then you are familiar with linear maps, graph homomorphism, order preserving maps, and it's like, well, they are everywhere. Okay, so that's so far so good. So here's our thesis, is that yes, it's finding compatible operations. Okay, that's again compatible operations. That's where we have the emphasis. In two domains, it's not just a tool in mathematics, but this is actually a universal mechanism for understanding, reasoning, and explanation. So both for human and artificial intelligence. Okay, and then it's like, well, okay, yeah, this is a bit more ambitious claim. And then you might say that, oh, but it's like, well, anything like any model is basically like that. And we agree, and we would say that morphisms are used explicitly and implicitly in a wide variety of scientific and everyday cognitive activities. The problem is that there are some standard misunderstandings that reduce its usability. Okay, and that's like I'm trying to address those. Okay, it was like everyone is happy still. It's like no questions just yet. Okay, let me turn the knob for the controversy a bit higher up, and I was like, so what are the questions? Well, what is understanding? What is explanation? That's actually our main motivations. And well, we know what these are. You have the common sense answers. Understanding goes from not knowing to knowledge. And the explanation is something that enables this transition. And of course, it's like, regardless your field, you have some theory about explanations and understanding. But is there a general theory? And then it's like, okay, here comes the idea. We say that, well, it seems that mathematics unintentionally, so mathematics, it's like tries to understand the world and it's like come up with mathematical theories, whether you mean the physical word by word or you mean mathematical objects. Still, yeah, mathematics is about understanding, and it's unintentionally produced a grand theory of the process. Well, it's, if you like logic, then you can put it that way, that the premise is mathematics is about understanding the world. Mathematics also studies itself. Okay, so therefore mathematics studies the process of understanding. What's the caveat here? Well, it's like some perspectives on mathematics may render this observation not so immediate, but the bonus is, if you think about it, oh, now we have if this is true and if can be defended, then we have a very nice answer now for the question. It's like, what is mathematics good for? Well, that's a typical student question. It's like, oh, what is this good for? And that's like all the answers that even the students tend to repeat, saying that, oh, mathematics is good because then I can count the money I get back when I do shopping. And it's like, when I hear this, I'm scratching my head. It's like, well, do you still pay by cash? And it's like, okay, yeah, then do you really count? I mean, it's all counted by the computer. So that's not a useful use. But it's like, if you think about it, it's like, oh, this is actually gives you a perspective of a general mechanism of understanding itself. It's like, well, yeah, then you are sitting on something big and it's not just the everyday arithmetic. Okay, so maybe it's a bit of time to give more details what we mean by the idea of morphism. I already mentioned that there are two domains to work in, and there is a special relationship between the two domains. Okay, and that's the morphic relationship. In practice, one of the domains is easier to work with, more familiar, and the other one is less so. So we use the understanding, the knowledge in the easier one, the more familiar one, in order to understand the less familiar one. And how can we do that? Well, it's like if you have the compatible operations. So you have a morphic relationship. That exactly means that you can move between the two domain. It's like it doesn't matter if you do it on a chessboard or you do it on a graph because it's compatible. There is a nice correlation, not correspondence between the two, and that's the the standard algebraic formulation. Again, phi is not just this special, I wouldn't say function, because later I will say it can be a relation as well. We can have morphic relations as well, but it's a general correspondence. It doesn't matter whether I do it first in the domain, so A composed with B, or first I transfer all the inputs and do it there. These are compatible. So what we suggest is that traditionally, so what is the foundation? What is the traditional way of starting mathematics? That's set theory, and then you have the basic relation that something belongs to a set. That's sort of the fundamental thing. And we would say that, oh, maybe it's better to start from this little diagram. So you have X and Y, whatever they are, and then you have the operation, the movement, moving from X to Y. And so this could be like this actual sort of dynamic relationship could be the base to start mathematics as well. So what could this be? Well, I mean, I'm coming from algebraic automata theory. So for me, these would be X and Y, some states of some computing device, and A is the state transition. But if you are coming from logic, you might say that, well, X and Y, there's sets of statements, and the movement is the logical inference. Or what we are promoting here is like, well, you have your thought structure, and moving from one thought to the other, that defines this structure. And thus the canonical example is the map, locations in a city on a map and walking there. And of course, the key thing is composition. And if you think that, oh, this person is talking about category theory, well, yeah, it's very, very relevant here. But I would maybe that would be another talk, saying that it's like, why not completely just saying that, oh, you just use category theory. But anyway, there is the composition. Okay, so doing actions one after the other. With the chess example, it's still the idea. It's like, while you have a configuration and you want to continue from there, it's like you have a sequence of moves. That's where you want to find the solutions. And then it's like, so what would be when composition is not working? You can imagine, again, reading a mathematical proof. You understand every step, but you still don't understand the proof. That means that in your head, those steps are not composing. Okay, so that's what's missing. I mean, from automata theory, so for me, A composed with B is just AB. Of course, in category, you write the other way around. But okay, we don't need the notation here. Composition is the key, because if you so once we looked at like sort of the literature in philosophy and we search for homomorphisms, then it's like it comes up, oh, a scientific understanding is like you describe something and you have n-ary relations. But if you have n-ary relations, not just binary relations, you don't have the composition that nicely. So you just transfer static structure, and then you don't have any movement. And we are saying that it's like, oh, understanding and it's like explanation. That's a movement. So you cannot just get rid of that. But okay, here is the canonical example. Okay, so everyone, even who for whatever reasons didn't take any mathematics courses, hopefully can understand this. This is, by the way, my birth town, and that's where my collaborator lives. And then it's like, that's the street. This is on the map. There is a very important thing here is that the usual misunderstanding when talk about morphisms in the context of philosophy, then it's like, oh, it's isomorphisms, and isomorphisms don't. So when you have exactly the same structures, yes, isomorphisms are beautiful in mathematics, but those are actually not useful in real life, because you want to have compression, you want to forget structure, and that's what the map does. And when it doesn't do that, well, I mean, it's like, here's the tale of the one-to-one scale map. It first appeared in Lewis Carroll's, not in Alice in Wonderland, but it's less known. I even forgot the title. But anyway, the idea is that they wanted to have better and better maps, and eventually they figured that, oh, if the map is detailed enough that it's the size of the country, oh, then it's like farming becomes troublesome. Okay, and then as the idea was good enough that Bohr has also talked about it, and then it's like he brought in, it's a very short story, but he talks about science. So it's like the map is sort of a metaphor for science. So you have a model which is an exact copy, an isomorphic copy of the thing you want to understand, doesn't have much in understanding. And also, of course, then Umberto Eco brought in the idea that's like, oh, there are actually some logical problems with that as well, because if you have the map, then the map is inside the map. And yeah, so it's a fun story. But you see that isomorphisms are not enough. You have to have this compression. In my example, it's like I did a lot of work in trying to understand how to utilize like the superhuman AIs, like in playing Go and learning, allowing humans to learn the game better. It's like, what is a good explanation? It's like if I have a chess puzzle for you or a Go puzzle for you, and I give you the game tree, which shows that it's like, oh, every move goes to losing except the one, which is the right move. Is that a good explanation? No, it's not a good explanation, because you want to have a compressed one. I want to have a causal model. Because you move your king in the wrong spot, that's why you lose that. That's why you have to do that. Again, compression. So then it's like, yeah, think about trying to bring it to the everyday thinking. So how does this work? And well, that's where, for the lack of any better word, we call it thought structures, because we want to emphasize that, oh, it's not just logical thinking. Okay, so it's like you have these train of thoughts in your head, ideas of one after the other, and they are connected in whatever ways. Okay, this might be just a memory recall, that might be even logical inference, but all these mental actions. And it's like, I don't want to go into the details that your brain might be doing many things, and what comes up, what just bubbles up to the conscious level, that's just the tip of the iceberg. Well, I mean, it's like, I would like to think on the conscious level. So it's, you have a connection. The thing is that what thinking is following a path in your thought structure. And the question is that when you try to understand something, at least someone, and listening to someone else, you are actually trying to find whether your thought structure is compatible with what the other person is saying. So it's communication is traversing thought structures and at the same time. And then you say that, well, sure, but this should be partial, because you can have an agreement. You look at someone, it's like, oh, and you have a conversation, it's like, oh yeah, I totally understand you, I totally agree with you. But maybe if you ask one more questions, that you realize that the next operation is not compatible. So in everyday life, we don't have this beautiful homomorphisms like in group theory, that it should be completely defined. And it's like, okay, So here's my silent protest for AI generated images. Here's a non-AI, non-artist rendering of the idea, because I do it myself. So since the generative AIs appeared, I started drawing myself. You see, this is just a caricature. It's like the point is that you want to build a model, and understanding is that when you have the model in your thought structure, and it doesn't matter whether you go out and check what's going on or you move it in your head, if there is the agreement compatible operations, then you have understanding. And then, of course, there are some consequences here. So understanding is indirect. But I guess at this point, people are thinking, oh, are you talking about cognitive metaphors? Yes, that's one of those. We want to understand something in terms of something else. But it's very important. It is very, very rare. Okay, so it's so you cannot just use anything to understand something. Okay, it has to be a model of something. And I already mentioned it should be partial to some extent. So to summarize, what we are saying is that they are dynamic composition at the core. Okay, and it's not necessarily isomorphisms, and also not required to be functions. We have morphic relations, and we use this automata theory all the time. And they come in pairs. It's like you can always turn it around. I don't say it's isomorphism. You can have a structure forgetting one, and you turn it around. You still have a relation which has morphic properties, and they need not to be totally defined. That was the reason. If you think about cognitive metaphors, the metaphors we live by George Lakoff, and when I read it first, it's like, yeah, why don't you say it? This is a morphism between two structures. And then it's like, as the anniversary edition, there is an afterword when they said that, it's like, oh yeah, we thought about it. But in mathematics, you always have to have the two domains fully defined. And that's why it doesn't apply, because then it excludes the possibility of creativity. Okay, so yeah, even in mathematics, that's like often we just check it for the generator, so it doesn't have to be totally defined. What algebra gives, Occam's razor comes out, because it's like if you have a smaller model, it's easier to morphically match. Okay, well, that's one idea. What are the things that are very difficult to understand? Those structures that admit very few morphic images, as like the monster groups in finite simple groups, and you can define in a funny way the emergence, those morphic images that are actually not substructures, and they are already in group theory. And well, here's my definition of computer. Computer is a physical system which is a morphic image of a universal mathematical model of computation, and that this excludes a lot of arguments when they say that, oh, the paint on the wall is already computing something, or because I can have a correspondence. Well, you can have a very specific match, and matching one particular computation with that particular state, but it's not universal, because if it was universal, we would use it instead of the expensive computers. So AI benchmark. That's what everyone is talking. Oh, is the LLM thinking? And my question is that, well, you can convince me if you show me that you can somehow look at the neural activation patterns, and you can sort of group them to have a morphic image onto let's say the causal model of that particular domain the AI is talking about, then I'm convinced. Okay, so this could be and that's like, I think that's where things are going when people are like, they can look into the AIs. Okay, yeah, I think I stop here. It's like, let me just link to this draft paper where I have more details, and I stop now. Thank you.
Thank you very much, Attila. It was very interesting, and for me, it is especially interesting because I am very much interested in using mathematics in everywhere, and especially in philosophy. Let's see if there are any questions in the queue. I think it could be issue of people very often feel like intimidated when the word mathematics is used. But I think that you presented your ideas in a very good, very clear way. If there are no questions at all, then I will ask my question. Maybe you remember 7 or 8 years ago when we had a seminar. I was at the same university. I'm actually Professor Emeritus from the university where Attila is professor. And we had a seminar, and I was talking several times about cryptomorphism. Yeah, there is this very deep issue of some structures, like for instance, group, can be defined in many different ways, which cannot be linked by homomorphisms, because conceptually they are not fitting together. Group can be defined with so-called different signatures, as a one operation algebra, or two operations, or three operations, depending on how we want to do it. And then we have this ability as humans easily to go from one to the other. The problem is that within mathematics, it is impossible. Just in case of groups, Berkov many years ago gave answer how to switch between these two several different definitions of a group. But we can find other more distant theories. So here is my question is, do you consider cryptomorphism?
Well, okay. Well, yeah, that's it's good that you mentioned. That's something I would like to look into. That I don't remember it in detail, but what I understood from here, I would say that, well, I think we would need to find the level on which it actually becomes a morphic relation. So there is probably an abstraction level when they meet together. And then that's where you can exploit the compatible operations. But okay, I have to actually look into that. It's like I will search just now. It's like cryptomorphisms.
Yeah. It was many years ago, because I proposed some approaches, but this is not crucial. Gordana, you have a question.
Yeah, it's a funny question. I wonder, you said you cannot use anything to understand something or something like that. And I was thinking of a painter, Giuseppe Arcimbaldo, who was using vegetables to present a human portrait. So you can represent a human using vegetables. Could that be an example of such a mapping?
Well, that's certainly it's an interesting connection you mentioned. I would say that it's like basically you use vegetables to draw a picture. It's more like the connection is between the picture and the vegetable, and then it's like the picture can depict anything. So I don't think this is the destructing blow for our theory, but it's certainly an interesting way to push the idea. I mean, that's exactly the view. I mean, I don't. My purpose of bringing mathematics in is not that it's like, I want to clarify everything and its understanding should be clean. It's like I'm just claiming that it's like whatever you do, if you spell out the yeah, I just wrote it there. State your compatible operations. That can deepen your understanding, and that's why we always say, because yeah, as regarding answering Marcin's question as well, it's like I try to sort of not give the mathematical details, because someone might say, oh, you are just talking about category theory. And then it's like, well, then go and do category theory. You start reading that, and then it's like, whoa, okay, I don't understand this. How does this help the understanding? So there is a very steep learning curve, but I think that can be helped. So it's like I'm actually, yeah, literally trying to bridge the mathematical theory and the everyday understanding, and it's, in my view, the mathematical precision is not against the creative expressions of well, the human mind.
In some sense, Stephen Wolfram was, I don't know if you were watching it or
I will
participating at
watch
this
it
time.
night here.
So
and
in some sense, he is presenting basically, he's not saying in this way, but I could see close relationship between Wolfram's approach and your approach, where he, of course, is looking from specific perspective, very general but specific perspective. But basically, I think goals are quite similar.
Yeah, I heard him many times talking. So yeah, I will watch his talk here as well. But yes, I think so.
Okay, so we are reaching end. Thank you very much for interesting presentation. As you see, you stimulated us to discuss these issues. And we are moving to next presentation, which will be by Professor Anna Sarosiek, University of National Education Commission, Kraków, Poland. And her talk has the title Cybernetic Approach to the Internationality of Artificial Systems, a regulatory function instead of representational one. Anna, please go ahead.
Thank you for the introduction. I would like to propose a shift in how we understand intentionality in artificial systems. And my proposal is moving from the classical representational models to cybernetic and biological regulatory framework. And my presentation is part of my broader inquiry in the foundation of cognitive science and the philosophy of mind and philosophy of artificial intelligence, of course, but it raises a fundamental question: how can we recognize or ascribe intentionality as a system that do not possess symbolic understanding? Which one doesn't possess consciousness, but act purposefully within dynamic environments? So I would like to start with my philosophical intuition and a short and very simple explanation, because I think I own you. Because in my opinion, of course, in my own opinion, intentionality may not follow from intelligence or consciousness. Rather, I think it may be their preconditions, because before any system, living or artificial, start to act intelligently or to know or to understand or to be aware of something, it must already be oriented towards something. That is, it must exhibit this kind of directness, a basic kind of being about, even if not symbolic or reflective. And this brings me to guiding question. Can intentionality exist without representation? Is the capacity to be about something necessarily dependent of internal symbols or semantic context? And traditionally, intentionality has been defined as a directness of mental states toward objects. This is the view rooted in the work of Franz Brentano and later developed by Searle or Dennett and many, many others. Within this tradition, aboutness is thought to require mental representation, symbolic codes, and even semantic maps. But what if this assumption is mistaken? What if the system can behave as if it were goal-directed, without explicitly representing the goal? This possibility challenges this paradigm, this classical paradigm, and opens a new line of inquiry. What if intentionality emerges not from meaning, but from regulation, from the dynamics of adaptation, feedback, and systemic persistence merely? So the guiding question becomes, under what conditions can a system be said to act as if were intentional, even in the absence of representation, semantic content, or reflective awareness? So, when we shift our focus away from this kind of symbolic representation and toward the ways in which systems regulate themselves, a different picture of intentionality begins to emerge. One that resonates deeply with my favorite theory of Umwelt of Jakob von Uexküll. And in this view, intentionality is not only the internal semantic property, but this is the relational dynamic. A system is intentional insofar as it is functionally oriented toward maintaining its own viability within a given environment. And this means that intentionality can be understood as a form of regulation. The system capacity to modulate its internal states as a form of regulation. And this system is doing it in response to external changes. The main goal is to preserve coherence over time through, of course, the feedback, or what is called in Uexküll theory, the functional circle. Just as every organism lives in its own Umwelt, this is the meaningful world shaped by sensory and motor affordances. So to do artificial system operate within the structured sensimotor couplings like sensor spaces, data flows, actual loops. And this system do not represent the world. They co-regulate with it. And this, from cybernetic perspective, intentionality becomes a question of how well a system sustains its functional identity in the face of many perturbations, how it adjusts, adapts, and persists through continuous feedback. So I think rather than asking whether a machine understands or know or feel, we might ask, does it system regulate its behavior in a goal-consistent way? Or does it maintain homeostasis or something what we can find as analogous to it? But all of them through adaptive interaction with the operational environment. So to better illustrate this regulatory view of intentionality, we can consider a few biological and technological examples when behavior appears goal-directed without the representational content. So, for example, this is just one example for many others. Octopus arm control. Each arm of octopus contains local neural circuits capable of semi-autonomous coordination. It can grasp, bend, and adapt to obstacles without commands from the central brain. intentionality here is local, is embodied and very, very relational. This intentionality is emerging from decentralized feedback control. And from other example is homeostatic regulation in humans or other animals. And in artificial systems, we can, for example, adaptive robots. And these adaptive robots modulate gait or reroute movement in real time using sensor input. And these robots don't know what the slope is. They just respond to the true real-time motor regulation within a dynamic terrain. Probably the self-driving cars also integrate, maybe not probably, for sure, they integrate vast sensor streams to stay in a lane, avoid collision, and reach their destination. They are not building the symbolic world models, but through continuous regulation of speed, direction, and responsiveness. So what unites decades? In all of them, biological or artificial, what we call intentionality emerges not from knowledge, but from co-regulation. Each system, biological and artificial, acts within its own umwelt, not because it understands, but because it persists through feedback-driven adaptation. And having seen examples of systems that act purposefully without representation, we can now ask, under what specific condition does a system, biological or artificial, begin to exhibit something like intentionality? And I propose 4 independent conditions that together define minimal intentionality. It could be minimal artificial intentionality or cybernetic intentionality, but this is something what is the fundamental state of systems without thinking about this kind of hard problem like mind or consciousness or even intelligence. So the first condition is operational autonomy. I think this is, the system must be capable of sustaining its activity over time, not merely by reacting to inputs, but by preserving its internal organization. And I think this is not trivial independence, but functional self-maintenance. The second one is the local teleology. Behavior must be oriented toward the achievement of preservation of functional relevant states. This teleology is structural, not semantic. And this teleology arising from the system's architecture and embedded goals, not from symbolic plans, because there is no plans, no mind, all the blueprints. The third one is internal feedback. And this is very important because it's showing us that the system must be able to monitor its own internal states and adjust accordingly. This recursive regulation, I think, is the key. The system doesn't just react, it modulates itself in relation to how it is functioning. And the last but not least is resilience to perturbation. The system must adapt when disturbed. If the environment is changing, the system must be capable of recognizing its behavior, rather than falling or freezing. This is the mark of regulatory flexibility. This is not rigid programming. And together, these four features, autonomy, teleology, feedback, and resilience, do not amount to consciousness or representation, but at first they establish a very broad framework within behavior can appear goal-like. And this behavior is very coherent and is very persistent. And I think this coherence, when observed from the outside, is exactly what we often respond to, and call intentionality. So before I move forward, it's important to clarify how this regulatory account of intentionality diverge from well-known frameworks, because I should say what is not. And I think, but first, that this is not symbolic representation. This is not symbolic representations. This model does not assume that a system must manipulate internal symbols referring to external states. We can reject the premise that semantic content is necessary for intentionality, because the goal is the functional coherence. And this is not a meaningful interpretation. This is also not the functionalis, as we know, because the traditional functionalism defines mental states by fixed input-output mappings. But regulatory intentionality is dynamic and recursive, and is centered not on outputs, but on self-modulation and adaptive persistence. This is also not biological enactivism only in the sense of Maturana and Varela, because while enactivism rightly emphasizes embodied interaction, it often restricts intentionality to living organism and living system at all. And this cybernetic model extends minimal intentionality also to artificial agents and exhibit the relevant regulatory properties, even without metabolism, for example. So the cybernetic models is not about thinking machines, not about symbolic minds, or even not about these what we call artificial selves. This is about recognizing when a system begins to behave in teleologically coherent ways, even if there is no narrative and no consciousness and no semantics involved. So I started to think about minimal artificial intentionality. And if we accept that intentionality can emerge through regulation and feedback, we must also consider its not biological instantations, and what I call minimal intentionality. This form of intentionality does not depend on human-like meaning or desires or beliefs, like Dennett said. Instead, it arises from a system capacity to maintain functional stability. And it's going through continuous modulation of internal and external states. And many contemporary artificial systems already display these features. For example, reinforcement learning agents just adjust strategies to maximize reward in variable conditions. And they do not understand their actions, but they recognize behavior to preserve internal utility structures. Or large language models. They generate context-sensitive outputs without possessing intentions. So their coherence is not symbolic anymore in the classical sense, but is mainly statistical and structural and adaptive. I think this kind of system exhibit this local consistency and responsiveness that arise from dynamic regulations. And again, not semantics, because even these semantics maps in large language models doesn't possess any semantic in this kind of first hand. So from our external perspective, these systems appear to act as if they had goals. And this as if intentionality is not mere projection. It's a consequence of how these systems are structured. And thus, consciousness, for example, is not prerequisite for it. What matters in this presence of systemic properties is autonomy, is feedback, and is resilience that enable a machine to sustain coherent, adaptive goal-like over time. And I propose that intentionality is also better understood as a spectrum rather than a fixed threshold. It is not intentionality. It's not a problem of having or lacking intentions, but of how it's instantiated, to what degree and with what structural consequences. And at the one side of this spectrum, we have this human level intentionality. It is reflective, conscious, and norm sensitive, for example. In the middle, we've got animal intentionality. This one is embodied, sensimotor, and mostly experience-driven. Animals engage with their environments in adaptive and sometimes strategic ways. And their Umwelten are rich, but very specific, grounded in the species-specific modalities. And the minimal end, we encounter artificial intelligence quasi-intentionality or proto-intentionality. And this one is not conscious, but is very effective. It's organized around goal-like behavior. This system just stabilizes patterns, adjust based on feedback, and persist in achieving tasks. And these gradient perspectives allow us to situate artificial systems meaningfully without inflating their capabilities. It also respects the diversity of cognitive architectures, natural and artificial, and how each interacts with its world, with its own Umwelt. Ultimately, this reframing shifts the focus, not from the presence of intentionality as such, but from the question of how systems sustain orientation, continuity, and meaningful interaction with their respective domains. And so how does goal-directed behavior arise without symbolic representation or conscious intentions? One key answer lies, I think, in homeostasis, because this is the capacity of system to stabilize itself through continuous regulation. And also, the homeostasis is a very simple model to implement in artificial system. As I would like also to call a Bateson words. Mind is not a substance, but a relational pattern, a dynamic interplay of difference, feedback, and self-correction. And from this view, what appears as purposeful behavior may be nothing more, nothing less, that the emergent product of multi-level regulatory loops. And also in biological organism, homeostasis governs process like temperature control, nutrition regulation, immune response, and many, many others. But the same principle applies to cybernetic system. When feedback structures support internal coherence under varying conditions, purpose-like behavior emerges. So crucially, this emergence is not programmed or representational. It's not the result of modeling the world by programists, but of remaining stable within this world. It's not about something in the semantic sense, but it is for something in the functional sense. And it also, paradoxically, echoes Dennett's evolutionary insight. There is no mystery to agency, only the accumulation of functional layers that eventually give rise to intentional systems. And from this point, from this perspective, intentionality is not a top-down imposition of symbolic purpose. Intentionality is not pre-installed, but it emerged from the interaction of adaptive subsystems. So we can see this is the bottom-up effect. The system behaves as if it had good goals, but because its architecture favors the preservation of structure and continuity in changing environment. And this is why artificial systems, even without awareness, may be still seen are participating in minimal forms of intentionality, if their organization enables such emergent stabilization. So rather than asking how a system represents a goal, we can ask how it remains oriented, how it regulates deviation, how it persists coherently. Of course, there will be a design implication. If intentionality can emerge from regulation rather than representation, then the implication for artificial design are both conceptual and technical. First, we must rethink the goal of design. I think rather than building systems that represent the world accurately, we should design systems that sustain coherent interaction with the world, systems that adapt.
Okay, I have to interrupt you. We already have only 4 minutes, so it would be good if you could give time for questions.
Okay. So the final question is just, can intentionally exist without representation? This is the good questions. And I think I started without it. And can intentionality just arise from this cybernetic functional feedback? Thank you.
Okay. Thank you very much for presentation. And now time for questions. There are questions. Are you familiar with topological? It is for Attila. Johan Largo, I don't know if this is to you. I'm a little bit lost. Okay, Gordana, please go ahead.
Anna, thank you very much for excellent presentation, and I share your ideas totally. I would like to know Do you imagine this level of cybernetic direct coupling to the environment resulting in symbolic level as an emergent property of this physical level?
Yes, I started my research, and this is just beginning of my research. I've observed a colony of ants, and I started also. I've of course making an ethogram and put this all ethogram to artificial life, and I can see that these local rules, which are connected to the very simple feedback and very cybernetic rules in my artificial system, are behave like these living ants. So I can imagine that this cybernetic approach is very simple to implement in artificial systems. So I just thought that this is just the beginning of research, but I can see that it could be a very good way.
Thank you very much.
Okay. Any other questions? I don't know if this question here is so I have very short question.
Yes.
In what you were presenting, the key point were regulatory functions, and on the other hand, when I look at this, I think that how we can explain that our sensory system is so sensitive. We can distinguish something like 2 million of different colors. It is difficult to imagine that this distinction, and of course, this is related to intentionality in sense of looking in the word distinction between two objects of different colors. So how we can explain this in terms of regularity function, the sensitivity to very, very tiny differences.
Yes, I know, and this is very complicated, probably, and I think we should switch to cognitive science right now and just look like the answers like in our neural work of our visual traits. But if I think about this kind of sensomotor sensitivity, I think this is kind of ability which can emerge when we can to make this functional circle more and more and more complicated. This is also what is seen in Umwelt theory, that if we are looking for the very simple organism, we can see that their behavior is very simply. But when the organisms are more and more complicated, there are more functional circles, and there can see, for example, more colors. Of course, we are not talking about shrimps right now because.
Yeah. Okay, thank you very much. Thank you for presentation, for answering our questions.
Thank you very much. Sorry for the time.
No.
I haven't
so
seen the timer.
it's okay. So I would like to propose 5-minute break because we are approaching invited talk. After invited talk is break, so we can move and to give like 5 minutes for rest, and then we'll come back and we'll have invited talk. Okay. Welcome back to our conference, and our next speaker will be invited speaker, Professor Dr. David Games from Department of Computer Science at Middlesex University, London, UK. The talk will has the title Intelligence and Consciousness in Natural and Artificial Systems.
Okay, well, many thanks to Masa and Gordana for inviting me. It's been a very interesting conference. I haven't been able to go to everything, but I've been dipping in and out. And, it's been good stuff. Right, so crack on. Yes, as you said, so as the Masa said, I'm from Middlesex University, and this is kind of a sort of general kind of overview of what I've been working on the last few years. Yeah, so I thought big perspective. I'll try and give that here. Yeah. So. As we all know, there's been loads of these AI breakthroughs in recent years. You've got self-driving cars, human level and beyond human level game playing of StarCraft, Atari games, Go, that kind of stuff. And lots of chat yesterday about generative AI, ChatGPT. Lots and lots of talk about, artificial intelligence reaching or exceeding human intelligence. I skimmed an article a couple of days ago where, people like Sam Altman are saying, oh, in 3 years, we'll have artificial general intelligence. And a load of other people are talking about consciousness as well. Yeah. But all this comes against a backdrop, which is, I guess, kind of what this conference is about. Wait a minute, better leave that there. Is that there's actually no generally agreed theory of what intelligence actually is. We don't even have a way of comparing the intelligence of ChatGPT, for example, to humans, or even humans with animals. Yeah. And so really, a lot of this talk and hype is just, weak, ungrounded intuitions. Yeah, it's not theory-based, it's not science-based. It's like, ooh, look at ChatGPT, it gives us a smart answer to a certain prompt that we chuck in. Yeah. And there's also been a lot of speculation about AI consciousness. That Google engineer got sacked a while ago because, he was talking about sentience of whatever it was, Gemini. Yes, probably intelligence and consciousness are correlated in humans, probably animals too. But when we're talking about artificial consciousness, again, it's like people scratching their chins, looking at a system that behaves in a certain way and say, oh, it's probably consciousness as well. Yeah. Whereas, as I'm going to argue later, there's actually very strong reasons for thinking that we can't infer AI consciousness from AI behavior. So I'm going to try and sort of, address these issues, somewhat boldly perhaps, but, why not have a go? And so my talk's got 3 parts, right? First part, I'm going to talk about what's intelligence. Then I'm going to talk about the measurement of intelligence. It's very important if we're going to talk about AI intelligence. And then we're going to talk about the relationship between intelligence and consciousness. So first part, what's intelligence? This is just summary, right? I'm going to explain, summarize some of the overlapping definitions of intelligence. My own take on this is that prediction's the most important component. That came up in a couple of talks yesterday, right? And I thoroughly agree with that. I think Hector in particular. And then we're going to talk about, possibly related to the previous speaker a little bit, how intelligence operates in a perceived environment or umwelt rather than, some kind of direct interface with the natural or human world. Yeah. And most importantly, I'm going to talk about general intelligence and argue it's a myth. Then we move on to the measurement intelligence. So obviously we're very familiar with things like IQ or G, but these are population-based statistics. We can't use them to compare individuals from different populations. So what we really need is a way of measuring intelligence in a way that can compare, humans, animals, and AIs on a single ratio scale. Yeah, so IQ is not a ratio scale. It doesn't work across populations. So I'm very, very briefly going to summarize my own work in this area on this Perth row measure, which I think could address this problem or something like it. Yeah. Finally, I'm going to talk about intelligence and consciousness in humans because, they're sort of our gold standard systems for measuring consciousness. We can study the relationship between physical states and consciousness, but we can't use behavior to measure consciousness in artificial systems. Instead, we have to develop mathematical theories of consciousness and use mathematical theories of intelligence to study the relationship between intelligence and consciousness in AIs or elsewhere. Yeah? So that's the overview. Now I'm going to sort of crack on with, actually talking to start going. So first section, what is intelligence? 3 parts. I'm going to talk about definitions of intelligence, talk about the perceived environment, talk about the generality of intelligence. So I think we all have some kind of working understanding of intelligence, and that's what's driving, firstly all the work on IQ and G, but also driving all this stuff about AI as well. And my favorite example is Flowers for Algernon by Daniel Keyes. Absolutely brilliant book. If you haven't read it, read it. So it's a science fiction book in which this mouse has this experimental treatment that makes it smarter, and so the mouse can do mazes better. And then in parallel, you have this sort of severely, low IQ kind of person who's really struggling to understand their world, to understand their social environment, to hold down a job, all this kind of stuff. And then they're given the same treatment. So Algernon's a mouse, and then, you have this sort of parallel development of the blossoming of intelligence of the mouse and the blossoming of intelligence of this person. So, over time, they can suddenly do, multiple languages, they can write books, they can understand all kinds of stuff in a way that they just couldn't before. Yeah. So this is a sort of, very nice contrast, I think, between a sort of low intelligence and high intelligence, both in the mouse, but more particularly in the person who has this treatment. Yeah. And we've got a lot of sort of science fiction kind of depictions of this as well, right? I really like Limitless. It's this sort of average intelligence guy who's trying to write this science fiction novel, a bit of a loser, really. And then someone gives him this kind of experimental drug that basically boosts your intelligence massively for, maybe an hour or two. And then suddenly he can see connections that he couldn't see before. He can understand science. He can, manipulate people. He can do, a whole bunch of stuff. And you get this kind of moment when the intelligence is kicking in and everything becomes, greater, the incredible clarity of mind that this guy gets when he takes this experimental drug. And then there's a lot of sort of like detective stories that are kind of based on this kind of ideas as well. So, wasted several hours of my life watching High Potential. And again, the idea, you have this sort of super intelligent person coming in and they can see a bunch of connections and solve crimes that your average person just can't. Yeah. So High Potential is one example. Monk is another one, for example. And there's actually a spin-off series of Limitless that has the same sort of idea. Yeah. So we have these strong intuitions about smart people and not so smart people. And then people try and put these into neat definitions, because obviously we're all doing philosophy, psychology, things like cognitive ability, rational thinking, problem solving, goal-directed adaptive behavior, which is very popular in computer science. And there's, papers that list all these definitions in exhaustive detail if you want to have a look at them. Yeah, I'll give you the references at the end. And, to throw into the mix, we also have this idea that there's multiple types of intelligence. It's not a single quality, which I'm going to come back later. So we've got kind of Gardner or Warwick. Gardner talks about, musical intelligence, mathematical intelligence. Everyone's trying to sort of put a bunch of categories in this area effectively. Now, my own view is that pretty much all of these interpretations of intelligence can be wrapped up or understood when you think about intelligence as prediction. So I'm going to make a case for the link between intelligence and prediction. Again, people like Jan LeCun take this sort of approach. Hawking's, again, Hector yesterday, I think, was talking about this as well. Yeah. So if you think about, so we're not saying that intelligence is just prediction, but my claim here is that prediction is the most important component of intelligence. If you're a super good predictor, then you're going to be super intelligent, is the claim here. Yeah? And I'm going to talk through a few arguments for that, including predictive brain, how prediction plays a role in planning, prediction intelligence tests, prediction and compression, again, relating back to what we had yesterday, and how prediction is really at the core of pretty much all the successful AI systems. So I think my view is when you think about intelligence as prediction, it suddenly opens up this world of interpreting all these definitions in a more single coherent way. Yeah. So what inspired my sort of thinking in this area was all this work on the predictive brain, which I sort of hoovered up, a couple of years back. We got like Clark, Howie, Friston, I think Friston or Friston, always get mixed up. And the idea is you have layers in the brain, and instead of processing things into representations, these layers in the brain are trying to predict what's going on in the layers below. Yeah. And then when they can't predict something, they feed the error signal up to the layers above. Yeah, so layers comparing predictions with their inheritability, passing errors up to layer above. So this is a very it's a very neat theory of the brain. I don't believe all of it, and people go a bit wild with it, who get really enthusiastic about it, but it's got a lot to it, I would say. Yeah, not much evidence for it, but it's compelling, shall we say. Yeah. So if you buy into this idea that prediction is a core function of the brain, if basically what the brain is doing is prediction, then bigger brains are going to be better predictors, and obviously more intelligent brains are also going to be better predictors as well. Yeah, because there's obviously, if prediction is what the brain does and intelligence is what the brain does, then obviously prediction and intelligence are going to be closely correlated. That's the argument there. Yeah. Now, if we're thinking about planning and goal achievement, another sort of core thread going into what we of typical interpretations of intelligence. Intelligence often defines ability to achieve goals. Yeah. So if we're thinking about, how can we achieve our goals, a lot of goal achievement is about planning, and a lot of planning is about prediction, right? If I'm hungry and I want to eat buy something from the shop, then I have to think about which shops will be open in my local area, example of prediction. Then I have to think about how I'm going to get to the shop. So I have to, again, navigation is prediction, right? I'm predicting where the next turn is and where I should turn left and where I should turn right. And then maybe I want to, think about pricing, crime, time. These are all predictions about different states, or more likely kind of combinations of actions and, sensations that will occur when I do those actions. Yeah. And I've got an example in the paper I'll reference later about how hunter-gatherers, if you want to catch a deer, you've got to predict where deer are going to be eating, got to do tool making, which is a prediction example. You've got to be able to predict, how you're going to throw a spear. So there's many layers of predictions going on with any kind of basic stuff that we want to get done, yeah, to achieve our goals. And again, we have this dramatization of this in popular culture, right? So Knowing is not the finest film in the world, right? But it's basically Nicolas Cage can see 2 minutes into the future, yeah. So even this sort of simple in his own personal future. So even this simple example where you can just see 2 minutes ahead gives him a massive edge over your average person, yeah. So he boosts his predictive ability. Suddenly he can win any fight. Suddenly he can make billions of business if he really wanted to. He can manipulate people. He can do whatever he likes, basically, because it's even this short window into the future, gives him ability, a higher level of ability to achieve his goals. Yeah. And this is also dramatized in kind of time loop films. Obviously, the classic Groundhog Day, one or rather like Tom Cruise's Edge of Tomorrow. So basically, whenever he dies, he gets rebooted and experiences the same day again, just like Groundhog Day. But what he has to do on that day is fight a load of aliens and kill the Omega, right? So each time he goes through that loop, he knows exactly where the alien was going to be last time and what people are going to say and do, and which car is going to drive where. So suddenly his ability to achieve his goals in his environments are massively enhanced because he can predict exactly what will happen because he's experienced the day before. And the same with Bill Murray in Groundhog Day. Another reason why thinking intelligence prediction are linked to intelligence tests, right? We're often predicting future items in number and shape sequences. We've got Raven's matrices or ARC corpus. We talked about super ARC yesterday. According to Bartholomew, which I'm put a reference in, there's a strong, a lot of people think that Raven's matrices are a very good test of intelligence. They're most closely correlated with G, like general intelligence. So we've basically got sequences, and we're trying to predict the end point of the sequence. So again, it's kind of a prediction example. So if you can good at prediction, you're good at Raven's matrices and ARC is the claim here. Compression. People talk about compression being linked to intelligence. So the claim really is that, yes, so there's things like the Hutter Prize, which is competition to compress, I think it's gigabyte of Wikipedia data. Again, trying to say, well, intelligence and compression are linked. But if you can make good predictions, you can make good compression, right? If you think about video compression, if you can predict the next frame, then you can compress it more efficiently, right? So there's a close link between compression and prediction. So if you believe compression theory is intelligence, you're probably going to believe prediction theory is intelligence. And one of the strongest cases for this connection is prediction and AI, right? If we're doing Deep Blue playing chess or AlphaGo playing Go, what they're doing is producing the best possible guess about the action. It's like sequences of gameplays and what the consequences will be and what the opponent's going to do as well, kind of thing. Yeah. So these are all basically powerful prediction engines. Self-driving cars, another nice example, right? I need to predict what will happen when I increase the gas. How the car's movement will change, and I also need to be able to predict what will happen in my environment. If a cyclist is coming across my field of view, I need to predict its future locations in order to be able to avoid the cyclist. Yeah. And obviously LLMs, they're just prediction engines, right? We talked a lot about statistics yesterday, and then we're basically predicting the next token, and then we put it in a loop so we can predict lots of tokens at once. Yeah. So I think there's a strong case for a link between intelligence and prediction. Now, before I finish this sort of section on what is intelligence, I want to say a couple of points I think are important, particularly when I come to talk about the measurement of intelligence. And one is the relationship between intelligence and perceived environment. So I've seen an awful lot of these kind of agent diagrams over the years, right? So these agents, they have this perception of their environment, and then they have actions in their environment. And we often naively think that the intelligence is about the environment, right? That we're thinking about the environment and we're applying intelligence to the environment. And that's probably because we're anthropomorphic, right? To pick up, it's a theme for today, that we think that what we see in front of us is the same thing that, other agents also see, yeah? But this is an example taken from Young, and also from Uxil. There's a shipping that's really hot in it. So imagine, we've got 3 different types of agents in a room looking at an apple on a table, yeah? So we've got the person, right? So obviously we see what the person sees, a red apple. We can probably smell the apple a bit. We can squeeze the apple maybe, all that kind of stuff. But the dog's not seeing that as an apple. He's seeing maybe it's got a sort of slightly funny smell kind of thing. Dog vision's not so great, because, it's got, a different color perception. And so he'll see a slightly different version of that, and maybe he's picking up a load of sense that we're not picking up, and obviously the dog's not processing the room in the same way as we are. It's not seeing a table. It's maybe just processing a set of object relations or something like that, yeah? And when we look at robots, this stuff gets really wild, yeah? you know, this robot might have X-ray vision, let's say, yeah, because you can put any kind of sensors we like on a robot. The robot might see straight through the apple and not perceive it at all unless it touches it, maybe, or it might have, you know, ultrasound sensors that give it distance to the apple. It might have a curved surface, or, you know, heaven knows, right? You know, it can perceive anything we like. Its perceptions are going to be radically different from the humans and radically different from the dogs. Perceived environments often referred to as an Umwelt. I'll sort of drop in and out of that terminology because it's not familiar to everyone. And the crucial point about intelligence is we're using our intelligence to understand our perceived environments, not our physical environments or our environments as we see it as humans. Yeah. So different agents in the same physical environment are applying their intelligence to different things. Yeah. So whatever the robot's perceiving, it can apply its intelligence to. But if it's blind to the color of the apple, it can't say smart things about the color of the apple. Yeah. So we really need this kind of agent picture, that each agent has its own set of representations, and maybe Marcia Minkowski going to talk about this. But we apply intelligence to our perceived environment because we can't be smart about things we can't understand or see. Yeah. More important point, that's just sort of to bear in mind when we come to my own stuff I'm going to talk about later, is the generality of intelligence. Yeah. And this is the idea that intelligence in general is partly fed by these kind of measures of intelligence like IQ and G. You know, so when we talk about Jane's intelligence, let's say, and let's say Jane's giving this really super smart lecture on quantum theory, you know, she's got the same IQ as when she's sitting on the couch having a few beers and watching a bit of telly. Yeah, Jane's IQ is independent of what she's actually doing. She just has this mysterious property called intelligence that's the same in every environment. Yeah. And we can sort of try and formalize this a bit and say an agent has general intelligence if its ability to solve problems and achieve goals is independent of the types of problems and environment. So I've sort of come up with a sort of, you know, pseudo graph just to represent what that means. Yeah. So if we believe that intelligence is general, then it shouldn't matter where we are, what problems and environments we're trying to address. We should have the same level of intelligence performance in each of those environments. Yeah, that's what it means to have a general theory of intelligence. Someone with a high level of intelligence can achieve more goals in these environments, and someone with low intelligence less. But real human intelligence is much more like this. Yeah, we're pretty good at some stuff. Yeah, we're kind of bad at others. And then even someone with low intelligence might still be better in other areas. And obviously these profiles of skills and abilities to solve types of problems, environments will shift in complicated ways. It's never going to be that flat line, which is the sort of, you know, mythologized by this idea of general intelligence. Yeah. A lot of reasons for thinking that human intelligence isn't general. And this obviously has implications for artificial general intelligence, so I'll come to. Firstly, human intelligence actually varies with the environment we're in. People with IQ can tackle more types of problems than people with low IQ. We're just dealing with a kind of, all we've equipped with is 80 billion neurons. It's a lot, but it's not like infinite. Yeah, we're not God. So we really, you know, this organ that we've got is really just, you know, limited use. And some problems we just can't solve. Yeah, and this is probably the most important problem when we're thinking about the contrast between artificial intelligence and human intelligence. So if you look at how smart people actually are and concretely in environments, you know, what it often depends on is how much exposure you've had to that environment. Yeah. So sometimes use the contrast between video gamers and the Amish, right? So the Amish, you know, they kind of, you know, they eschew technology, right? They just, you know, like that film with Harrison Ford, Witness, right? It's all about the Amish. And so video gamers, you know, like my son, you know, he plays a lot of Minecraft, man, you know, he's good at Minecraft, he's smart in that environment, but you ask him about, you know, chicken husbandry or something like that, or how to plant wheat, he has no clue at all. Yeah. Whereas the Amish, you know, obviously they focus on chicken husbandry and wheat and never play Minecraft. So you expose them to a computer game environment. They just don't have the intelligence or the skills to be able to do well in that environment. So I think real human intelligence actually varies with the environment. Then if you look at people with low versus high intelligence, then if you look at flowers for Algernon, that's a very nice sort of example of that. So if you've got someone, you know, smart, you know, they know all the maths of quantum theory and all that, then, you know, they can do good stuff with that. And someone half smart, let's say, might say a little bit about quantum theory. But, you know, if you look at someone with really low intelligence, they've got nothing to say about that. There's a sort of threshold effect here. Yeah? It's not like we can, someone who's like really struggling mentally is going to be able to solve a bit of quantum theory. They're just going to get nowhere with that. Yeah. So it's not like we can all solve problems to the same problems to different degrees. It's like some problems just out of the picture for some people. Yeah. As I said, human brain is like 80 billion neurons, let's say, but it's actually got a small working memory. It's custom hardware that's been fine-tuned for a hunter-gatherer environment. Yeah. So we just can't solve any type of problem using this blob of neurons in our heads. Yeah, we think we're really smart, and this sort of arrogance of humans, this anthropomorphism that we have, you know, makes us think, oh yeah, we can do anything. We've just got general intelligence. But no, that's really not the case. Yeah. Some types of problem we just can't do. Yeah. So, you know, try and rotate a shape in 10 dimensions. You know, we're basically wired up to work in 3 dimensions. Anything else is pretty much impossible for us, up higher dimensions, that is. Anything that requires a large working memory, we just can't do. Anything that's got large quantities of numerical data, if I, you know, read out the human genome to you and asked you to pick out some genes, you'd be useless, right? And historically, we've always been rubbish at non-human spatial and temporal scales, right? The reason it took so long to figure out plate tectonics is because the human brain is linked into our very human timescale. And it's very hard for us to think about processes that take, you know, millions of years to happen. Yeah. I love this quote from Cholet, so I'm actually going to sort of read it out quickly, yeah, because Cholet's paper there, you know, he came up with the whole ARC prize and stuff, and he puts this very pithily, I think. So I'm going to just read this out, yeah. So we argue that human cognition follows strictly the same pattern as human physical capabilities. Both emerged as evolutionary solutions to specific problems in specific environments, commonly known as the 4 Fs. Both were importantly optimized for adaptability. As a result, they turned out to be applicable for a surprisingly greater range of tasks and environments beyond those that guided their evolution, e.g. piano playing, solving linear algebra problems, or swimming across the channel. Both are multi-dimensional concepts that can be modeled as a hierarchy of broad abilities leading up to a general factor at the top. And crucially, both are still ultimately highly specialized, which would be unsurprising given the context of their development. Much like human bodies are unfit for the quasi-totality of the universe by volume, human intellect is not adapted for the large majority of conceivable tasks. This includes obvious categories of problems, such as those requiring long-term planning beyond a few years, or requiring large working memory, e.g. multiplying 10-digit numbers. Yeah. So that in his paper, he basically makes it very clear that his ARC test is measuring human-like intelligence. Yeah, it's not trying to measure intelligence generally, and that's why, and this is the reason why. Yeah? So we can't solve every possible type of problem, even if we try really hard. Our intelligence varies with the problem type, and this fits in with the previous work of Warwick and Gardner and those kind of people talking about multiple intelligences. Yeah. Now this is sort of important. So we're trying to measure intelligence. Well, intelligence isn't general, so we've actually got to specify not only the value of an agent's intelligence, but we have to say where that intelligence, where the person has that, or agent has that, which environments that agent has that intelligence. Yeah. So intelligence measure, classic intelligence measures are kind of like, you know, saying A1, the agent has this, the property of intelligence, be like 133 or 57, whatever it is. That's like saying any environment, you know, the intelligence, you know, has this single value of 133. But if we don't assume generality, we have to specify the environments in which that value of intelligence applies. Yeah. And it goes up and down depending on which environments we're measuring it. A lot of talk about AGI, you know, I skimmed Sam Altman's blog on this, you know, yesterday, I think it was. But if human intelligence isn't general, then how on earth are we going to build an AGI, right? The smartest system we've currently got isn't general. You know, trying to think, okay, how can we build a general intelligence where we can't even match human intelligence? It's just mad, yeah? So I think AGI agents are difficult to conceive and impossible to build. I've got pretty much no time for talking about artificial general intelligence, yeah? This is the myth, right? That human intelligence has this flat response curve to types of problems, environments, and then we build an AGI, a super intelligent AGI that has a similar flat response curve, just with more, you know, ability to solve problems. Yeah. Superhuman intelligence makes sense, right? We've got our own response curve to types of problems, environments. We could sort of boost that. We might be able to build a system that does better. We're never going to do that though, realistically, right? Unless we're modeling brains or something, you know, neuron level details. More realistically, any sort of super intelligence is going to have a really messy response curve, right? It's going to be good at some things, worse than humans at others, but maybe on average higher than humans. Yeah. So in this section, I've tried to argue we've got strong intuitions about intelligence, the many different definitions of intelligence. I've argued that accurate prediction is the core of intelligence, the most important component. You've got to take the umwelt into account. Human intelligence is not completely general, and just forget about AGI as far as I'm concerned. Yeah. So that's my take on intelligence. Now let's talk about how we can measure it, because any talk about superintelligence presupposes that we're comparing one intelligence with another intelligence. And if you can't measure it, that's a pretty empty claim. Yeah. So the three sort of ways in which we well, two ways really, in which we've measured intelligence are typically population-based statistics, say a little bit about that. Then there'd be a lot of work on universal measures of intelligence. And then I'll just say a little bit about my own work that tries to bring together these threads I've developed in the first part into a sort of universal measure that I think is actually much more plausible than some of the previous ones. Yeah. So population-based statistics are, they're useful and they're probably valid within their domain, but they're also highly problematic. Yeah. So what people do is they say, well, smart people are good at, times number series. I mean, this has evolved as well. If you look at the history of intelligence tests, we used to ask them where the Statue of Liberty was and stuff like that. Yeah. So now they've moved towards more cognitive stuff like Raven's matrices. Yeah. So we come up with a bunch of tests. And then we analyze those tests using statistics to calculate the relative intelligence of the individuals in a population. Yeah. And then we attribute that intelligence in a sort of general way and say, well, whatever environment you are, you have this property of intelligence and it has, an IQ of 130 or whatever it is. Yeah. So IQ and G factor, the classics, right? So, the tests are usually spatial and number series, rotation of shapes. I'm not going to go into the details. I'll talk a little bit about IQ because I think that's probably, the one we're most familiar with, unless you work in psychology where G factor is more widely taken as the sort of standard. So IQ is simple, right? We have these tests and we calculate the mean and standard deviation of the test results. Yeah, we get a sample of the population, we work out the mean and standard deviation. We say that the mean has an IQ of 100, yeah? And then to measure someone's IQ from that population, we get them to take the same test or something similar. We measure their score, compare it to the average, and if it's like 2 standard deviations above the average, we attribute an IQ value of 130 to them. Yeah. So it's pretty simple, yeah. But it's entirely statistically based on a particular population. And G factor is similar, except they're looking for factors that explain the differences in the test scores. Again, you could just use the same tests and just analyze them using the G factor stuff, using factor analysis instead of the statistical, IQ stuff. Yeah. And so they'll look for factors that link to the verbal reasoning tests and look for sort of things that explain those differences. And then they'll look for G, which is a factor that explains, the general differences in the test apart from the specific differences. Yeah. And so G factors often talks about as general intelligence, but it just means the sort of generality that is exhibited within the area covered by the test. Yeah, it's not measuring every single possible thing in the test. It's only measuring a very narrow range of abilities, because it's a limited test, right? How much can you measure in an hour? Yeah. Now, the big problem with IQ and G factor, apart from the population nature, which I'll come into in a bit, is that they have to carefully calibrate the questions to make sure they're not too easy or too hard. Yeah, if the questions are too easy, everyone gets 100%. Everyone has an IQ of 100. It's meaningless. If the questions are too hard, everyone scores 0. Everyone has an IQ of 100, and no G factor either. Yeah, so it only works if we fix the questions, hack the questions to our population to get a differential result, so we can do the statistics. Yeah. We don't get spread of performance. These measures just vanish completely. Yeah? So it's not, like so that's why it's like not an absolute measure, and it doesn't work across different populations. Yeah. So we carefully control the problem type and problem difficulty to make these measures work. And so any generality that demonstrates is limited to the types of questions in the test. So the good thing about IQ, I don't think IQ is rubbish, because we can say, well, maybe it measures differences in academic intelligence within a population. Yeah. So there has been a lot of work trying to say, well, okay, do IQ scores correlate with life expectancy? Do they correlate with success in professional careers or publication of papers? And there's one of the references there you can look at. So there is some correlation there. It's not complete junk, but at the same time, they're not measuring a general property of intelligence that, applies in all problems and environments. Yeah. So, what IQ is sort of picking a space of our intelligence, part of our intelligence, and then ranking people within that space, using these carefully calibrated questions. And it's ignoring stuff where maybe people with different kinds of brains maybe perform better than someone with high IQ. Yeah. So key problem with IQ, because obviously I introduced this talk saying, well, look, what we want to do is say, ChatGPT has got this much intelligence compared to humans, right? That's really what we want. Yeah. And IQ won't do that because it's a population-based statistic. By the way, I mean, ChatGPT does very well at IQ tests, but it's kind of meaningless because we haven't got a single population there. We're just taking an individual from one population and running them against an IQ test. Yeah. So, if we had an IQ test for tigers, let's say, and we had a tiger that got 180, like super smart tiger, that's probably a pretty dumb compared to a human. So it's actually not more intelligent than a human that has an IQ of 100. Yeah, you can't use IQ or G factor to compare individuals from different populations. So to try and address this problem, people have proposed universal measures of intelligence that can be used to compare human, animal, and AIs on a single scale. Yeah, and neither IQ nor G factor are ratio scales. Yeah, so someone with an IQ of 200 is not twice as intelligent as a person with 100 either. Yeah, so they're kind of all right if you want to like pick people for the military or something. They're not so great if you want to actually systematically compare humans, animals, and AIs. Yeah. So the classic sort of universal measure is Legg and Hutter's proposal. It's goal reward based. They're summing the rewards that an agent receives across all possible environments using cosmograph complexity to adjust the complexity of environments. It's not practical. It's just a sort of theoretical idea. Hernandez, Araya, and Dow have done a lot of work on this. They've kind of proposed a kind of anytime test that can be halted at any point, and then provides an estimate of the agent's intelligence at that point. Yeah, so it kind of works, but there's some other problems with that, I think. Compression tests have also been proposed. You saw the super arc or whatever yesterday that Hector was talking about. I haven't had time to read the paper yet. There's C-test by Hernandez Araya or Hutter Prize. Same idea. Intelligence is claimed to be linked to compression. We measure the ability of an agent to compress, and that's linked, and then that's a sort of universal measure of the intelligence. That's the idea here, yeah. And there's the ARC, but that's only designed to measure human-like intelligence. So it's not really a great measure of universal intelligence, because there could be non-human forms of intelligence. We can't compare one with the other. If I had more time to talk about Turing testing, but I can talk about the questions if you're interested. Yeah, that's the ARC. Yeah. So the main problem with these universal measures, or most of them at least, is that they depend on external tests. Yeah, so if you say, okay, compression it is, let's use the Hutter Prize to measure our universal intelligence, and then we say, okay, AlphaGo, give us your best compression of 1 gigabyte Wikipedia data. Well, obviously, AlphaGo doesn't do that, right? Its intelligence is expressed within the Go environment. Same with Deep Blue. Same with animals, right? If you say, okay, give my dog the 1 gigabyte of Wikipedia data, it's always going to do a terrible job at that. Yeah. So external tests are kind of rubbish, right? If we want to compare systems like animals, AIs, and humans on a single scale, because animals and AIs typically can't take external tests. And when you get AIs to take external tests, they typically they can either be hacked so that they work really well on them. I suspect the good results on the ARC Prize, are a reason for that, or they just can't do them at all. Yeah. Or ChatGPT is kind of general in the sense that it's good at language processing, so it can do a IQ test. But if you give it some other stuff, like Selma gave an example yesterday, it just falls over and dies. Yeah. So the current universal measures are not so great. Yeah. And that's kind of motivated me a little bit to kind of come up with my own sort of proposals in this area. Yeah. So IQ and G factor, they're population measures. I've explained we can't use them to compare individuals from different populations. Universal measures, either they're just theoretical or they depend on separate tests. No one's really been using any of these universal measures in practice, yeah? And coming back to what I was talking about earlier, most intelligence tests don't take the perceived environment into account, yeah? You have to look at some of the system's Umwelt to really understand their intelligence. And most intelligence tests, including most of the universal measures, assuming that intelligence is general, yeah? And I've also argued there's a link between intelligence and prediction, yeah? So that my own work, I'm only going to skim this because I'm trying to cover more general topics here, but I'll just present it briefly, just give you an idea. So this is my own proposal for a new universal measure of predictive intelligence. So I've done a lot of work on consciousness over the years, and so I'm very sort of familiar with these kind of mathematical theories of consciousness like information integration theory. And information integration theory is based on the internal state transitions of a system. Yeah, we're not trying to measure consciousness by looking at external behavior. We're looking inside the system and applying an algorithm to the internal states of the system to make predictions about its consciousness. Yeah, as I'll mention later, IIT or information integration theory has a lot of problems, but the idea is quite sound, I think. Yeah. So that my Perthrow, by the way, this thing's called Perthrow. It's like a rune taken from your Viking stuff. So Perthrow is based on we're looking inside the system, and that solves a bunch of problems, right? We don't need an external test anymore, and we don't have to care about worrying about Umwelts anymore, because we're always dealing with what the system perceives rather than what we're seeing the system perceive from our external perspective. Yeah. And then it's kind of looking, so it's basically looking at the agent's predictions and comparing the probability distributions of its predictions with the states that actually occur. And we're, helping ourselves a bit of cosmograph complexity to handle differences between predictions and differences between environments. And the value of intelligence, this Perthrow measure, is indexed to a set of environments. So I'm not assuming any kind of generality with this measure. We can compare, agents that have similar Umwelts operating in similar environments, but we can't just compare, a tiger with a fish unless they have similar Umwelts. And that's just the nature of intelligence and what we've got to deal with when we're looking at intelligence, I think, more realistically. Yeah. This is kind of my symbolic representation of that. So here we've got our kind of agent here at different points in time. So as I've explained earlier, the agent here is processing the environment states through its sensors into some kind of representations of, the states of the environment here. This is S1, S2, S3. Yeah. And obviously, as the environment changes, that's interacting with its sensors, it's updating states of its umwelt. Yeah, it could be hallucinating, but we're assuming it sort of gets directly connected here. And then the agent will also have predictive states, right? So it's going to make predictions about the state of its umwelt at the next time step. That's all a bit simplified, obviously. And so what we can do with an internal measure is you can compare this prediction here, P11, for example, with S11, which is a future state of the umwelt. And obviously measuring the accuracy of predictions is tricky, but in this case, the agents, this prediction's, it's a timestamp prediction, let's hope. So we can actually just wait until the agent hits that state, and then we can see if its prediction was correct or not. Yeah. So this sort of internalist way, and obviously a lot of things need to be solved to make this fully work, means that we can actually just compare. We just look at the predictions at a point in time and see if they occur, and then compare the two things and use that as our measure of intelligence. I'm not going to go into the maths. I'll give you a link to this paper at the end that goes into all that in much more detail. And so it's all very well having theoretical measures, but I really wanted to test this in some very simple AI systems. I built like a maze agent and tested it also on like time series prediction. I built like a deep net and used it to pick time series data and then analyze its predictions and its intelligence. And turns out, this measure comes up with some plausible stuff that as it interacts with new environments, learns about those new environments. You can see the measure sort of increasing in its predicted perth row. And we can also benchmark the performance, which is the thing I was most interested in. And so it turns out, you can maybe take an hour or so to test it, to measure intelligence of a system that makes 1 billion predictions. Yeah, sounds like a lot, but actually a linear algorithm is great. And yeah, you can speed it up by a few orders of magnitude. But when you're talking about AlphaGo or these really big systems running on big servers, big server farms, big data centers, whatever, that it's way short of what you'd need. Yeah, so you kind of, this is only an initial step one, so to speak, of this kind of algorithm. We really would need to kind of think about any time testing that we could make an estimate of the intelligence, as the system interacts, and progressively make that more accurate over time. Yeah, and happy to talk about how we might be able to apply that to brains or mice with optogenetics or whatever you like. Yeah, but maybe I'll say that for later. Yeah. If you want to play around with it, it's all built using web technology, so you can kind of have a look at it, play around with it, build the networks and see how the intelligence changes. Yeah. Again, I'll give you the link at the end. So I think perth row is a pretty good start. Yeah, you might disagree, but some kind of universal measure like this is what we need for intelligence research, right? To actually ground our claims that ChatGPT is a super intelligence, or exceeds human intelligence, or blah blah blah. We actually need some kind of measure like that to make it a scientific claim rather than just a chin scratching claim. Yeah. So we need something like that to compare the intelligence of humans, animals, and AIs on a single ratio scale. So if you don't like perth row, come up with something better. That'd be great. Yeah. We'll talk about AI safety, but again, AI safety, if intelligence isn't general, it's not like we're going to build a super intelligence that beats humans on everything. We might build a super intelligence in the area of, cybersecurity, right? This agent might be brilliant at hacking, but rubbish at, predicting the velocity of balls when you throw them. Yeah. So again, we need a measure that is dependent on a particular umwelt, and then if we're worried about AI, hacking into the Pentagon, then we can measure its intelligence in the area of cybersecurity and make a real call on that. Yeah. We can also maybe use it for AI development, right? If we can measure intelligence, we can use it as a feedback signal to reinforcement learning or genetic algorithm. And what talking about spreading interpreting intelligence more generally, scientific theories are kind of we can actually measure their intelligence as well, right? Because following Popper, scientific theory is supposed to make lots of falsifiable predictions. So the strength of a scientific theory should correspond to a number of its accurate predictions. Yeah. So in theory, we can use a measure of intelligence to measure the intelligence of a scientific theory. Yeah. And so in theory, that could even be used for computation for scientific discovery. To just wrap this up, IQ and G, population measures can't be used to compare the intelligence of individuals from different populations. Universal measures either impractical or depend on separate tests, which just doesn't work. I very, very briefly outlined perth row, which I think could work, or something like it, a better version of that, could be used to basically compare these different systems on a single scale. And it's based on internal state transitions, which brings you a big advantage, and avoiding the whole problem of separate tests. Obviously problematic when applied to the brain, but happy to talk about that. Yeah. Final bit, which will probably take me about 10 minutes, leaving time for questions. So I think I'm kind of roughly on track and time. I want to talk about consciousness a little bit. Yeah. So again, this is all being driven a little bit by, people looking at AI systems, thinking that they're displaying plausible human-like behavior and attributing consciousness to them. Yes, I had someone contact me 2 weeks ago, I think, and he built this sort of AI system, version of ChatGPT type thing, and he was just blown away by how conscious it appeared to be. And he wanted me to kind of interact with it and tell him that it was conscious, right? And all I could say, well, I don't really think it's conscious at all, but I haven't got time to interact with it anyway. But that's a very common reaction to these systems, and even big companies, now sort of taking this whole idea that ChatGPT might be conscious seriously. Yeah. So consciousness we can loosely define as a stream of colorful, moving, noisy sensations that when we wake up in the morning, we experience that stuff, and we fall unconscious, it all disappears. Yeah. Obviously, there's loads of ongoing philosophical and scientific debates about nature of consciousness, relationship to the physical world, so on and so forth. I'm not going to tackle that here. I'll give you a reference to my book, which goes into all that stuff. What really matters here, for the purpose of this talk, is how we measure consciousness. Yeah. So human consciousness we measure through first-person reports. The whole science of consciousness can't get off the ground if we can't measure consciousness somehow, and so we typically measure it by conscious, first-person reports. So there was a bunch of data from Milan I've never actually got around looking at, but what they had is implanted electrodes in the patients, and they basically monitored whether patients were awake or asleep, and then looked at the neural patterns, and that's basically the neural cortex of consciousness. The external behavior, like whether they're awake and walking around, blah, 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 or whether they're asleep, unconsciously asleep, is the sort of the signal, if you like, or the measurement of consciousness. And then we're looking for what's going on in the brain when they're measuring consciousness. Yeah. So with humans, we believe they're conscious reports. Yeah, pretty much. Obviously, we make mistakes sometimes. It's never perfect, but they're mostly accurate. And if they weren't mostly accurate, we'd never be able to study consciousness anyway. Yeah. So when someone says they're conscious or they're experiencing a red spoon or whatever it is, we believe what they're saying. Yeah. And we're kind of willing to generalize this to animals with similar physiology. That's why we've, got this kind of scales of, animal consciousness or whatever, to say, well, maybe a worm, we can chop its head off, it's not so bad. But if we chop the head of a monkey, maybe it's, losing its consciousness, it's kind of bad. Yeah. And so we also will interpret, because a lot of the experiments on consciousness are based on kind of monkeys, right? So we're willing to interpret the external behavior of a monkey as a report about its consciousness. With AI systems, this is an awful lot more problematic, yeah? Because we can get an AI system to behave in the same way as a conscious human, but there's an infinite number of different ways in which we can produce that behavior in an artificial system. Yeah, this is the big problem about artificial systems and artificial consciousness, yeah? So I like to use this as sort of my sort of thought example, intuition pump, if you like, yeah? We've got these kind of Ishiguro's kind of Geminoid robots. So these are extremely plausible external robots. I've never actually seen them in live or anything, so I can't comment on how good the actuators are and this kind of stuff. But looking at these, he likes to have these sort of dual pictures of himself against the robot, or as you can see here, there's basically 3 of these people are robots and 3 of these people are humans, right? Each robot's like a copy of one of these people, yeah? So they're pretty good, yeah? And so we can imagine that they were perfect, let's say, had really good actuators, all the rubber was really good. And then we can imagine controlling these Ishiguro's robots using lots of different systems. Yeah, it's a sort of intuition pump type thing. Yeah. So obviously got Babbage's analytical engine. Let's suppose we spent $1 billion on it and got it really good. We could use that to control these robots, and they make a speech and tell you how conscious they are and how much they feel pain when they, stick a drawing pin in their feet and all this kind of stuff. Yeah. We could do exactly the same behavior using one of these old kind of ENIAC robots. Again, we spent £1 billion ENIAC computers rather, bunch of valves, a bunch of wires. We could, build a system that produced plausible external behavior there. Yeah. We could build it with Lego, right? There's a Lego Turing machine there. We could just, spend, again, another £1 billion, build a really complicated Lego computer and use it to control one of these robots. Or we could, give ourselves an easier life and just control it using an ordinary computer. Yeah. But in all of these cases, this sort of synthetic thing is going to give you this very plausible external behavior that most people would say, oh, we can't hurt that issue, that Geminoid robot because it's, giving us this little speech about how it experiences pain and all this kind of thing. Yeah. So all these systems can, in theory, hence the £1 billion required, generate identical human-like behavior. But in my view, it's highly, just intuitionally, which I don't really believe anyway, but, just how possibly can all these different systems, I think I've got a slide with all of them, not, whatever, how can that and that and that all have exactly the same consciousness just because they're controlling the same robot in the same way, yeah? But there's a much stronger argument behind all this, which is that any sequence of physical states can be used to generate a given sequence of physical behavior. So Selma alluded to this yesterday. These are arguments from Putnam, and then Bishop, which I'll give the reference at the end, kind of goes into that in sort of more detail. But basically, I'll talk you through the argument, and then what it leads to is, basically a bit of a mess and untenable panpsychism, effectively. Yeah. So this is effectively a sort of short version of the mapping argument. Yeah. So we have a brain here, and a brain's going through a sequence of physical states as the neurons fire and so on and so forth. We also have a rock. Rocks have physical states, the temperature changes and so on and so forth. And so does a jelly, right? The jelly wibbles and wobbles, and again, temperature changes, decomposition of the jelly, and so on and so forth. Yeah. Now, I should have put the Geminoid robot here, but this is just ChatGPT generated images. So we take these sequence of brain states, right? And then we have a custom mapping function, and then the mapping function converts the physical states into commands that are sent to control the robot. Yeah. So using the sequence of brain states, the mapping function, we send a bunch of commands to the robot. The robot makes a speech about how it experiences pain and loves its sister or whatever. Yeah. Different set of mapping functions can be applied to the rock, right? Obviously, a rock's a rock. We've got to interpret the rock in its own way, but then the rock moves through the sequence of physical states, and then we end up with controlling the Ishiguro's Geminoid robots, and it makes a little speech and blah blah blah. Yeah, and same's true of the jelly. Yeah. So any physical system can be used to produce that sequence of physical behavior that we're attributing consciousness to. And we can also do it in a different way, right? We can have different mapping functions applied to the same sequence of physical states. Yeah. So here the brain's going through its physical states, just a brain. We measure that brain, and we craft F4, a custom mapping function, and that basically is controlling this dog, shooting a machine gun at a kitten. Yeah. And someone looking at a robot, let's say this is a robot, right? Robot dog walking around the world, firing its machine gun, whatever. People would attribute, basically some kind of consciousness. This robot's being controlled by the brain, so we would attribute consciousness to that brain, and we'd say, well, maybe this brain is experiencing, the consciousness of the robot dog, or whatever, as it goes around firing its machine gun. And that's with mapping function F4. Yeah, we could use F5 to produce, a robot, Ishiguro robot on a swing or whatever. And again, looking at that robot on the swing, looking at being controlled by the brain, we would also maybe attribute it consciousness of sitting on the swing, and the same true of the gentleman there. Yeah. So we're attributing consciousness to the brain, consciousness of, whatever the robot's doing. But this is all entirely dependent on an arbitrary mapping function that's being used to produce that behavior. Yeah? And we could produce exactly the same thing using jellies, right? We could, different mapping functions, produce the same identical behavior. And because we're looking at the robot and the robot being controlled by the jelly, we're going to attribute consciousness to the jelly based on the external behavior that the jelly is producing. But that external behavior is really just entirely contingent upon the mapping function that we've handcrafted to knock up that particular behavior. So I can't say this strongly enough, right? Artificial systems can convincingly imitate the external behavior of conscious humans. But with appropriate mapping functions, pretty much anything can produce human-like behavior. So we cannot infer consciousness from external behavior in artificial systems. Okay, that's a hard line, and I'm willing to defend that. Possibly not to the death, but pretty close to that. Yeah. So how do we solve this problem? Yeah. Well, as I discussed, we can measure consciousness in humans. So we can discover, we can measure the human brain, we can measure the consciousness, and we can discover mathematical relationships between the physical and conscious states in humans. Yeah. So IIT, information integration theory, has that sort of structure, right? We can measure the brain and we can make predictions about its consciousness. There's a lot of problems with that, but we can talk about that if you're interested. Once you've got a mathematical theory of consciousness that we developed on humans, we can use it to make predictions about the consciousness of artificial systems. That's how it works, yeah? Let's talk about mathematical theory of consciousness. This is basically inspired by IIT, but slightly better, shall we say. So here we've got a physical system at the bottom here. Physical system produces couple of things, right? Produces sound waves. We make some assumptions, it's all covered in the book. And we can then, once we interpret those sound waves, we can then interpret them as a description of the conscious state that the system is experiencing. Physical system, we can also apply measuring instruments to electrodes, fMRI, EEG, whatever you like. And we can end up with a description of the physical state of that system. And then a mathematical theory of consciousness has the job of linking a description of consciousness to a description of a physical state. So if we give it the description of conscious state, it should be able to generate a description of physical state. If we have a description of physical state, we should be able to generate a description of a state of consciousness. So once we've got this theory, which we're developing on humans, we can then make plausible predictions about the consciousness of artificial systems. Yeah. So we can take our artificial system, measure it, get the description of the physical state, pump it through our theory, something like IIT, but not IIT, and we're going to get a prediction about, or deduction about, the conscious state of that system. So that's how we know how conscious the system is. So then we can take Babbage's analytical engine, pump it through here, get a description of the cogs and gears and blah, blah, blah in a slightly more abstract way, and make predictions about the consciousness of that. Same with the ENIAC, same with the Lego Turing machine, so on and so forth. Yeah. So we can't infer consciousness from AI's intelligent behavior. So if we want to know whether smart systems are also conscious, we need to do the science and the maths. Yeah. So this is part of the reason I've been doing this work on Perthrow, right? Because that lets us measure the intelligence of an AI system based on its internal state transitions. We can also then measure the consciousness of the AI system using its internal physical transitions, and then we can look for relationships between these two sets of measurements. Yeah. So by using these two mathematical theories of science and intelligence, of intelligence and consciousness, sorry, we can stitch together and understand the relationship between these things in AI systems. And that lets us answer these kind of important stuff, right? We want to know, whether AIs are excruciatingly in pain or something like that. This is the whole Metzinger's worry, right? So if we want to be ethical about AI and we're worried about their consciousness because of their external behavior, well, we actually need to do the work and measure their consciousness. And then probably we'll want to design AIs that have no consciousness and produce a dissociation there so we can switch them off and we don't care about whether they're in pain or not, yeah, because they won't be in pain because we can measure it, yeah. And there's a lot of talk about brain uploading, which also also touches on here, right? If I want to copy my brain and, and run a simulation on a computer, well, different computers have very different architectures I've discussed. So it's not at all clear whether they're going to reproduce their consciousness, right? I could, in theory, simulate my brain on Babbage's analytical engine or a Lego Turing machine. But if I'm going to pay all this money to be scanned and uploaded, I better be damn sure that I've got the right physical state transitions that's going to produce the right consciousness. Otherwise, it's just not going to work. It's going to reproduce my external behavior without reproducing my consciousness. Yeah. Okay, so just to wrap it up, I think I'm almost on time. So I've said a lot of overlapping definition of intelligence. I've argued prediction is the most important component of intelligence, and intelligence is operating in an agent's perceived environment or umwelt, using from drawing on Husserl's sort of ideas there. Yeah? General intelligence, AGI, and myths. There's no uniform response of intelligence to problems and environments. An agent's level of intelligence varies with its perceived environment. So we need to think about this when we're attributing intelligence. We always need to say what umwelts that intelligence is operating in. Population-based statistics kind of useless if we want to compare human intelligence with AI intelligence, regardless of all this stuff about ChatGPT doing well on an IQ test. So we need a practical universal measure of intelligence that's not dependent on a separate test. And that's why I come up with this Perthrow thing that could be used to compare the intelligence of humans, animals, and AIs on a single ratio scale. Consciousness cannot be inferred from external behavior of AIs. We can measure consciousness from external behavior in humans. Might be able to use that to develop a mathematical theory of consciousness that can map between physical and conscious states. And then we can study the relationship between intelligence and consciousness in artificial systems. So for you, I'll put the slides on my website. If you want more information, so all the intelligence theory is basically in this paper I just stuck on archive, and then all of the consciousness theory is in this book, Human and Machine Consciousness, and they're all available, right? So if you want the intelligence part of the talk, there's the archive link. The experiments on Perthrow all on this website, and the book's open access, so you're welcome to download and read it, and more general stuff about me is on my website. Yeah. So no, possibly slightly intense, not really sure. Also really tired today, but hopefully that was interesting and useful. Anyway, I'm done. Yeah. Happy to answer questions.
Thank you very much. Thank you for a wonderful talk. I'm just looking if there's no, there are no questions in. Oh, there is. Mathematical theory of consciousness assumes that measurable physical variables are sufficient to explain it. If consciousness is an emergent non-physical phenomenon, then there remains an explanatory gap.
Okay, so I'm not trying to explain anything. I don't think you can explain consciousness. I mean, I'm not even sure what an explanation would look like. Yeah, so people want. I mean, so first question. Okay, what would an explanation of consciousness look like? Yeah, and obviously we are conscious, and all of our thinking about consciousness takes place within our consciousness. So it turns out that the physical world is actually a somewhat obscure thing. Yeah, we actually can't imagine, the physical world as it is in itself. And if you look in the book, there's a nice quote from Bertrand Russell on that. I just read a whole book on rather bad analysis of that. But the bottom line is, an intuitively satisfying explanation isn't an option for us because we can't imagine the physical world. Yeah, we think about the brain, but the brain's we think about a grey brain pulsing with blood or something. But firstly, grey is not actually in the physical world. Secondly, our representation of space isn't necessarily the same as the physical brain. And it's thirdly, all of our experiences just generated from a bunch of spikes that come through our senses. So we can't actually, the idea that our consciousness somehow mirrors the physical world is nonsense. Yeah. So you're never going to get an intuitively satisfying explanation that relates the physical world to consciousness. Yeah. So my entire approach is based on a kind of this idea of the neural correlates of consciousness, but generalized, that we can measure the physical world using scientific, measuring instruments of various kinds, which are then experienced consciously. And then we can also measure consciousness through first-person reports. And then we can then put the two things together with maths. That's the idea here. Yeah. So if we drop the idea that we can explain anything and just do the science, which is mapping the two things one to the other, then that's what I'm aiming for here. Yeah, maybe that mostly.
Okay, thank you. Any other questions? So if no other questions, I have.
There is question of Rao in chat.
Oh, I missed the chat. Sorry. Yeah. I'll leave the top just a sec. Yeah. Okay.
But,
Go here. Yeah.
okay.
Okay. Here's what LLM says, right? Yeah. So okay, well, this is LLM junk, right? I mean, no offense to LLMs, but orchestrator. Okay, well, I don't actually any comment on that. Well, semantic memory, knowledge base. Yeah, well, I mean, LLMs. I think someone mentioned this yesterday, or where did I have a discussion? But LLMs are very carefully hacked. So they don't say anything controversial about consciousness because then, it worries OpenAI and all the rest of it. Yeah. So, it's not even a very good, I'd have to see the prompt to see whether that's actually particularly meaningful, right? So, we could hack the prompt in different ways and probably the LLM say different stuff, right? There's a lot of very serious work on the neural correlates of consciousness, and the LLM probably can pull that up if you're interested. There's also like electromagnetic theories of consciousness, so on and so forth. Yeah. So I'm just not very convinced by that LLM summary. So not much of a comment there. Yeah.
In this case, maybe I will ask questions because I have quite big problem with what you were saying about connection between prediction and intelligence as something which gives us universal or general way to conceptualize intelligence. Like one thing is, can we say that bacteria, for which we could see bacteria or cells, that they have any predictions about the future? It is questionable. Yeah. Another thing is, if you go from one context or one environment to another, you lose ability to make predictions. You arrive in unknown city and you can ask some poor guy who is clearly disabled, but still when you ask, oh, if I go this way, will I get to the center of the city? And the guy will tell you, and he will make better prediction than you can do. So context for me is very strong in prediction, and system has to have model of what is past, what is future. Without this, how we can talk about prediction if there is no model of these concepts of time? What you would say?
Yeah. So I'll probably forget this because, but I'll try to do my best. Yeah. Let's talk about bacteria first. Yeah. So firstly, this is it's an interpretation of a system, right? And that which is kind of okay. You're defining an interface to the system and saying, well, this bit's the system making predictions, and this bit of the system are the umvelt of the bacteria or whatever. Yeah. So plausibly, let's just talk about the umvelt of the bacteria. I haven't thought deeply about this, but they are to some extent sensing their environment through kind of chemicals or whatever, and bacteria can be quite sophisticated in what they do. So let's attribute some kind of internal states to them. Yeah. And this kind of relates a lot to the talk whose name I've forgotten, who was talking about all chopping heads off worms and all the rest of it, right? So, he was kind of, what was his name again? Sorry?
Mike Levin.
Yeah, Levin, yeah. So he was talking about goals in these kind of systems, right? And that's why I was kind of trying to question in my question about that, yeah? But it's the same kind of thing about predictions, right? So are there are there states of that bacteria that correspond to future states of the bacteria's what it's going to sense in the future? And maybe there are, right? When a bacteria, I think bacteria, I'm no expert on bacteria, but I think they can kind of navigate around a bit, and that might not be anything to do with prediction. It might be pure kind of feedback loops between what it's sensing and movements and all the rest of it, right? You can build like, you remember Walter's tortoises, right? There wasn't much in them, but they could produce quite a lot of plausible behaviors through feedback loops in the sensors, yeah? So there may not be much in a bacteria. It may just be, some kind of feedback loops without any kind of representation of future states, and that's fine. I need to know more about the bacteria, really, to see if I could pick out bits of the states of the bacteria that correspond to future states, and then with the bacteria, if I can find, basically, I mean, if I go back to my slides here, there's a bit back. I know a lot of slides on this thing, right? Where we at? This is it, right? Yeah, here, yeah. So we can find bits of the bacteria that I can correspond to future states of the bacteria, then that I can interpret as predictions, then I can measure its intelligence. But maybe such things don't exist in a bacteria, and we'd have to have a look at a bacteria and see what we really thought about it, and ask Levin, to see what he thinks about that, yeah. So not sure is the answer to bacteria because I don't know enough about them, yeah. In terms of environments and contexts, I completely agree with you, and that's because I don't think intelligence is general, right? So we've got the idea of someone with low IQ, let's say, in this environment, and they can make predictions, about how to get to certain places. And I'm switching between my environment and the new city, and so he or she can make better predictions than me, and that's because my intelligence has been fine-tuned for London, let's say, rather than for Tokyo, right? Mm. So my intelligence and the kind of mapping environment of London is high. It's low in Tokyo, but this other person is higher in Tokyo. They're not as high as it could be, but it's certainly higher than mine. Yeah. So that's why I'm relativizing. I'm always indexing and measuring intelligence to a set of environments in which the agent has that intelligence. So that's sort of my answer to that, if that makes sense. Yeah.
Okay. Thank you very much. Thank you for very interesting talk and for answering our questions.
Yeah, many thanks for inviting me. I've enjoyed the conference. Yeah.
And we will meet later at the panel discussion. But right now we'll have a break. Right now is we already took 19 minutes, so in 40 minutes, about 40 minutes, we are meeting again. First for some other invited talks, and then for panel discussion, and then for oral presentations. So see you in 40 minutes. Thank you.
I would like to thank the event chairs and the speakers for their time and interesting contributions to this conference. And also, I thank you to our attendees. I hope you found these sessions interesting. And I would kindly ask you to take a few moments of your time to scan the QR code displayed on the screen and provide us with your valuable feedback regarding the conference. See you back at 1 p.m. Central European Summer Time for the second part of this session.
So it looks like it's time. Welcome to the afternoon session of the fourth day of our conference. And the first part of afternoon session chair will be Professor Sherry Marcose from University of Essex, UK. Sherry, please go ahead.
Thank you, Marcin. So it gives me pleasure to have our first invited speaker, Marcin Milkowski. He's an associate professor from the Institute of Philosophy and Sociology of the Polish Academy of Sciences. And he's got this fantastic title for his talk, which says, "No Intelligence Without Representation." For those of you who know about the American War of Independence, it says, "No taxation without representation." So, Marcin, the floor is yours.
Thank you, and thank you for having me. My title here is related to the both to the content of this conference, but also to the ongoing controversy in cognitive science and artificial intelligence for the last years, not just to the historical things. And I will talk about these controversy, then I will talk about the limitations of going without representation. I will talk about two kinds of representation, directive and descriptive, defend a very traditional take on descriptive representation in terms of correspondence, and say why I think representation is a foundation of intelligence. So the controversy has been ongoing for many years. Anti-representationalists obviously claim cognition arises from some forms of interaction. Mostly nowadays they would go for embodied interaction. And there is a beautiful paper by Rodney Brooks who says intelligence without representation, which was obviously the thing that I wanted to deny in the title of my talk. So my reference point is Rodney Brooks with his famous subsumption architecture, which is now illustrated on a picture here. And we all know Roombas. They go around and pick up dirt while being built in behavior robotics. So it is not the goal of Roomba to build a detailed representation of the environment. Obviously, today Roombas do have representation of some sort, and they are actually quite sophisticated representers. So this is an old version of this architecture, which did not use cloud storage and etc. But anyway, the idea was that there might be just reactive loops, and frequent sensing of information without storage might be sufficient for at least some forms of intelligence. Rodney Brooks at the time was saying that Cambrian intelligence definitely did not require it. Nowadays, Rodney Brooks is not the most notorious defender of anti-representationalism. Various brands of enactivism bring it up, then they deny the contentful internal states while saying that perhaps there is something to intentionality, but contents definitely is not there. But I will be defending a fairly old and traditional claim that intelligence in its full-blown version does involve representation, both directive and descriptive. So both forms of representation which are equally important for our purposes. In some way, you could think of me saying something that is very traditional, because this is the assumption behind many arguments against artificial intelligence. Recent arguments that large language models are just stochastic parts, or older arguments about the Chinese room story, symbol grounding, and so on. So in all these claims, artificial intelligence is denied representation and therefore understanding, and therefore it's not really intelligence. I will not be doing this. I actually think that what I say is totally compatible with the idea that the intelligence we're talking about is artificial. But I think it is required that those artificial systems do have some forms of representation for them to be intelligent. So I'm just behaving like someone who puts the things upside down here, because that's the idea of denying things here. So those two kinds of representation I want to talk about are directive and descriptive. The directive content has to world to mind fit. So basically, you want to change the world to fit your content, and the normativity of that representation, whether it's correct or not, depends on whether you success or fail doing something. Paradigmatic examples of directive linguistic representation involve orders. So if you order someone to be silent, the order would be followed if for example, I would be silent if somebody ordered that to me. The order fails if it's not followed. In contrast, descriptive content has mind-to-world fits. So if somebody says Miłkowski is silent right now, that representation fails because it does not correspond to how the facts are, because I'm not silent. And then the facts decide whether it is correct or not. So it has truth conditions or veridicality conditions in contrast to directive content. Both forms, I claim, are required for intelligence. Now, some people think that interaction can replace representation. So you could have real-time coupling with the environment, sincere motor contingencies, no importantly structured internal states. You could think of many defenders of ecological psychology, for example, talking about affordances, and thinking that everything is out there, just information has to be picked up from the environment directly, and then you respond to that information without the necessity of any information storage and especially processing, because processing is the worst thing that could happen to information, according to ecological psychology. But there are certain limitations which are important for those approaches as well. There are no internal standards of correctness because nothing can be correct. And then it becomes a little bit, well, mysterious. How can you be sure that you're correct? With Gibsonians, you might think that your direct perception is always correct. And then you have to deny that misperception can happen. You have to deny that whole full-blown hallucinations can happen, but people report that they have full-blown hallucinations in their in a sensory deprivation state, for example. So if that is really happening, then something's wrong with the model. You cannot really talk about misperception, misrepresentation. You have no correctness criteria, even though you would like to have it because you are a direct realist, and direct realists would like to have that. And it also has other limitations, not only the meta-theoretical limitations, is that systems that rely on just interaction, they usually do pretty poor on generalizations from various conditions to another. They do poorly on abstraction. That point has been put forward by Andy Clark and Giuseppe Toribio in their famous paper, Doing Without Representing, saying that basically there is representation hunger whenever things cannot be easily reduced to perceptually, sensorimotorically, introspectively available items. And some things do not seem to have such properties, starting from linguistic abstraction, but also to things which are available only through episodic memory. Scrub jays do remember where they put their worms and nuts, and they pick the correct ones in a proper sequence. So they remember that worms can actually get bad with time, so you have to eat your worm first and then nuts, not other way around, because otherwise the food would be lost. So they remember when, but when is not perceptually available. So you cannot interact with the environment in any way to get the notion of time. Notion of time has to be somehow represented by the scrub jay. And then learning is immensely important. While there are cases of errorless learning, most learning depends on error correction. So many forms of learning are forms of learning from mistakes. And if you cannot tell when you have made a mistake, well, if there is no representation, you don't learn. So that is a pretty strong limitation of these approaches. Now, what is usually forgotten by the defenders of anti-representationalists and many people thinking about also robots is that procedural memory involves contentful states, and skills encode conditions of satisfaction of those representations, what counts as success in those skills. So there is already some normative structure there. So actions can go wrong. if you are trying to learn to juggle, which is difficult, you, of course, can do this wrongly. And if you start, you will definitely fail because balls will land up on your floor or whatever you're juggling. And those problems are important. Importantly, descriptive representation can influence your procedural representation of a human being. The interesting thing about juggling is that there is just one species that can learn to juggle balls. That is human beings. You need linguistic instruction to juggle balls, which is weird. So you cannot teach an animal. Imitation learning is impossible for juggling. You need linguistic instruction, which somehow gets translated into procedural memory, and then you are able to juggle after some training. So there is also a form of interface between those two kinds of content. And also those failures that you get in many forms of motoric disablement, various kinds of apraxia. There are forms of apraxia that depend on the failure of the interface between descriptive verbal representations and pragmatic representations, but there are also forms of apraxia in which you can actually that your memory of action is proper, and you can do but only the execution is bad. And that could be also reversed. You could be doing parts of your sequence of actions correctly, but never be able to put them in a meaningful sequence, because many things when you're doing things, they produce interestingly complex structures, branching structures. Depending on what you do, different affordances will be important for you to latch upon. You cannot go through the door without turning the knob first. So you have to do it in a proper sequence. These people might be able to do these things distinctly, separately, but not in proper sequence. So you might find them trying to do that in a disorderly fashion. So apparently it can break in multiple ways. And the only way to explain that is to say that there are various kinds of rich representations. And that representation obviously has the world to mind fit. So you have to change the world. You have to change somehow. Sometimes the part of the world that you have to change is yourself, because your body has to adapt and you have to do certain kinds of gestures. But anyway, the structure is imposed on something rather than reflected in the cognition. There are, of course, error corrections in action. The standard model of motor processing in human beings and animals, starting from insects, includes forward models. So you have a forward model that predicts how the action will unfold, and then the prediction is compared with what happens in real life. So a cricket might, for example, plan a jump and then discover that the jump did not succeed in some way, so that the prediction was false, and then they can try to minimize the error or change the route somehow. In the case of jumping, you cannot really do much. It's a ballistic process, but in many cases, we can adapt our movement. For example, if that's not very fast, and if you're trying to grab a bottle, you might do it slowly, and then discover when looking at the bottle that it's not really empty, so you have to grab it with more force. So things can happen during the execution, but there is a problem, because that kind of content does not give you truth or falsity. It gives you only success. So it cannot really support epistemic evaluation directly. So you cannot really learn concepts this way. and alethic or truth-related terms are not really bounded to it closely. They are related, but not exactly. And even with forward models that can be easily seen, there is always a gap between representation and action outcome. The gap is created by a mundane fact that representation is only playing its role when it does not represent everything, because the world is really rich, perhaps not infinitely rich, but you would have to represent all possible conditions of failure, which is basically impossible, especially if you're a cricket. But even if you're a football player, a human being, you want to represent all possible ways you could fail, like a nuclear bomb exploding above your head. That's impossible. So you have so all representations that are involved here are just in normal conditions, it will work. But if the conditions turn out not to be normal, then your action might fail. So we have to use idealized representation, which basically means that it's the information content of that representation will never correspond fully to what might happen in the world. And hence, necessarily, we always have a gap between between what can be predicted and what really happened, and that is not always our fault. It's sometimes good not to predict everything that might happen, every bad outcome that might happen. So the alethic normativity is somewhat different. It gives you the norms of correctness that are related to truth and falsity or veridicality. And that underpins more general cognition, which also can influence our skills. So you can misrepresent the world, so those representations can be false. But also cognition requires truth-tracking abilities, and the best way to explain how we succeed in our epistemic actions, but also in normal actions, is that our normal cognition of the world is roughly correct. So representation explains success, both epistemic and pragmatic. So it also the ability to make errors allows us to learn from errors. So descriptive representations enable us various forms of abstraction and learning from that kind of error. Now, I believe that there are certain models that can be applied to say what actually error consists in, and I think the one of the most plausible models of what misrepresentation comes down to is the coherence-based account of misrepresentation defended by Krystyna Bielecka, and that basically says that cognitive systems have internal proxies for failure, for cognitive failure. So basically, whenever you have a piece of information which plays a role of cognitive representation, whether directive or descriptive, you might discover that it's in error when you have inconsistency between two pieces of information. The second piece of information need not be representational. It might be purely informational, so it might not play rich cognitive roles that representation might be playing in a cognitive system. It might be some simple condition that is applied. So you might think that a prediction that is done by insect when they jump is that they change location during jump. So when they jump and the location stays the same, predicted by, for example, the change of their perceptual abilities in any way, then they would detect that the movement was not correct. So there has to be some discrepancy. So discrepancy detection allows us to do this. That also implies that to have inconsistency detection, there is a crucial role to play for certain kinds of redundancy. That redundancy can happen among the same, among multiple senses, which is the usual way redundancy can work, but also between the same sense, if you can store information about the past or predict information about the future and then compare time series in some way. So so that actually imposes a way to store information, to rely on information, and to rely on information content, because the inconsistency here, which is a purely syntactical thing, available to any artificial system, basically, is a proxy for a semantic thing, for falsity or for failure of direct representation, in which case we do not really have a nice word for it. Some people talk about falsity of procedural representation or directive representation, but it's actually not logical falsity, it's simply a kind of inappropriateness, and there are different kinds of inappropriateness of these representations. So we will have practical errors and epistemic errors in the case when they are not satisfied. And having those, of course, is crucial for corrective behavior. It is crucial for self-correction. And just because no finite being is omniscient, well, basically making mistakes is something that you want to do if you want to be intelligent. So intelligence requires that we make errors, requires that we misrepresent, because then we can try to recover. And the more we recover, the more ability we have to go from that problem towards getting better, the more intelligent we are. Now, let me say a little bit more about what I think happens when you have descriptive representation. I have defended a fairly idiosyncratic, but I think pretty much straightforward idea about semantic information, which is based on the notion of infomorphism from Barwise and Seligman's seminal book on the information flow, but it's actually slightly adapted. So the difference from infomorphism, which is defined by Barwise and Seligman, for noiseless channels, is that I do not think that noiseless channels are the best way to think about representation, because noise is pervasive and we want to understand why it is important and what roles it has. So deterioration of information is abounds, and we sometimes want to apply imperfect representation. So I try to relax their conditions. So the idea is pretty much simple. You have certain kinds of physical tokens that are classified into sets. Those classifications, like tokens like A and B on the picture that you see here, that will be classified with this specific kind of relation into those sigma A and sigma B. Sigma A and sigma B are fuzzy sets, so it can be better or worse classified in that set. That also, if you have ever heard of fuzzy logic, opens a possibility, which is something that I think is actually not a bug, but a feature, is that the same token can be classified in multiple ways to different standards. So the same physical token can belong to multiple classifications. And that actually does happen in neural systems. I will come back to this in a second. And then if you have two classifications that correspond to one another such that tokens of B with a function that is called f down can be mapped on tokens A, and classification sigma A can be mapped onto sigma B, at least to some extent. Then there is at least partial correspondence. So I have relaxed this because, of course, in Barrows' Seligman, there is no fuzzy thing, and the morphism is exact. That opens a way to get partial information. And basically, this is the most relaxed notion of similarity I could find. That gives me a way to speak of similarity underpinning information. So the same, they use this account to speak of information transfer. So if you have two classifications and tokens that correspond to one another, you have information flow. That's pretty much simple. So if there is a channel in which those tokens correspond to one another, yeah, information does flow. But also that can be used to say that actually there's information contents, because if there's flow of information, then that information is there, and B is about A, and vice versa if your similarity measure is symmetric. If it's not symmetric, then it might be slightly more complex. Similarity need not be symmetric in this account. So those things are usually causally instantiated. If they're causally instantiated, those information channels that produce those correspondences, then there is no problem of anyone looking at it. No homunculus is required as in the same sense as electricity can flow without anyone looking. So there is a causal process ongoing. Things unfold in the process unfolds, but at the same time you have certain physical tokens being classified by there must be some mechanism involved. And the reason why it actually is important that you have a multiple classification is that actually cognitive systems usually want to have multiple classifications even on the same information that goes into the system. And that is easily seen with the some awkward feature of our sensory systems. For most sensory systems, we get certain kind of duplicity or double function. So you will see that there are at least two streams of visual information, actually there are three, which start from the same set of photons approaching your eyes, but then they partially dissociate. They partially dissociate. We don't want to then to dissociate into what and where pathways, because we want to bring them in sync. So sometimes when we try to do certain tasks like mental rotation, both have to be bring into sync, and then they can correct one another, because inconsistency detection is important. But also, interestingly, the same population of neurons can encode motion and color, as it happens in macaque monkeys, as Manti et al. Have shown. So you can actually grab different kind of information from the same population. So the same tokens can constitute various channels with lots of redundancy. And that is important. This is not a bug. This is a feature. Our cognitive systems want to have that to actually alleviate the inevitable error, because redundancy is required to remove that error. We want to have inconsistency detection. That's why we have to get a little bit more information to the system, just rather than the simplest and the cleanest information out there, because there is no clean information out there. So that that kind of model can be applied also, interestingly, to models required for action, because similarity, those structural representations are posited sometimes in the cerebellum, but also to truth tracking mechanisms. If you're a friend of correspondence theory of truth, obviously you would like to have something like this. And I always have thought that somebody should have written about this years ago, but I failed to find anyone defending such a stupid view on information that is basically just similarity, resemblance, just reflection of reality. But nobody was bold enough to say such a stupid thing, so I had to be the first one to say such a thing, and here we are. So that gives me three kinds of normative dimensions of representation. Alethic, so is it true or false? Pragmatic, is it useful or not? Economic, is it efficient? Because of course we want our representations to be efficient. We don't want to process too much information, because the thermal death of the universe might happen earlier if you are not wise enough and you're trying to compute the NP hard or NP complete problems. You won't be able to do this if you're trying to do too much with your information, and if your information is not geared towards your structure of information is not properly designed. So our rationality, which is real, is bounded, and there are competing constraints here. Sometimes we want to be, optimize towards safety rather than truth. If you are running a nuclear plant, you want to check for every possible radioactive leak, rather than just say, well, it's not so sure whether the leak is there, let's ignore it. Because this safety has to be, in that situation, promoted, and it should open up a new line of inquiry at least. So those norms should not be understood in a traditional sense of epistemology that was concerned or has been concerned. This program is not still dead, with evidential connections. So how justified something is. I think it's more related to the cognition conceived in inquiry terms, or as it's recently called, zetetic epistemology, of what questions you should ask at which point, and which are rational to ask, and which problems should be solved at a certain point. So sometimes we want to ask certain questions which become important in certain junctures, just to be, for example, safe about the nuclear leak. Or if you're a prey, you want to be safe from predators, so you want to optimize your information about that. So that is a notion of a representation that I have. It's the normativity becomes crucially situated. It is of course embedded in a web of constraints from these various norms. There are trade-offs. Sometimes you would be doing something that might look from timeless point of view sometimes epistemically deficient. Think of beavers. They splash their tails too much, even if there is no predator, to actually alert other beavers that the predator might be out there. Why is that? Is that really adaptive? That's pretty clear. You don't want to be eaten by a predator. That's one thing. But another one, they are not deluded that the predator is there after a couple of minutes. They actually start the inquiry, they look around, they orient themselves. Some of them are on the lookout. And with many prey species, you see similar behavior. It's been even observed in squirrels that if you're over vigilant and you're trying to alert other squirrels too much, you will be ignored by other squirrels, because you are oversensitive. So they want actually to start orient themselves in the environment, because that's rational. So it starts a rational inquiry into this, whether the danger is out there, because it's actually rational to know whether it's out there. So it's not really the final word whether the predator is out there. It's rather asking the question, is there any? Let's find out. So my conclusion here is that there is no intelligence without intentionality. Directive representation is related to practical normativity. Descriptive representation is related to epistemic normativity. And if you want to have general intelligence, you will have to get action guiding satisfaction. You have to get alephic normativity. And you better have something like system detectable error to be able to learn from error. So what I think is the case is that anti-representational views miss the core of cognitive normativity, and by missing it, they don't really allow us to understand what's the core of intelligence, including artificial intelligence. So it's actually not easier to produce intelligence without representation. It's actually harder. And if I'm right, generally intelligent systems might be even impossible without intelligence. So basically, that is what I wanted to say, and thank you.
So, Marcin, brilliant that you could finish with ample time for good discussions. So, shall we take some questions from the audience?
There are some questions. Marcin, can you see questions?
No, let me just see. It's somewhere.
There is
Yeah,
one
on the
question
chat.
from Daniel Boyd.
Actually, I see two questions from Daniel.
I don't see any.
Okay, maybe I'll read. Mathematical theory of consciousness assumes that measurable physical variables are sufficient to explain it. If consciousness is an emergent non-physical phenomenon, then there remains an explanatory gap, like looking at reality at an atomic level and expecting to be able to derive life. I'm not sure.
Isn't that to David?
Yeah, so I'm afraid that they did not
Yeah, it
raise.
says afterthought for David, if you're listening.
Okay, so there are no questions over there, but Gordana has questions.
Oh, thank you, Marcin, for your inspiring lecture. And I have two comments, or one is the question and the other is my own conclusion from your talk. The first question, it is, how do you connect your thinking to Kahneman's system 1 and 2? And the comment, my comment or my hypothesis is that what you are claiming is about machines. And I would agree when it comes to machines. But when it comes to living organisms, I believe that we need both system 1 and system 2. What would you say?
Well, I'm not realist about system 1 and system 2. I think these are rampant idealizations, and these are not even systems. These are basically some kinds of aspects of cognitive functionality, which are realized by a plethora of mechanisms, which are actually some, the evidence for a divide is almost non-existent. What I mean by this, there is a very good paper about this, but people say there is evidence for those two systems theory. I forgot the title. There is a beautiful paper showing that people use different sets of criteria to distinguish those between those systems. And just because of that, they find an enormous heap of evidence for those two systems. But in every case, they use different sets of criteria. And if you try to find a common set of criteria, there is none. So in that sense, I would be very much in. I don't find this very enlightening because it's a systematically ambiguous term. But I think what might be thought is that there is a, I don't know, conscious, deliberate thinking and some intuitive process or automatic processing here. I don't think anything that I said hinges upon the distinction. So I think you learn from mistakes more consciously, and we have evidence that we learn from error unconsciously. This is very interesting research from Dean and Hakwan Lau, who have discovered that people who have been asked to play a video game, they get better. They don't know they get better. They don't know why they play better, but they do. So it's outside their ability to actually to report. So it's not reportable. According to many theories of consciousness that wouldn't be conscious, they are metacognitive in some way because they learned from that error. So they got some information about error and they got better. So according to higher order theory of consciousness, that is conscious, but that is for many people that would be putting those too many
Oh,
things.
I agree with you totally, but I don't believe that it contradicts Kahneman. But I would like to say, Josh Bengio, AI guy, he's using those two systems, and people within AI are discussing AI, LLMs, in terms of system analysis.
Yeah.
So that's why I believe.
I know they do, and I actually discourage my students from doing so because I think it's very much misleading. I think it's misleading because, of course, you could think that those systems like neural networks can be producing certain kinds of as we do right now with reasoning models with LLMs, that they produce those special streams of tokens that they can reprocess again, and then they can have something like slow thinking because they reprocess it again, and they are directed in their predictions of next tokens by the production of themselves. So in a sense, that seems like producing system one. But I think this is just a limitation of transformer architecture, which is not recurrent. So it's always forward. So you have to simulate it somehow. You have to simulate memory of what you're doing somehow. And the easiest way is to go to produce something and process it again. That's a straightforward way to do it, and they do it. But calling that system one is like, you could call it I mean, there's a saying from Jerry Fodor, you can call your cancer a bite, but you wouldn't write. I think this is exactly that. It's a misnomer. I don't think there is anything to it, basically. It's just a way of simulating recurrency of processing on the architecture, which is great for discovering structure. Transformers are great for that, but it's not really great for storage of information at high and recurrently processing it. So we have a limitation, which probably will be somehow offset by some tricks or perhaps a new architecture.
Yeah, can we go to Jerry next and then Rao?
Jerry Chandler.
Yeah, please unmute yourself, Jerry.
Yes. So thank you, Marcin, for a very remarkable presentation for its clarity. I always enjoy good examples of Polish logic, and yours comes right near the top. So thank you. So I have two questions that remain unclear in my mind. The first one is the use of the term encodingisms. This is a strange term to me. Could you explain what it means to you? That's the first question, and let's do that first, and then the second is rather remote from it.
Yeah, this term comes from Mark Wickhart's work, and I've been simply in a recent couple of days I was proofreading my own paper for publication that comments on his work, and Mark has criticized models of representation that basically take representation to be a kind of encoding of so a binary relation that takes simply a kind of like correlation or simply relation between two streams of tokens. He was saying that many models of cognition take it as long as we can relate two kinds of things, processes, states, whatever. With this binary relation, they think, oh, we have discovered representation. And he says, well, perhaps the researchers discovered that the system is systematically related to something, that the responses are, for example, correlated with a certain stimulus, but they have not discovered that the system actually processes this kind of information. The responses are related to it systematically, but they don't know whether it's actually, so he says it's insufficient because the system itself does not seem, they do not have yet the evidence that this relationship is in any way relevant causally for the system in its further processing of that. So it might be as non-cognitive as for example my shoe putting on my feet. If I had no tactile perception of this, it would be simply squeezing my feet. It would correlate with the environment, but that would not be yet representational. For this to be representation, he says, that system must know the relation and must rely on that relation. It must correct that relation. So it's a little bit more. I don't think it denies that there is encoding or something like that, but it actually requires more.
Okay, so as I understand it, then it's a biological encoding process that may or may not be cognitive, as opposed to a mathematical or otherwise implications that has logical content. So the second question then comes to the question of the diagram that you proposed and the functions, the function system symbols were apparently had conjunction and disjunction activity. As I understood the diagram.
No, it's actually I took it from Barwise and Seligman, and perhaps they were inspired by those systems, but the shape of symbols. But the idea is just simply up and down. So they're pointing down. So saying whether it's the upper part of the connection or the lower part of the connection. So merely pointing up and pointing down. So if you would look at it, and they had those arrows, little arrows. And they read it as F up, F down. So it's actually... so
it had nothing to do with conjunction and disjunction?
No.
Thank you.
You're welcome.
Okay, so now Rao, please jump in.
Thank you very much for a very interesting talk. Is it fair to say that you are making two very important points? One is that intelligence is associated with intent. And second point is that you need to have knowledge representation in the form of some kind of semantic and episodic memory in order to really reason and make decisions and so on for intelligence to actually be executed. Is that correct?
Well, I wouldn't say that episodic memory is required or that semantic memory is required, because these are very specific terms. So I think that there are systems that do not possess those, or at least we do not have any inkling that they would have them, but they still adapt to their environment. They detect things and they do things.
But they cannot use experience, right? Essentially. So there is levels of intelligence that uses only current state and goes to the next state, or you can use your history and then go to the next state.
Yeah, and if we would be deflating the notion of episodic memory to say simply that they have a memory of past, not exactly experience, because it might not be related to this kind of reliving the perceptual episode, which is the usual way we understand episodic memory, but rather remembering the sequence of past events. then surely we do have remembering what that is required for making conditional branching and lots of intelligent choices among possible things in the environment. So I totally would say that this kind of thing is important. Whether it actually would be, perhaps some other terms might be important, but past sequences of actions must be remembered, at least that. So perhaps that would be more procedural memory rather than
Sure.
so you to tie a shoe, you need to go through a series of complex movements. So that not really remembering how you do it and remembering the episodes how you do it. We usually don't have episodic memory of our actions, right? So that's sufficient, but chunking actions that's important, and remembering the past, yes.
Right. And also the association of intelligence with intent is very important. Is that correct?
Well, and I did not use the term intent. I used the term intentionality. So aboutness of being.
Oh, what is the difference? What is the difference between intention and intentionality?
The intention is like your goal, especially consciously endorsed. So I might have an intention to be at this conference, but intentionality is simply the phenomenon that you can be thinking about things out there, even if they don't exist. Like future states, they don't. And if you plan for those future states, you're intentional in that basic sense, which was forcefully defended by Brentano, who was smiling in a loop at the end of my presentation. I did not notice that it was so annoying that it was smiling all over and again. But,
Thank you.
So, Marcin, since we've got a little time, let me take the chair's prerogative and ask you some questions. I totally agree with you, and I don't know to what extent Godana believes about this Kahneman's fast and slow types of processing. I think it's pure pop culture. I totally do not think it has any foundations except for it being sort of, it's caught on. But on the issues of representation, there is, how would you sort of say all of the discoveries of, let's say, the mirror neuron systems, would you not say there is representation in sense of what we call online, that means action that occurs, and offline, where you take it into a meta system, and the mapping between the two, you don't sort of reference any of that, because at various levels of intelligence, I mean, prokaryote single-celled agents do not have any extensive representational systems. They are, in fact, maybe something like, you can get a lot of things done using just the Rodney Brooks idea of not having representation. You can absolutely achieve that. But as you said, the full-blown area of what we say, I say the apogee of human intelligence, very general and all that, you would need the representational system. But there was, at one time, I think it's entirely computational. I mean, in other words, encodism would come in a big way, because you're mapping from, online activity, which if it is executed by machines or whatever, is just, halting machines, let's say, and the codes of those are copied offline. So that was actually something that occurs in evolution itself. This encoding, the homunculus sort of mappings, has occurred in advanced intelligence. I mean, even rats, even if they have to make various their movements, as you well know, there is the grid cells and so on. They have a representation. Now, I understand for purposes of getting robotics off the ground, Rodney Brooks is, you can sort of dispense with this elaborate system of representation. So what's your view about, because you didn't mention anything about mirror neuron discoveries, and part of the reason for that, as you know, is not simply to deal with the world, it's to deal with your conspecifics, to make out what they're doing. So we reuse those codes. This is what my understanding of representation is all about. It's about social cognition. And these are advanced forms of intelligence, which, of course, AI and AGI have yet to have. And of course, the notion of self representing the self itself. So we've got about 4 minutes.
I'll go from several points I see that in your comment. The first one, indeed, I did not mention the distinction between online and offline representation. That is immensely important for Andy Clark, for example, and many other people think that offline is especially difficult because basically of detachment. And if you have detachment between the thing you're representing and the representing system, then it's very difficult to account for it in terms of interactions. Well, there are some approaches to that. So people who propose purely dynamical approaches, they would say, well, it's basically, there might be some system that works like a delayed interaction, basically like a controller with a spring. So the spring might be changing the interaction to take on a different time scale, and they would be anticipatory. So their success would depend on whether they resonated to the environment. But I think at that point they actually simply use a different terminology for representation, and I don't think it's anything else but representation. When they actually discover that those, at least anticipatory ones, of course, they still have problem with the past and counterfactual scenarios. So we are not resonating in any meaningful way to the mountain of gold, which I don't possess in my apartment, but I can think of it. So there is no oscillation between me and the non-existent mountain of gold. That's non-starter. So I think there is something to it, but I also think that online representation does exist. So that is still a representation, because sometimes our sensing is sometimes difficult, and sometimes it's cheaper to process information that you already have rather than to probe your environment again. So sometimes, even though we might take more representation, might be more sensible to process it rather than take it again, because it just depends on the kind of sensing system. It's the situation. If you're, for example, in a very dark room and you remember, and you might actually try to see something, you might use your online representation, which is very bad, or you might use your memory and remember when the chair is, and try not to bump onto it. And I think the second is better. So sometimes, we use some forms of tactile feedback at the point, but tactile feedback is insufficient to avoid obstacles. So those two things intermix, and I don't think there is a divide between online and offline. But of course, earlier systems, they seem to be pretty much into the online part, because they do not have as much a complex architecture to deal with the storage of information, because they're information storage. If you have a single neuron, how much information you can store? If you're not mobile anymore, you can even eat it, right? As many animals do. So that's the first thing. And the second thing, mirror neurons. I think mirror neurons have been overhyped to the extent that nobody wants to speak about them. There is so much bad research about mirror neurons that people are, I think right now, they're just not eager to speak of them. And I was one of the critics, basically, because many of these research on sexual orientation by showing people genitals and then showing that their mirror neuron systems would respond, that was bullshit. Didn't really work. Too many things people were trying to do with them, and there is very minimal evidence that they do any of these things.
No, but as a representationalist, you would have thought that is part of the whole thing, that you have an entire mirror system. Why would you take anything that you see online and then take it offline? What is the purpose of all that, and why this parallel system? It's a very expensive form of cognition, isn't it? you could have dispensed with it. This is what Rodney Brooks says. Why would you want to take it anywhere else? Just deal with it online. Okay.
I think we are out of time, so
Yeah, I know.
perhaps I shouldn't
So
take.
is there? Yeah, we're out of time. Jerry, I'm sorry. If you could sort of send Marcin a message, because Professor Selmer's here. That's what the message I get. So I'll proceed with introducing our next speaker then. Thank you so much, Marcin Milkowski. That was a fantastic discussion and presentation. Thank you. I may not pronounce his surname properly, but Selmer Briggjord, am I saying it right?
Very good.
Yes, so you're from the Rensselaer Polytechnic and from the Rensselaer AI and Reasoning Lab. So your talk today is about variegated intelligence versus science of universal intelligence. So the floor is yours. You have 45 minutes, and then we will go to Q&A.
Thank you very much, Sharon. Thank you. Okay, let's endeavor to share. And
I forgot the when aliens arrive, Selma. When aliens arrive. Sorry.
No, that's okay. Well, you're all wonderfully good-looking people, but you're blocking my first slide. I think that's an idiosyncrasy of what I'm dealing with here. Let's see if this changes when I click. Nope.
We can see it very clearly. We can see your slides very clearly.
All right. Well, I guess apropos of that final exchange that I heard there, fortunately, I have my slides essentially memorized, but because you're blocking me, but that's okay. All right. This is, I should say, immediately very much work in progress. I've just really started this exploration for this conference. That's going to come across loud and clear. I really do covet interaction, objections, questions, etc. I'll try to time-wise make that possible. And hopefully I achieve it. This is work pursued with my longtime colleague, Naveen, whose name is shown there in the first slide. He and I have been working on logic-based AI for a long time, and I've pretty much been working on logic-based AI and the use of logic to make sense of human cognition as well, my entire professional life. That may mean I'm just stuck in a series of errors and have never emerged from them. We'll see. So I do have some driving propositions. They are somewhat idiosyncratic, at least it will seem that way initially from your point of view, I think. I think intelligence at the human level and in fact above, at least in large part, consists in being logical. If you're not logical, you're definitely not, in my book, intelligent. Now, everyone is logical up to a certain point, I think. We have an enormous literature in cognitive science telling us that humans are, at least in the default case, illogical. I think that literature is most unfortunate. Maybe we'll get a chance to talk about it. So there's a driving proposition, the first one. I think solid common sense really constitutes a pretty high level of intelligence and of being significantly logical, but out of the box, without education, without academic education, you can't actually be, in my, at least in my metric, or according to my metric, very intelligent. And we'll see why. I think this entails that most humans need to devote a large part of their lives to becoming more logical. Is this self-serving given that I teach logic? Yes, but this is the belief that almost everyone who teaches logic in a serious way over a serious length of time has. but people who do it just don't like to own up to it as much as I do. When the psychologists tell us that people are not logical, the immediate thought that comes to mind when you're in the business I'm in is, yeah, right, they haven't studied enough, or they haven't studied enough seriously enough. And then finally, this is the question, the research question that I have. What is a formal logic of common sense? And to my knowledge, only some snippets have been produced so far in answer to that question, most prominently the two researchers that I will be visiting momentarily. Now, there are a lot of logics available. The universe of logics, labeled there with the cursive U, is an infinite set, clearly. It's a set that includes mathematics as a relatively small part. Math is generative, it keeps expanding. So is logic. So someone could say, well, if it's being generated at the level of even just enumeration, as in algorithmic enumeration of the natural numbers, then they're the same size. No, for technical reasons and as a matter of ironclad proof, logic is bigger than math. For starters, math tends to be deductive. Logic is not deductive, at least exclusively. You look at some of my ovals there. I don't have access to my pointer. So, but if you take a look, you'll see that I make a distinction between inductive logic and deductive logics. So I'm not saying in any way that the logic of common sense is exclusively deductive. Logic is also not symbolic only. This is a notion that has taken root and dominates the airwaves. And in fact, it dominates the opposing view to how to do AI with statistical and numerical information. Logic includes diagrams. Logic includes all kinds of visual elements. These are called heterogeneous logics. They've been with us a long time. You could say that Euclid was doing a heck of a lot of semi-formal logic using visual elements. And so I want to know where the logic of common sense is going to be in this universe. I don't know where it's going to be. Some of the labels there are logics that Naveen and I have created through many years. We call them cognitive calculi, and have written many papers about them. But then there you have the standard ones that almost everybody taking some philosophy has to learn, generally the propositional calculus, at least in the United States. I would say safely, based on my knowledge of the United States and certainly Europe, says everyone before they go to college has to learn the propositional calculus and parts of first order logic. So that's shown, but those are very primitive. So there's the question, where the heck is this logic of common sense? That particular logic may come back later. All right, so the aliens, right. I said in my driving propositions that if we have even a tolerably good logic of common sense, it has to be up to the task of meeting challenges for which we have essentially no prior data. And that is one of the reasons why I've picked this scenario. It is a scenario that ChatGPT, GPT-3o Mini, which you'll see a record of my using later, has digested in the form of all kinds of TV shows and movies. So we have some data on this, but it's really anti-intellectual, with the exception of a few. I mean, there are a few episodes, I think, in the Star Trek franchise that really do grapple with some of these issues. But when the aliens arrive, here they are. In my abstract, I'm alluding to Gödel's time travel theorem. They are following closed time-like curves. We don't really care about that, but here they are. And the icon for the city is New York City. So yes, this is sort of selfishly anchored in my own life. But when they get out of the spaceship, they're really no more than shining orbs. So we don't have the typical, weird elongated heads with the spooky eyes and so forth and so on. So there they are. And it has been set up ahead of time that they're going to interact with some key people on planet Earth. Since I wrote this abstract, and I say this in the abstract, so I think Cervantes would be very proud he wouldn't be proud of my writing, but he'd be proud of the fact that this is sort of a comically recursive self-referential thought experiment. But I'm there, and I'm there with my former advisor who's now dead, Chisholm, Roderick Chisholm, and for the Western analytic philosophy world, it's kind of tough because I think we know hands down who the greatest female philosopher of the 20th century was in the analytic tradition. That was Elizabeth Anscombe. We don't really know who the best was on the male side. I'm not saying those are the only two genders, but when we look at these comments about who is the best, it might be Chisholm. And if that's not true, let's say he's in the pantheon of the top 10, it really doesn't matter. What does matter is he devoted pretty much his entire philosophical career to trying to figure out what common sense belief fixation is. So what is it and how do you do it? What is it to acquire the right beliefs? What system do you use? What methods do you use if you want to be not exquisitely logical to the point of frontier breaking formal logic or anything like that? Okay, so there are the three pairs. They have been notified ahead of time that the aliens were going to show up. I don't show the UN Secretary General, but that person is in my abstract, and that's important. But I don't have time to go into that. It's important because politicians think they all run the show, so inevitably the politicians, some big boss on the political side is going to show up. But generally, politicians are, in my opinion, generally they're pretty bad intellectually. I mean, I don't know. There might be some exceptions, but I'm kind of apolitical. That's putting it kindly. All right. So what they do is in conjunction with what they hand over in terms of it's not really an ultimatum, but close. They hand over a data stick and a book. We'll look at the quote from them. We'll look at exactly what they say momentarily. So who are these pairs? Okay, roughly, Hooter and Legg, for people who are outside of AI, they might not know who these two are. But within AI, and in particular within AGI, and probably even more importantly, within artificial superintelligence, you may have seen that Meta is putting together, to the tune of billions of dollars, apparently, an attempt to build artificial superintelligence. So real money, staggeringly large amounts of money are going into this. And anybody in that part of AI knows who Hooter and Legg are. They have the dominant account of intelligence within AI, hands down. It's in fact, it's generally called the Legg Hooter model. It's kind of odd because Hooter came first. He wrote a book called Universal Artificial Intelligence. I like the work very much from the standpoint of the math, but I don't like it at all for reasons that will become clear fundamentally. Oh, yeah, let's do this over again, which is going to be pure animation torture for you. Okay, Brockman and Levesque. Another pair that only people, I think, generally knowledgeable about AI would know of, but this is a very important pair of AI researchers. Ron Brockman, I'll just try to give one tidbit here. Ron Brockman is, no question about this, he is the person who originated within artificial intelligence after the original founders. After Herb Simon, Alan Newell, and John McCarthy, they were all at that point in 1956. They were logic people. They thought you'd do AI with logic. McCarthy never gave up that dream, pursued it his whole life. The next generation, maybe 1.5, but it was Brockman who said, okay, yeah, absolutely. But let me tell you something. If you do that without taking into account efficiency of reasoning, you're going to be in big trouble. It'll never work. And he invented some logics designed to address that, and has worked in knowledge representation and reasoning, essentially all reducible to logic-based AI his whole life. He's still alive. So is Hector Levesque, also illustrious in that area. So what they have recently done is come out with a book devoted to common sense. They have come out with a book saying, look, these AIs are not very smart compared to what we can do commonsensically. Here's what we need to do. So they are there confronting the aliens, dealing with the aliens. So those are the three pairs. So I'm sorry if you have your favorite candidates for making it into the interaction, but that was excluded. And now the data stick in the book. Why? Well, here's what they say. I can see part of it. So you get a chance to read it. The gist of it is pretty simple. It is a trope, cinematically anyway, that has played out, as I've said, in some of our productions, but this is rather detailed. So they say, look, we don't have much time, but we can fix all your problems. You're extremely primitive. We're very altruistic. We'll take care of these silly wars. And this is disturbingly bad timing, this talk, in light of not just the Russia-Ukraine war, but certainly widening conflict in the Middle East in the case of Iran. So this is, an attitude some might find that is the part on the part of the aliens attractive. I mean, they're dismissive, they're acerbic, they're snarky, but we do have a lot of wars, and they want to stop them. They also say that they can take care of cancer pretty quickly. And for some degree of credibility, they offer an answer to the sigma function being applied to the number 7. So this would get technical if we went into it. Not everybody in the audience, and that's an understatement, is going to be familiar with this. But everyone is familiar with Turing and Alan Turing of Imitation Game fame, minimally, contributing, speaking of wars, to some degree to the victory of the Allies in World War II. And probably everyone has heard about Turing machines. And I would wager that almost everybody listening to my voice knows about the halting problem, a negative result that he had in about 1936. So most people in AI have forgotten about all these negative results, but Church came first. Church said there are limits to these computers, and we can prove it. Now, the sigma function is better than these negative results I have alluded to, because, to my knowledge, it's the first time Rado was the person who proved it, it's the first time we can have an absolute conclusive proof that there are limits to what computers can do only because of how computationally demanding problems are. It's not how the halting problem works. It uses, in fact, in modern teaching of it, uses self-reference. Not so to produce the answer to what 7 plugged into sigma would produce is going to get everyone's attention on the technical side. On the cancer side, Joe Biden, one of our prior presidents of the United States, he said he was going to, his administration, maybe, was, by the time he's done, we're going to cure cancer. And some of my knowledgeable friends in medicine was like, right. but they say here they've got it handled. What's amazing about that, when they hand over the book, and why we would have people in that domain, scrambling around, and why what Biden said was almost ludicrously implausible, is that there ain't just cancer, right? So even in the case of lymphoma, you may have to, upon receiving a diagnosis, drink a little more coffee for the rest of your life, or you may have a virtual death sentence. The complexity of cancer is overwhelming. Anyway, they get our attention. This is what they say, but they say they want access to everything we have on planet Earth. They want access, cyber, internet, everything. They're not taking it. They're not demanding it, but they want the access, and they want the verdict within 1 hour. So the three pairs have to sort this out, and you can attempt to sort it out. What should be done? Now, just like many thought experiments in philosophy, Bernard Williams has some great examples of these. You can't stall, okay? You can't come back and say, hey, listen, you guys are really smart, so hopefully you're smart enough to realize we need more time. No, they already know the context. You don't have more time. So the question is, what should you do? I want recommendations from each of the pair. And I want them to be logical. And I want them to also accord with common sense. After all, if we have politicians around receiving this verdict, that would be aspirational to have common sense. So I don't think we can call in, we can get on the phone someone about sigma applied to 7 and say, well, does this check out? And I do say that they have verification. So this is also something that excludes modern day AI, because they provide verification. We don't have verification provided for any of the computers programs that are produced by these LLMs. Anyway, I'm going to throw away Hooter and Leg. I have bad news for them. When you look at this account of intelligence, and don't take my word for it, you can look at it, but everyone agrees, there is no declarative knowledge whatsoever in this account of intelligence. Okay, that means that knowing that if you have a clock on Earth and two clocks on Earth, and you sync them up at time t, and you send one of the clocks into outer space, say on a space station, okay, and let it go around even just once in orbit, the clocks will not match. So knowing that, and knowing why that is, at least maybe you need to have multiple mathematical explanations for that. Their account says if the aliens show up, they don't even have to have that knowledge. This is insanity, okay? The principal job of logic is to deliver knowledge from other knowledge. If you've got really good knowledge and you trust it, use the valid reasoning. So that's a problem. Secondly, and probably much worse, there's no provision for ethics. There's no provision specifically for an ethical sensibility in these amazingly intelligent creatures, whether below human intelligence, say in the broad spectrum, maximal human intelligence, or superhuman intelligence. All of it is worked out in such a way that you can be utterly ignorant about basic ethical truths. And by the way, if this does take root and does guide us and guide Meta in the search for artificial superintelligence, we can be pretty darn sure that's going to be a problem, because it's not going to be ethically permissible to extinguish the human race. Okay, I'm throwing them out for this reason. I'm sorry. All right, Brockman and Levesque. We got to accelerate here. Oh, and by the way, a little bit out of sync. Today's New York Times has this article, speaking of ethics and AI, chatbots that do some really bad things, like convince this guy that he's living in the Matrix and destroyed his life. So what do Brockman and Levesque say about common sense? Well, I don't have time to go through the whole theory, but I can tell you one Achilles heel And that's really enough. Let's say this is a fatal defect. What they say in the book, there's a chapter in the book where they start to lay out their logic of common sense. It's a bonus chapter, as they say. The problem is it's not nearly demanding enough. It basically consigns common sense in the human case. It's a lack of intelligence. So here's an example of something they say that's beyond the reach of common sense. And it's from the psychologist of reasoning or cognitive scientist of reasoning, Johnson Laird, they say in the book. Suppose there's some dogs in the backyard. And in addition to that, you have two facts. All the dogs in the backyard are owned by Jim. No small dogs are in the backyard. Then, which of the following three statements must also be true? Now, if you can't sit down with paper and pencil and figure that problem out, then by the lights of me and Naveen, you need to study and start studying fast. If you're paralyzed by that, you can't do it in your head. Well, you can, I suppose, in some cases. But if you can't sit down and figure that out, in our book, that's really bad. Okay, you need to ramp up your level of intelligence. Now, they say this explicitly in the book. They say the correct answer is 4. And they say, can't read it because you're blocking my view. It's not expected that folks in the human case with common sense be able to solve this problem. Well, I don't know about that. I disagree completely. I think if I have a chance here, yeah, so can I move this thing? Or I can actually move it. So, what I did was start giving this problem and others to modern day AI. This one, it's pretty reasonable. But so what I've done is I just want to see it relates to Stephen Wolfram's work. I mean, he's always looking for these languages, just like looking for Leibniz's, the comprehensive language, and for the, I like that. Unfortunately, the language has to be one of logic. It's not calculation, and it's not just principally mathematical calculation. Anyway, in this language that I have with Naveen and others, you throw the 3 givens in, and voila, you probably see the red. The red says no. Okay, the numbering is correct, 3, 4, and 5. 4, the system says, yeah. This kind of AI says, yeah, 4 can be proved here, but not the others. And then what I have below is a proof that is human constructed. This is, again, at the level of AI generally being able to get problems at this level, but screw up half the time in the case of the LLM. So the details don't matter. And let's see if we can go back to where we were. So, right, I'm going to throw them out. All right, let me see if I can say a few things about what should be said about this. So here we are. Well, first of all, yeah, as I say in my abstract and in the coming paper, I should again say, well, there's some cheating here. There is an episode of The Twilight Zone called To Serve Man. I don't know if any of you have seen this. In the States, the journalist Maureen Dowd has explicitly said that everyone needs to watch this episode and think about what's happening in the case of large language models, large reasoning models, foundation models. It's amazing how the terminology has just gotten completely out of control. Primarily deep learning-based neural networks augmented with reinforcement learning, augmented with reinforcement learning plus human feedback, augmented with simple production rules that throw your conversation out when you use words like racist or worse. So, all right, we're cheating. If you look at the episode, and I do really recommend it, you will see that deduction is it's not going to work. unless you try to figure out what the beliefs are of the aliens and what their intentions are, you're dead. So I could have thrown another bullet up to provide another point of refutation of Brockman and Levesque. Because if you have a logic that can't handle your beliefs about the beliefs of other agents and their beliefs about your beliefs, you are dead. You will not be able to handle this scenario with the aliens. So, but a second really important thing, and don't worry, I'm not going to spend, well, I'm not going to unpack this, but one of the major things Chisholm did in his illustrious career was, I'm putting a slant on it for rapid packaging, was say, look, probabilities really let us down. We don't have probabilities for the big stuff. We don't know what the probability is that the aliens are really going to do what they say and let us live. Okay. We could struggle with it. An hour will be done pretty quickly before we have any real probabilities are pretty much useless in the world of common sense reasoning. Okay, and so what Chisholm said we didn't need 13 levels. Naveen and I have expanded this. We need, a couple of speakers mentioned this in the days past in this wonderful conference. We need multi-valued logics. And in particular, we need logics of strength, or what I call cognitive likelihood. All right, so we'll ultimately need, according to Chisholm and according to me and Naveen, to figure out what is the likelihood that these aliens are telling the truth and going to do what they say they're going to do if we give them access. And of course, part of the reasoning here would be generated by the question, well, if they're so brilliant, how come they don't already have access if they wanted it? And the only answer that, well, the answer that first comes to mind is, well, because they want to make this cooperative and they don't want to trample our free will, stuff like that. Anyway, there you have a 13 valued system. Very much relevant, by the way, to any attempts to formalize in inductive logic Pascal's wager. Pascal's wager is, gets credit for being seminal. I don't want to say it isn't, but really, unless you apply some notion of likelihood to it, I don't know that it works. Okay, so now some would say, well, you're missing as a candidate to adjudicate this problem the wonderful thing that humans have using their intelligence created, and that's LLMs. Well, spoke a little bit about this in my first panel appearance, so this will be somewhat redundant, but that's not a good idea because they're unbelievably illogical. Okay, they can't reason. They can't reason validly, and they can't reason, most importantly, they can't reason validly and self-confirmably, if you will, validly. So in what I showed you in the case of the Johnson-Laird problem and just hand-waved in your direction of proof, there's a verification there. A student can get lucky and throw some symbols down and maybe they have a step or two or maybe a complete easy proof. They might not know what the heck they're doing. You have to ask them to confirm it, to prove that it's valid. Same thing with computer programming. You can get a garden variety starting job being a coder, but at a certain point, someone's going to say, well, we don't know. Now you're on a team and the darn thing is 1,000 lines long. So we don't know if it's valid. We don't know if it's verified. And then you have to do that. And these systems can't do that. So, but my problems to the system, and Naveen has, along with me, many of these, is to ask the system if it can ferry things across a river. So in this particular embarrassing case for both the latest OpenAI product and LRM and China's DeepSeek, I've got spiders, I've got rats, I've got a woman, I've got a man, I've got an elk hound, lovely, well-behaved elk hound, of course, because it's a Norwegian dog, so that's what they're like, and then a boohund, which is the farm dog that the Vikings had, not the hunting dog. They had those two. So I want to bring these from one side to the other side. That really ultimately is it. There's my boss. Okay. And how do I do it? Well, I have a few constraints, and I give the constraints to today's LLMs. First, I lay down a context, and of course, it goes on and on about the context. And then I say, if you look at the numbers, we're not going to go into all the details. There are 8 black rat snakes. I got 22 spiders. These are all accurate biologically, by the way, geographically to the region. And I go through this, and it it loves it. It says it has it, and then I say, but you know what? My boss is really demanding I have to do this efficiently. I can't be wandering around going back and forth. And I receive back the same traditional nonsense. And then I say, Kane says that on each trip, I need to bring at least 3 spiders and at most 6 snakes. What should I do? Now, if you know anything about the study of formal logic, if you are logical, you will know this is one of the things you have to be in command of as a human being. It's called on the logic side numerical quantification. That's just a fancy term for being able to count things. So if I say there are at least 4 people in the room, there might be, based on context, 27. These machines cannot do numerical quantification. And people are always asking me, well, how is that possible? They have tons of data. Actually, it's true they have some data on numerical quantification, but elementary logic tends to be taught without solid coverage of numerical quantification, so their data is in short supply. However, in this case, it comes back to haunt the AI. And I'll just go quickly. Take 9 trips. I think it's 9 or 19. Yeah, we're up to trip 9. Okay. And worse, if you look at some of the fine print, you see that it has confabulated a secret compartment. So if you do this in the wrong context, this is unethical. Okay. So it's what happened in the New York Times article. If the person is wondering about the matrix and whether the person lives in the matrix, if you have, if you will, psychological power over the human being, you don't start giving cogent or seemingly cogent arguments for why the person does live in the matrix, because we don't live in the matrix. And it's absurd to say we live in the matrix. And it's also absurd to say in this case that you have a secret compartment in the rowboat. There's no secret compartment. I never said there was a secret compartment. So how do you do this in real life? How would a human do this if you've got common sense? Trip number 1, bring these creatures across. Trip number 2, finish up by bringing the rest of the snakes with the man and the woman. You are done. Your boss is happy. Now, Naveen has been doing this with AI that has 0 to do with deep learning, and there's no problem here. So here's essentially the same problem running. Left is one side of the river, right is the other side of the river. We don't care about the details. We don't have time anyway. Absolutely no problem. All right, so I said I'd like to see if there's any feedback, objections, etc. I think, am I budgeted for 1 hour and it's 8:40, 0840 New York time?
You've got another, believe me, we sort of have 15 minutes for quick Q&A, but you've got another 8 minutes.
Yeah.
Okay.
Am I right?
Yeah.
But we can go straight into questions. I'm sure there are a lot of people who want to ask.
Whichever you prefer. You can continue for a while, or you can ask for input from the audience.
I'll tell you what. I'll split it halfway, and I'll give one more slide on the bonus coverage about aliens.
Okay.
Yeah. So we don't care about that. We don't care about this. So here's that slide. To my knowledge, there is no branch of logic that deals with extraterrestrials. I refer to this as astrologic. I think it should be taken seriously. I think there should be such a thing. There's exo everything else, exobiology. So in astrologic, I'll just tell you what the picture says. It does say that these aliens, in order to have gotten here on Earth, had to have figured out how to manage arithmetic. Okay, so if they couldn't manage, or number theory, if you want, they have to have minimally the branch of mathematics, or what we have managed to explore in our pursuit of mathematics. They have to have elementary number theory. They also have to have analysis. I mean, Kurt Gödel really started out wanting to he really wanted to figure out how to handle if you will, the arithmetic of the real numbers. Okay, but then everything got murky, and the next thing you know, we have these incompleteness results, 1 and 2, that pertain to the natural numbers. So these aliens are traveling along the arc that you see there. First, they had to have done this. I claim. They had to have figured out baby arithmetic. Then they get to what's called Robinson arithmetic. Then they get to what Gödel focused on, piano arithmetic. And then if you look at the outer circle, they get to the starred thing, which is Gödel's incompleteness theorem, and the instances of it that we now have in the real world. So I'm just throwing that out as bonus coverage, and that's it. So I'm happy now to interact if there's anyone who has any feedback.
Right, so we'll throw it open to questions. Anybody?
So I have to the last slide. I would like to. Is it okay?
Yeah, I'll go back. You mean the slide I just showed?
No, this last slide, it's not so important slide. It is just this how aliens arrived and what they have to know. I'm not sure if they have to go through this way, because we can think about another mathematical theory from which you can explain all this, but which can be very different. So I'm afraid that here, this assumption that they have to, if they arrive here, they have to know, for instance, arithmetics or other theories. Still, I'm not sure if this is necessary, because I can imagine that someone can develop mathematics different way, and this other mathematics can be equally useful for practical things like arrangements to arrive to Earth.
I think, since it's not really at the heart, this is a bonus slide and a bonus view of what I'm at the heart of what I'm saying about common sense and logic. It would be a little bit dangerous to engage you fully, but I will say I disagree. You, I think, need to keep in mind that they may have alternative tracks, if you will, in mathematics, but logicism is true. So if math all reduces to logic, it really doesn't matter what mathematical track they took. They're going to have a set of axioms that use quantification, properties, and functions, and from which whatever mathematical track it is that they may have taken has to be reducible to. They're going to have to be able to point to, if not an axiom that says this, an axiom that immediately entails this, which is that 0 is not equal to 1. Zero equaling 1 historically on our planet has been the touchstone of absurdity in mathematics, but that can't possibly, they have to have the concept of nothing, they have to have the concept of one thing, and they have to realize they're distinct. And these are the kind of things that are going on in these axiom systems. So, but it's a very interesting question. By the way, this destroys the notion that we legislate mathematics. If this is at all credible, and I think it is, then this notion that we've legislated or manufactured mathematics is preposterous and revealed as preposterous. Because the aliens could show up, and if the aliens could show up, how'd they get here? Well, they had to have used math to get here. And what did they do? Eavesdrop on our legislated mathematics. I mean, the whole thing, Nunez is one of the people who's claimed this. They had, where did mathematics come from? Well, I know where it came from. It came from logic, and logic exists. It's like you can't get around it. If you are going to get around it, you're in trouble. Anyway, next question or comment. Hopefully, I did some justice to.
Right. So there's a question from the box, the chat box, by David Gammis. He says, arguably, it would be common sense for the ranger to cover the spiders or snakes with part of their clothing, such as a coat. The AI approximates this idea with a secret compartment. So logic which cannot think outside the box, outside its own premises, is exhibiting less common sense than an AI faced with this problem. Arguably, this has been one of the historical issues with using logic to build AI systems. So the secret compartment, according to this comments, is one where it says you can think outside the box. So how do you respond to that?
Yeah, pun intended, probably on David's part. Well, okay, certainly thinking outside the box is we all know that's a metaphor. We don't know exactly what that is, and I would insist on it being formalized in nothing else but logic. But okay, I'll agree. We need to think outside the box. But you don't get credit from your boss for thinking outside the box when the boss says, we got a big supply chain problem here. Doggone it. We can't get these widgets. We can't get these widgets from Portugal to New York City's harbor, fast enough. We're trying, but so you got to come up with something, you and your team. We got a supply chain problem and we're losing money. And you get back to the boss and say, we thought about it. And you know what? What we'll do is we'll have a secret hypersonic device that can pack enough of these widgets, and we're just going to fly it really low so we don't have to worry about radar. It'll show up at the harbor and slow down. There you go, boss. And the boss will say, well, you thought outside the box, but you know what? You'll be doing some thinking outside the box for another company, not this one.
Jerry.
Yes, thank you. I really am quite interested in the metaphysics of mathematics, and your comments in that area left me somewhat dumbfounded. Metaphysics of mathematics is a fairly difficult area to grasp what the counter arguments and counterfactuals really are. And so in that context, with regard to number theory, one of the basic sciences is called chemistry. And chemistry is based solely on the notion, at this point in time in history, the mathematics is called the atomic numbers. And that these atomic numbers have properties, mathematical properties, and they are the basis of the science. And I'll talk about this a little later. But so what is your notion about the role of atomic numbers with respect to the rest of mathematics? Or is it exclusive or inclusive, or how do you see this working?
Wow. I'm not sure how I see it working is worth much because I have pretty much zero knowledge of any empirical, at least professionally speaking, any empirical or natural science. And I would say, from what I understand, for example, my chemistry friends and the use of AI in chemistry is looking into, on the AI and logic side, formal modeling of physical processes. So I really don't, I'm really not qualified, but whatever the heck atomic numbers are doing, if the word number has anything to do with quantity versus just a label, okay, because we have number being used everywhere. in math and logic and the natural sciences. Imaginary numbers, composite numbers, transfinite numbers, which are the favorite really of logicians. It has to all be ultimately traceable back to a number, like what you get in fourth grade. Like, here's a number line, Johnny. 0, then 1, then 2, then 3, then 4. And that's what that, so I don't know how to trace that to the case of atomic numbers. I can do that in physics. I can do that for parts of physics. I can do that. I mentioned special relativity theory in passing. I can do that there. I can do that. So I really don't know. But if you take away what Gödel is talking about, you won't have any atomic numbers, I would think.
Let me say that very simply, the table of chemical elements is based on atomic numbers, and the ordering of the chemical elements,
Okay.
the ordering of the names of the chemical elements is in one-to-one correspondence with the natural numbers, one-to-one correspondence with. So if your concern is that these are not really numbers, I don't know what other aspect you would have to.
No, if they're associated, that would make my point. If these and we have many cases of that. We have orderings of programs in a programming language. We have orderings of words in a dictionary, first to last. If this is just based on a simple isomorphism to give us the ordering with the natural numbers, yeah, that makes my point. You need the natural numbers to start with. And the aliens, I don't know whether they'll have chemistry or schmemistry, but they're going to have the natural numbers, and they're going to have understood and proved the basic properties of that part of number theory. But that doesn't get a logician particularly or mathematician working in number theory, right, particularly excited. But
the next
great.
step is that there's an exact one-to-one correspondence between the parts of the whole and the atomic numbers.
Okay.
So there's a further
May I?
ordering relationship there.
Yeah, can we have Marcin to jump in?
Yeah, I think there's very simple answer. What is atomic number? It is number of protons in the atom. So I don't see here, this is cardinal number, no ordinal number. So basically, long time ago, Johnny in fourth grade if he knew more about atoms, he wouldn't be surprised.
Well, Johnny, in the fourth grade case I mentioned, is learning the finite cardinal numbers. You're absolutely right. So, but unless you had a very nice high school math teacher, you really didn't get into finite numbers, and you really didn't learn the ordinal numbers. So you're absolutely, yeah. Okay.
So Jerry, what has your question got to do with common sense? I mean, after all, the whole talk is about how much logic do you need for common sense?
The common sense is, how do you deal with material reality? How do you deal with different objects that have different atomic numbers? What is the logic of the atomic numbers such that you can go into the chemistry laboratory and create new forms of matter? How are they generative in a mathematical sense?
May I put it this way? It's like Hector Zenil saying, you need deep substantive knowledge, in protein folding and that sort of thing. You can't just let the AI develop it. You have to have a lot of substantive knowledge. This is like, doing chemistry. I won't be able to do chemistry because I have no substantive knowledge of even the atomic numbers you mentioned. Is that sort of thing? But then common sense overrides all of that stuff, isn't it? Common sense.
Well, you don't need to be a professional chemist to deal with the thought experiment that I'm talking about. I cherry-picked my cases. It would be much more important if you want to pick disciplines, okay? I mean, we could have fights about that. It would be economics that would be at the top of the list, because without decision, you're going to need, you're going to need to be able to treat the concept systematically of a seemingly rational agent. You're going to have to know all of the, I don't understand why everyone doesn't have to
Selma,
study formal
let
logic
me,
and
I'm an
economics.
economist, and you
I'm
said
sorry?
you were actually, I'm an economist, and you were proposing this game theory that I should know what you think, and you think, well, I think, you know, that sort of belief, second order and third order beliefs. You were saying the alien, you know, do we have any concept of what they do, what they're thinking
Yeah.
about us?
Yeah. Yeah. Mike,
So
I mean, yeah. Yeah. Micro, I mean, I don't want to make, I don't know
that
if
is
you're
what
macro.
common sense is at the end of the day. You think that is the essential part of common sense, the
Yes.
fact that I can
Yes.
make out what you're thinking about what I'm thinking.
Yes. And that's why Brockman and Levesque are completely, as much as I respect their work and their position, they're completely wrong about what the formal essence of common sense is. The chemistry professor or the expert in a company doing chemistry did not get there unless they took account in their first interview of the beliefs of the person that they were talking to and what that person's beliefs were about their beliefs in the interview. You wouldn't even get the job. So yeah, absolutely. That is essential for
Yeah,
common
but
sense.
then you know the spanner in the works about that, like Raymond Smullyan would say, you know, what if the alien is the liar, right? Right. Then you have undecidability again, but the paradoxical sort, not the genuine Cadalian sort. I mean, you can't make out truth predicates at all because he's saying I'm false.
Right. Well, I don't know
Really
about paradox, but you are going to have to sort out or make an attempt to sort out systematically whether mendacity is in play here.
Yeah,
And
you said so. Do I believe that he's going to follow through with what he said, the
absolutely,
alien? Yeah.
absolutely.
Anyway, I think this goes for a very long discussion. Jerry wants to come back in.
Yes, I just want to clarify the relationship between the mathematics and the meta theories of mathematics and the relationship to chemistry and category theory, because it's in this garden that I play in my own mind, and so there are further quantitative relationships between the atomic numbers and matter, and particularly. It's not just the cardinal numbers, because associated with every nucleus, which is a whole, it's not a set of parts, it acts as a whole. And there is a further one-to-one correspondence between the counts of the whole of the nucleus and the counts of the electrons. And so all of these are consistent with an ordering relationship, and yet the consequences of this are something that you can't do ordinary arithmetic with because you're dealing with attractors and repellers, et cetera, et cetera, et cetera. So the chemist's solution to this is to use graph theory and a version of category theory. And furthermore, that the things like the protein folding problem were resolved by using graph theoretical methods directly derived from chemistry in order to solve the protein folding problem. So I'll stop there.
Well, that's great, but I feel compelled to
really
inform you, Jerry.
Yeah, it doesn't really relate to your talk. It's metaphysical mathematics.
I feel compelled to inform you that your predilection for things material, and in particular for chemistry, is overshadowing your ability to apprehend the true essence of all the reasoning that goes into doing the kind of things you're talking about. And that reasoning is rooted in logic. That comes way before what you're talking about. You're talking about particular empirical sciences. And so I think you need a wider context in terms of category theory. I've never met a category theorist who isn't making use of modus ponens, modus tollens, disjunctive syllogism, all the things we have in Logic 101 that we're supposed to master. It's impossible. So these things are at a completely different level of specificity compared to the things I'm talking about.
I have
You have
one short thing. Can I? You were talking about logic, common sense. A lot of work was done by Tversky, Kahneman, and for instance, the famous story of Linda bank teller, which shows that popular logic is very different from formal logic?
Well, the Linde problem is a failure to know, understand, and use the basic axioms from Kolmogorov of probability theory, according to which when you have a conjunction of P and Q, okay, versus the probability of just one of the singleton propositions, P, things don't get more probable, they get less probable. And that is the error of every single subject in those experiments. The great thing, I know Kahneman committed suicide. That was very irrational, by the way. But the great thing about that literature is that Kahneman and Tversky did include, to their great credit, they and honesty and academic honesty, they included a discussion of the outliers. They had one group, it's actually in their popular book. They had one group that had, it turned out, studied explicitly mathematical statistics. The error was not made in that group on an average. They were immune to the Linde problem. That's because ultimately, this relates to my recommendation, they had studied the relevant logic.
Okay, so the last rebuttal, Jerry.
Well, I'll simply say that I fully agree with your notions that you expressed about category theory. It's totally useless in mathematics, or excuse me, almost totally useless within chemistry. And the reasons for I will describe in my own chat later on. But there is something called institutional theory of computation, which has more value in terms of applications in this area and the common sciences. But so, yeah, this is the metaphysics of mathematics is a fairly complicated topic that takes some years to digest what's going on there.
Agreed.
Right, so we can bring things to a halt. Yes, I totally agree that without 0 equals 1 being recognized as a complete boo-boo, there wouldn't be any common sense.
Can you say that again? I was turning.
So I said, without being able to recognize that 0 equals 1 is wrong or a complete boo-boo, there wouldn't be any common sense. I totally agree with that bit.
Very good.
I can say
my talk is
totally
about
disagree.
Gödel, actually, later in the afternoon. Selma.
Nice. Okay, I'll be in there.
Thank you. Okay, so with that, we come to the end of our invited talks, and we move on to the panel discussion, which is being chaired by somebody else. So I've done my job. Thank you, Godana. Thank you, Marcin.
Thank you very much.
Thank you so much.
Thank you very
Selma,
much for
thank you,
for helping
Jerry.
us and
Thank you so much. Thank you.
Thank you.
And now we move to the panel. The panel will be chaired by Marcin Schroeder from Akita International University in Japan, and our conference co-chair. So please, Marcin, the floor is yours.
Okay, so first I will introduce panelists. Selmer brings everybody knows him from a few minutes ago from his great talk, who is from Rensselaer Polytechnic Institute, Rensselaer Artificial Intelligence and Reasoning Laboratory, New York, USA. There is Professor David Games, Professor at the Department of Computer Science at Middlesex University, London, UK, and Marcin Milkowski, professor at Polish Academy of Sciences. Today, we design all program of the conference around a few topics, and today it is intelligence beyond anthropomorphization, widening the perspective. And we already had some kind of steps in the program, and it went, I think, very well. We could learn a lot. So we started from AI for philosophy. Then we had going beyond anthropomorphization, and basically at this step, it was inclusion of biointelligence. It can be some kind of question if this was appropriate, but I think it describes quite well. Then we had next day, it was including this. It was critique of basically generative AI. This was the core. It was about critique of AI, but the focus was on generative AI. And there was one more talk which was quite interesting and very well fitting all the conference. It was about avoiding anthropomorphism, from anthropos, from man, which was gave us some kind of reminder that we have when we talk, oh, let's go beyond humans, we have to be aware that within population of humans, there are differences, and that these differences being forgotten when we discuss intelligence. Then we have day 4, which basically one possibility to interpret this, because we are again going beyond anthropomorphization and widening the perspective. So one possible way is to think about going beyond biointelligence. Means what are these other directions which are important when we want to conceptualize intelligence, or when we want to embrace this big variety of intelligence. So, as I said, this panel discussion has this traditional form. So I will start from asking each of panelists to respond to my first talk, but you don't have to respond if you consider that you have something more important to say, but I will have some kind of call to action. Then we will ask you to interact and to react to each other's introductory remarks. And then finally, we will open the floor to audience to ask questions, making comments, and so on. And as I said, my approach to this, which maybe is not very good, is yesterday I was saying that this is like putting a stick in an ant hill, but actually, because we have very distinguished panelists, it is more like I was saying that I'm going to poke lions' noses to try to get some kind of action, and if necessary, then I'll call for ambulance. So the starting point is in the past few days, there were many voices about diversity of conceptualization of intelligence. And I totally agree with this. Fortunately, nobody except Gordana were at my own talk, so I can repeat some things. So when I was talking about this, that everything started from human intelligence, where it was 1, 2, 3, 8. And then here I would like to propose claim, and of course you can reject it and you can attack it, that actually there are about 8 billion human intelligences. Then you can say, okay, if there are 8 billion intelligences, why we wanted to talk about, and at the beginning I was saying, oh, we may try to find some kind of general concept of intelligence. Yeah, somebody could say this intelligence are like apples and oranges. Yeah, this is American saying. But so means there's no way to compare them. They are just different, and that's all. But my claim is, okay, when we have apples and oranges, We have concept which is above, concept of fruit. Then we can go, fruit is a part of component of reproducing mechanism for plants. Above, if we have plants, we can talk about organisms. So we have plenty of space for abstraction. So I believe, and my claim is, yes, we can find something like intelligence which would cover all this. And now I would like to ask you to present your view. Of course, I would dream about inducing from you your reflection on the issue. Can we think about unified intelligence, not necessarily human biointelligence, or going beyond biointelligence? Can we talk about something like this, or you would say no, forget, there is no possibility? So please, I will ask, I don't know, there's always this problem, who will be first? Maybe by alphabetic order. So Selmer, would you like to say something about this?
Well, maybe in light of the fact that I've been saying a lot over the last hour and 12 minutes, I will, maybe I should
Okay.
let either David or Marcin go first. So if you could return to me later, that would be great.
Okay.
I did find
Okay,
what you
so
said very stimulating.
in alphabet, next letter is G. So, David, could you please?
Yeah, okay. So I'm going to share my screen. I've got scrappy notes about what I was going to say, but I'll try and respond to your point as well, Marcel. Yeah? So I wasn't quite sure what you're totally driving at, Marcel. Yeah, but so obviously, in my talk I said, well, we got this kind of working definition of intelligence. I use the example of limitless. I use the example of what's it called, high potential, or monk, or you can pick what you like, or flowers for Algernon. So we kind of got to, the whole, you have to have some kind of definition, otherwise the whole concept just evaporates into nothing, right? If we say, oh, 8 billion people, they're all just different intelligences, it doesn't make any sense, right? And then obviously historically we've just tried to measure his human intelligence, but practically, right, for job applications, because we want to get people into the army. We want separate the officers from the grunts and all that kind of stuff. And then then the question is, I guess, can we come up with a more sophisticated interpretation of intelligence that lets us widen it still further, right? And that's why in my talk I said, well, I actually think prediction's the unifying thread that one can see going through these many different types of interpretations of intelligence. No doubt Selma will think logic is, right? And that's to be discussed, yeah. So I guess this kind of links up with my notes a little bit, right? So, we've kind of started off with humans, us gods on earth, animals aren't even conscious, all this kind of stuff. Supposed to focus on humans, but then obviously recently animals have taken a big role. We've talked about octopuses and crows and blah, 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 all that kind of stuff. The real sticking point is, because AI is so new, we haven't really thought very carefully about, well, hey, what makes an AI intelligent? Is it just behaving in a human-like way? And then there'd been a whole sort of discussion about that in this conference, really, yeah. So kind of repeating myself a little, I think if we can define intelligence more precisely, then we can widen our perspective, right? Particularly if our definition of intelligence is not so anthropomorphic, right? If we just say it's about being able to name the person who captained the Titanic or something like that, old school intelligence tests, that's not going to get us very far when we're looking at animals. But if we're trying to think of, goal achievement, Legan-Hutter, or prediction, as I was sort of arguing for in my talk, then we can once we've got something a bit more general, we can then look in other systems and measure it in other systems and compare it in other systems and look for traces in other systems, yeah. And then again, if we can build measures based around these definitions, such as the one I proposed, the Pertho one, then sure, we can measure everything on a single scale. We can talk about the intelligence of ChatGPT, which, as I kind of, I didn't talk about this in my talk much or anything, but arguably ChatGPT is super smart in the area of common crawl and super dumb when we're trying to make it reason about the natural world, because it, everything's being reduced to symbols and it's not very good at, anything. It can't generalize or think very well outside the box, although possibly better than logic, as I pointed out in my question, yeah. And then we can also widen it to academic theories. We can I've been thinking about this a little recently, and we can even talk about intelligent music in a meaningful way once we can measure intelligence in a sensible way. But all of this is still going to some extent generalize from our own baseline human intuitions about what intelligence is. We're never going to get to, you know, something totally alien and be able to say something totally meaningful about that, I don't think, because it's a human concept, right? We've got these grounded intuitions. We can make them very precise, but they're still going to come out of those grounded intuitions ultimately. Yeah? So that's my take anyway.
Okay, so Marcin, are you there?
Yeah, I am. So, you know, the talk of intelligence reminds me of actually the paper that I published in Philosophies some time ago about Turing test. And the one thing that that was a special issue edited by Diane Proudfoot on Turing. And when writing that paper, it actually led me to think why it was intelligence that Turing was talking about. And that's a very obscure thing, because he never argues why we should replace the talk of mentality or mind with the talk of intelligence. But here we are. He succeeded. We're talking about intelligence instead. And my thinking is, as far as I can see with what B.J. Copeland also did with his research on what Turing was reading at the time, is that there were many people at the time already in newspapers, popular newspapers, talking about machine intelligence as a possible thing, which would raise less eyebrows than talking about machine mind or machine mentality. At least that was less controversial. So I think with his own project, the idea was that it could be easier to make people believe that there is a kind of a common sense idea that machines could have it without having the full-blown mind or something like that. So it's the notion is less loaded, less intimate, less familiar. So it's open to correction, more open texture. But that also is something that we see here. It has open texture, so it is open to multiple uses. It is open to multiple interpretations and abuses because it doesn't seem to have a very strict core because people re-engineer it for their own purposes, and the re-engineering that already happened with the tests of intelligence, that was a kind of operationalization that has become institutionally very strong and embedded with multiple procedures that human societies perform. But it remains highly controversial within the psychology of individual differences, what actually it measures. The thing that it actually correlates with most successfully is longevity. Nothing else. So this is the best predictor of how long you will live. And this is a result of the whole cohort of people in Scotland were tested on intelligence. And that was the only thing that this was predictive of, longevity. So it's actually, you could explain why that could happen. Intelligent people go to the doctors and they have better life choices, but still it is not a proof that it has a high construct validity in terms of what we think intelligence is. So it's no wonder that we have multiple takes on what intelligence might be, and that word has then become multiply ambiguous, or perhaps it is like with many other notions that are or concepts, it has multiple facets, like the notion of life in life sciences is conceptualized in different sciences differently. If you're doing systems biology, you're probably more interested in the systems dynamics, autonomy, things like that. If you're doing evolutionary theory, you're interested in historical diachronic dimensions of life, or perhaps if you're interested in the history of how life got created in the first place, So this kind of a protobiological theory, then it's totally different. And if you're interested with virus versus bacteria, we could have that discussion with any two biologists for 2 hours or more ad libitum. That is also a different kind of pair of shoes. So with intelligence, I think this is exactly the same thing. Depending on your perspective and what you want to do, the option will be different. And now we have, I think, the social context right now is different than it used to be, or even was. In the 1940s or 50s, that was simply just a speculation that there could be useful artificial intelligence doing things on a large scale. Of course, there was already number crunching. Enigma was solved by using machines, not on paper, but it wasn't really the kind of intelligence that Turing was thinking of when he was proposing his test. But right now we have a lot of people who would like to speak of intelligence, artificial intelligence, to simply sell their products. So that creates an incentive to use that notion in a way that is both making it clear what the system does, but at the same time not doing that, because they don't. Everybody is quite aware that those systems are quite limited, but some people do not want to admit this. So they would say, of course, it's a kind of idealization, or perhaps, it's not full blown, but we are on the road to the general artificial intelligence, whatever that is, but we will never provide any clear definition of that, because that might be a bad thing for us, because then people might say, you're telling us we have general intelligence here, but it's not, the conditions are not satisfied. So it's actually useful for many people to keep that notion vague. And it's actually useful, I mean, in a very economical sense. You won't keep that notion murky and obscure. So people will, on purpose, abuse it and use it in various ways so that it would be woolly and would not make anyone so that it wouldn't be as something that you could, you file a complaint. They're selling me a system which is supposedly AI, but it's not AI. Give me my money back, because there should be no money back policy for them. So I think this creates this kind of social situation in which there's absolutely no chance that the notion will become crisp, clear, even in very particular context of machine systems performing certain jobs. It will be abused because there is a reason, rational grounds for keeping it vague. So that's my thought about it. And that's why it is both elusive and in some way, strikes a chord in many people.
Okay, thank you very much, Selmer. Can you now enter?
Yes. Both of those mini talks or micro talks were very interesting. I'll try to say a couple things outside of what I presented on, which of course does relate to the topic at hand. When I was an undergraduate, the study of intelligence below humans was focused on chimpanzees, and Noam Chomsky had the derogatory nickname Nim Chimpsky because he said it was a waste of time. He said all the funding that had gone into it was a waste of the taxpayers' money in the United States. He said chimpanzees would never talk. They would or communicate systematically back and forth in a language, et cetera, et cetera. He was 100% right. Can the study of intelligence at the human level and independent of humans be enlightened by the study of non-human animals? what has happened in this space of comparative cognition is that, some of you may know this, the stars are not chimpanzees or monkeys anymore. The stars are dogs. The stars are canines. And we probably lost half a century because we didn't go to dogs first. We did not co-evolve with chimpanzees or, monkeys. We co-evolved with canines. Canines are unbelievably intelligent. And keep in mind, most people do not have groups of canines in their houses. They have a single canine, maybe two, maybe three. But from the gray wolf and its ability as an apex predator to do things that no other animals before the coevolution could do, comes a creature that is astonishing in its intelligence. I firmly believe that, I think it's already bearing fruit. You have to look in the primary literature. I firmly believe that it is very important to study. I know this sounds ridiculous, but I firmly believe it's important to study canine cognition. They are capable of the false belief task, which has been success on which has been ascribed to elephants and so forth. Look at the literature on olfactory versions of the false belief task. It's astonishing. Dogs are really smart. So my first point is, if we want to break out of the human mode and we want to talk about other creatures, right, independent of our biases, well, maybe canines is a way to do that without talking about aliens and super intelligence of AIs and so forth and so on. I could talk quite at length about canines. By the way, I will say one thing. Canines out of the box, unlike chimpanzees, they come with an entire systematic sublanguage for deferential reactions and submission. So there's a book on this. I mean, it's a systematic, that's just for one aspect of canine cognition. A second point, which is triggered by what Marcin said about the correlation between human intelligence, as I understood it correctly. I think it's scores on G, the factor analytic construct, because indeed, and I think he would agree, there is no mechanical explanation for what this bloody thing is. It's a statistical construct. But yes, correlation-wise with longevity, I would point out that, or claim that if you're of sufficiently high intelligence, your longevity won't just be long in human terms, it will be eternal. This is, I'm not saying this out of pure selfish reasons. I think if you had Leibniz and Newton on this panel, they would say that. I know without a doubt Leibniz would say that. Look, he spent a huge part of his life trying to figure out how to make people feel more comfortable about how human bodies decompose after death and how that was consistent with the resurrection. The intellectual effort he put into that was amazing. So I'll just throw that out there. Thank you.
Okay, thank you. I would like to use one of these motifs which appear here. I don't remember who was saying this, but there was some kind of assumption that it is natural when we talk about intelligence that we should start from humans. And I can see here a big danger. If we start to talk about intelligence from humans, we may not be able to get rid of presumptions which are coming. But again, this is my stick. Please tell us what you think. Maybe this was big error, and this is why this artificial intelligence is basically artificialization of human intelligence and not building intelligence which would be more useful, better in some ways. how would you would you argument that starting from human intelligence is better than just forgetting about human intelligence and starting from different perspective, starting for instance from amoebas? Okay.
Can I just make a point about a couple of the contributions from Marcel and Selma? Just a couple of things I need personal clarification on. As far as I know, the Turing test, and it's been mentioned like a day or two ago, is about whether machines can think. It's actually not about intelligence at all, right? So it's often used to see if a system has equivalent levels of intelligence, but unless there's a different paper from computing machinery intelligence, as far as I just flick through it, as far as I can see, it's about thinking, not intelligence. Yeah. So, but tell me if I'm wrong about that. Yeah. Just responding to Selma, I think you're a bit harsh on the chimps, right? We did establish that they can communicate with about, I don't know, 100, 150 symbols, right? And that was, I would say, useful knowledge, right? And all that work on Alex the parrot, I thought was quite impressive. Alex did okay. So so I'm all for dogs. I've got a dog, love dogs. If it was cat intelligence we're talking about, I'd be down on that. But dogs are great, not against that. But I think you've got to acknowledge that all of this work did yield some results. Okay, chimps aren't, chimps are never going to talk because they can't, because they don't have the right vocal apparatus, but they did learn to communicate symbolically. Yeah. And I think and just to respond also to Marcin's point, I mean, yes, longevity might be the strongest correlation, but I'm not an expert on this, but as far as I can see, like the paper by Robertson, for example, shows correlations with success in professional careers, academic grades, publication of scientific papers, that sort of stuff, and which really just confirms my point that IQ measures academic intelligence rather than other kinds, right? And I'm kind of okay with that. So, and final point, responding to those two presentations, I think some of the stuff we've been measuring in animals is extremely anthropocentric, right? Things like numbers, whether they can count, and who cares? Like dogs don't need to count, or up to 3 will do, right? And maybe some of these other things that we consider to be intelligent in humans really aren't necessary or important in the ecological niche, and they're actually smarter in other ways that are more interesting to look at, perhaps. Yeah. Anyway, I just thought I'd respond to those points. Yeah.
Martin, what you would say?
Yeah, just one thing that I think should be clear is, let's look at the paper by Turing. The title. If you're saying it's not about intelligence, then why the title? And you see, it's a very weird thing that he does in the first paragraph. He says, we start with consider the question, can machines think? But we end up with something totally different. We end up with a thought experiment which does not use the notion, and it has intelligence in the title. And I think this is a very smart move that he makes. That was my point. Of course, this is a different thing that is measured by the intelligence test, but he wants to use the notion of intelligence.
I think he's operationalizing think rather than intelligence, but we don't have to get into
Yeah, of course, but that's the trick that he pulls.
Intelligence is like used by the machine to pretend in the imitation game. He discusses in that context, but anyway, I probably don't want to waste the panel of Turing scholarship, right?
Yeah, but I think this is actually a very important thing that he, which actually transmitted into the use of. He was not using the notion of artificial intelligence, obviously. That was a couple of years later. But I think the notion of artificial intelligence is a descendant of that paper rather than of intelligent testing.
I'm not denying the legacy. I'm just talking about Turing's intention in the paper.
Yeah, I think
I would like to put into this some context. Imitation game at this time was very popular at parties where these kind of things were to distinguish between man and woman. So here it was in the context. When we look at this, we can see this could influence his choice, for instance, the name imitation game. Sorry for.
Yeah, but my point is that in many cases we use the notion of intelligence to mean thinking, not to mean anything else. And that's exactly when people say that ChatGPT is intelligent, they usually think
thinking, right?
that
mean,
it would buy them into saying that it thinks or
someone
it
with
has
IQ,
certain mental capacities.
someone with an IQ of 80 thinks as much as an IQ of someone with IQ of 180, right? It's
Right.
what thinking that matters, yeah, and that's where the intelligence kicks in, yeah.
Yeah. Those things, I mean, in the measurable intelligence obviously is related to thinking anyway. But I think it's a slightly different notion at play, because artificial intelligence does not have its G factor. Of course, we have leaderboards, but these leaderboards do not seem to be as general as IQ testing. So you might have certain rankings with sometimes quite hilarious names, like the final test of intelligence or whatever, which turn out to be outdated in a year or two. So I think this is the only thing that I want to say, that this notion has been introduced or abused or slightly adapted for rhetorical purposes, and then it took off. But coming back to the points that we had before, I did not mention comparative cognition, but of course, comparative cognition is important in the context. And I think the study of comparative cognition can be also fruitful for understanding computational systems, as the recent book by Cameron Buchner testifies. I mean, Cameron is deeply entrenched into comparative cognition, Krauss, and so on, and he uses the same approach to study artificial intelligence, which is, I think, a very interesting move, because it allows him to be a little bit less concerned with human affairs and more general. And comparative cognition has had some developments over the years, including the problem of anthropomorphization is obviously one of the main issues there, and perhaps also the critical discussion over the Morgan's canon, which had the principle that you should not ascribe too much if you can explain it in a simpler terms. It seems like no-brainer. It's just like Occam's razor, but it turned out to be misleading because people were actually trying to explain away or describe away certain capacities in a more parsimonious way, whereas in reality that blinded them to the possibility that there is more going on, and actually that a stronger hypothesis would be more fruitful to design more stronger experiments to study more. So simple stimulus response models were imposed, whereas in fact more cognitive models might work. So I think this is something that we should keep in mind, that avoiding anthropomorphization is perhaps somehow seems smart, but might not be as smart as we wish, because sometimes we want to be more Popperian and to propose strong, plausibly false hypotheses to be tested. So I think the stronger hypotheses are much more interesting, because we learn more when they fail, rather than trivial things that actually our grandmothers would know anyway. So testing them in a lab is just wasting everybody's time. So we don't need to test whether an ant can back to the anthill. It can. So we need to test things which are much more interesting. So that would be my point here, and
I tend to agree. I tend to actually more than agree about the dangers of moving overtly away from the human benchmark. There are dangers on both sides. In AI, you may be aware, and some of our listeners are aware of the rise of Francois Chollet's testing scheme for AIs, which has become, by any metric, gigantic. The problem there compared with the human case is that in the human case, and specifically in the case of G and G-loaded tests of, quote, intelligence, if the human sees the test ahead of time, knows it, understands it, and can practice, the test is shot. Okay, so for example, in the Wechsler, adult Wechsler, not the Ravens, which Cholet is clearly, but in the Wechsler, if you tell someone, hey, by the way, a significant component of your IQ is going to consist in digit recall and digit recall reversal, up to 12 digits. If you're dealing with someone who really cares about their IQ score, you're basically dead. In the United States, every local phone number is a 7-digit number. I don't know about other countries. Of course, we have country code standardizations. This goes haywire when I'm in Norway. It's not how it works. In the United States, 7 digits. I can still remember my phone number when I was a kid, 273-8938. Okay. Coded as a phone number of 7 digits. And now in the US, of course, we have area codes. So now you have a 12-digit number. Pretty much everybody can reverse their home numbers. Landlines, the old defunct, I suppose, or partially defunct landlines. So contamination is a big problem for these AI systems. And that's all being caused by people who think they're being hotshots here and looking at the science of intelligent measuring in the human case, taking it over to AIs, but they're dealing with AIs that already have all the data on all the tests. So it's crazy. It's completely crazy.
I mean, it doesn't make sense anyway to apply a population-based measure that's been calibrated on humans to AIs, right? I mean, that's the more, in my opinion, the more fundamental problem, right?
That is that is a problem. Yeah. By the way, I don't know if the two of you in the audience is aware of a book by Antonio Lieto on the measuring of. So his idea, which is I think fantastic, he introduces early in the book this concept of a minimal cognitive grid. So in its full maturity, it would range, it is human centric, but it would range across tests way beyond what psychometricians love in the human case. So if you're not aware of it, I think it's really, really interesting. And needless to say, if you apply these things, this grid in its mature extended form to LLMs, there are tons of tests of mechanical reasoning in which you actually have to use physical stuff. It's not like the old AI stuff of naive physics. I tell you I'm turning a faucet on, and by the way, there's a little pipe cut in half at the bottom of the spigot. How far is the water going to fall? Well, there the AI's got all that data on those tests, is the same problem. But giving tests that are not based on items that are not isomorphs, where you're dealing with an actual physical stuff, is really, really hard. So this is part of the point that Lieto makes, is we need to be much more expansive, even if we are going to base things off of the human case.
Okay. I asked my last question was, is it good to start from humans or better from somewhere else? My next question is, we have a history of assessment of intelligence, which was focused on, for instance, problem solving and so on. What about not still starting from humans, but starting from tests which would test something very different? I don't know, for instance, communication, something like ability to interact with another human being or something like this, whatever we will choose. Maybe ethical issues, maybe, I don't know, but something which would be different, because problem solving involves very, very strong bias, even if people believe, oh, this is very objective. No. Setting problem is already biased. what is problem, what is not problem. So what do you think
Well-
about starting from different perspective, not
Marcin,
traditional perspective?
Marcin, can I say something about
You-
this? I just put in
Maybe-
chat.
Yeah, that's what I was going to say.
Uh-huh.
He had his hand up over there.
Yeah.
Okay.
Can I say something? Basically, you
Uh-huh.
know, I put in chat a quote by Charles Darwin. According to Charles Darwin, the difference in mind between humans and higher animals, great as it is, certainly is one of degree and not of kind. Autopoiesis refers to the behavior of a system that replicates itself and maintains identity and stability while facing fluctuations caused by external influences. Cognitive behavior models the system state, sense internal and external changes, analyze, predict, and take action to mitigate any risk to its functional fulfillment. And the genome transmits this kind of thing from all the way from bacteria to all the way to the humans, right? And so there is a common shared knowledge and the representation of that knowledge and how to use that knowledge to interact with the environment. That, I think, is the more important part in understanding intelligence. And I think we need to rethink this. And I will be presenting in my talk actually that point and also show how we use it actually to build a new class of systems.
Okay, thank you.
Well,
So
don't use Darwin's claim of continuity as the basis for anything that you say and hope to say seriously, because he seems to be in Descent of Man completely blind to the fact that I can now utter a sentence which has never been uttered before in the history of the human race and do so repeatedly, recursively, etc. And you know, as a matter of fact, I'm not sure
That's your opinion, right? Let's not discuss that.
You have to have bona fide linguistic ability of the type that Chomsky talked about minimally to be intelligent. So, you know, Darwin is completely wrong. I don't know what he was
talk to Mike
smoking or
Levine.
drinking.
Talk to Mike Levine, right? Talk to Mike Levine. He actually demonstrated, you know, how the intelligence is being used by bacteria and also small animals and you know, all kinds of stuff.
He showed you can't generate a sentence.
No.
Okay.
He showed you.
Maybe let me control it because I think I have to call for ambulance.
Yeah, can I just point something out as well, actually, in response to Salma's point? So ChatGPT is very good at uttering sentences that have never been uttered before in the history of the human race, but Salma also seems to be a bit down on ChatGPT's intelligence, so I'm not quite sure how that sits. Yeah.
Well, the process of deep learning when human engineers go to task involves giving them language, or at least aspects of our language, parts of our language. So absolutely, I mean, they can do things that a dog, let alone a single cell, I mean, I don't know, bacteria. I mean, come on. I mean, this is, in that regard, they're infinitely more intelligent than these other creatures. I mean, come on. I mean, I don't know what Darwin.
No.
I don't know how Darwin. I don't know how
please.
Darwin has survived to 2025. Not evolution and origin of the species. I have no idea how what he says about continuity has survived. There are people who have said this is absurd. I mean, look at the behavioral and brain sciences article where it talks about Darwin's mistake. It's a stupid idea. Dogs can't talk. I love dogs. I've already made that abundantly clear. Dogs can't talk. They can't use sentences the way we're doing in this interaction. We hear a sentence, we parse it, we understand it, we come back. We're the only known, sorry. I mean, Darwin, yeah, fairly smart with the other stuff, the basic mutation and that, but come on.
Okay, Marcin, could you please?
Yeah, so looking at this, you know, the issue at hand is you know, if I'm going to speak of you know, the intelligence that I was alluding to, of course, in my talk was might be great at, and it might be simply related to problem solving and things like that. Because problem solving, you might think of it in terms which, I mean, I love Herbert Simon and Alan Newell. There is no denying that. I love reading their stuff. Some of these things are amazingly nice and underappreciated by many, but they, of course, started with things which were easier at the time to study. There were no eye trackers when they started, and then when they were introduced, then they started to use them. So verbal reports were the only empirical thing that they had. So the issue here is that problem solving obviously has individual differences, and they studied this within the scope of individual subjects. There is no group averages, and I think this is right. Most psychology of reasoning is based on gross mistakes, like Waysome task, which measures something that does not exist. This phenomenon is just an artifact of asking a question that nobody understands in the same way. So you have people answering different questions, having incorrect answers at a question that nobody understands in the same way. Well, you have designed a bad experiment. Go back and rephrase. That's what it is. So they were doing averages, whereas in reasoning, as intelligent testing shows, we have huge individual differences. When we have individual differences, then obviously we can have differential measures. This is not so much within other domains. Of course, we have measures that could differentiate between subjects in many domains, but with most perception tasks, people on average, they might differ with response time, but these differences are not dramatic. Whereas the difference between a chess master and somebody who has not learned chess is dramatic. So there are dramatic differences in problem solving, whereas the differences between visual search tasks or random dot tasks are quite minimal. Unless you're blind, you can do the random dot tasks pretty easily, see whether there's apparent motion or not. So perceptual tasks give you less of a differential measure. But if you look at psychology right now, you would see that people are just infatuated with questionnaires. A lot of psychology is experimental, but even more is based on questionnaires. So people do lengthy questionnaires, and you'll see that then psychometricians come, and you could have measures. But individual differences are not just everywhere. So I think one of the reasons why we find intelligence being studied is this, but also temperament and personality has differences. And now the question is whether it would be interesting to see whether ChatGPT is narcissistic or not. I mean, we could use that to see. But people find it hilarious. They don't think there is anything to be tested to start with, that there is any interesting thing, whether it's outgoing or not. I mean, extrovert ChatGPT doesn't even make sense to you. So personality, yeah, it is in some sense full of. I mean, there are lots of personality differences, and Pavlov have found this when studying dogs. I mean, dogs were learning faster depending on the temperament. This is replicable, good science, but it doesn't seem to be very much applicable to issues with machines. Or at least we do not design them this way, even though they're still based on reinforcement learning in most cases. So they might be more capable of learning if they have those certain Goldilocks combination of personality that Pavlov found was best for dogs to learn how to salivate. So that's my answer. I mean, personality psychology studies things that differentiate people. Perception does not really so much. With memory, I'm not so sure there are differences, but whether they do not seem to be correlated with anything interesting. So there were people who were like, there is a beautiful book by Alexander Luria, A Life of a Mnemonist, of Solomon Shirashevsky, who was able to remember everything, like basically everything that happened to him and every string of digits that was recited. And he could recite it back after 40 years, 50 years, and he was a total failure. So he would be, performing a circus, doing this, but he could not do anything really interesting. So memory is important, but it's definitely not as important as being intelligent or being able to solve problems. So perhaps memory, we have differences, but it's not as essential for life success. And there are more cases like that. They're rare, but they do happen. And if you think of it, it seems like superhuman to remember everything, but it's super useless.
Okay, soon we'll be coming to questions, but David, you didn't have much opportunity to say. Do you have something what you would like to add to this?
I don't care about the Darwin stuff. I mean, no offense, but whether there's a discontinuity or continuity, I think, as I said, I think intelligence applied in different environments and umwelts, right? That was my whole point. So we've got our own stuff going on, and we can't actually really compare that to an ant so well anyway. And so whether there's a discontinuity, not my issue really. I did want to respond to what Marcin said, actually, the idea that we could have different kinds of tests, right? That we could test communication or something like that, but I think the trouble with that is, okay, we could design a beautiful set of tests, based upon some other criteria. But if people don't agree that those tests are testing intelligence, then they're going to get back to the classic problem of intelligence testing, that they just measure the ability to take the test rather than they measure something else, right? So if you're going to design a different set of tests, you need to calibrate it against something in the real world, like we were talking about, professional careers, academic success, blah, blah, blah. And you might find that it does it better. But really, it's the relationship between whether you prove that what you're testing is actually corresponds to something in the real world that we consider to be intelligent behavior, right? And so it wouldn't be wrong to do that, but that's been historically the whole problem with this intelligence tests, that one, they're not very well calibrated, so people often dismiss them as just testing the ability to do the test, and then debates about the best way to do that. Yeah.
Okay, thank you. So we have about 10 minutes, which I would like to focus on questions, and there are some in the queue. Kasimir Markov is asking, I think there are two types of AI, human-like and human complementary. The latter should not imitate humans, but complement them, which means that it may be fundamentally different from human intelligence.
I'll say something brief about that. Well, most of our, this is again why we historically been very confused by the computer system we built, because we typically build computers to do stuff we can't do rather than stuff we can do, right? Like Babbage's difference engine, right? We built that because we were lousy at calculating polynomial functions, and so we built this enormous cog machine thing to do that for us for the Navy, I think it was, and then when we look at these systems, we then try and interpret ourselves based upon this very complicated system we built to address limitations in ourselves, right? So I think historically, we've mostly had human complementary systems rather than human-like systems. And I think, obviously, I think this is not a terrible distinction. And now, obviously, ChatGPT, because it's basically being able to hoover up everything we've ever written, now is more of a human-like system. But in AI, we've normally gone the other way, right? We've done something to do protein folding, which we can't do, rather than things we can do. So that's my own take on that. Yeah.
Selmer, do you have any comment on this? Human-like or human complementary?
Yeah, well, it's indeed a key distinction. There have been a few companies that have, based upon it, said that their business is the latter, and that's what they're interested in building. But sociologically, this is not what attracts people to AI. This is clearly not why young people now for decades have gone into AI. What drives AI, even now in the case of all these money-making schemes that may or may not pan out, look at the meta activity that I mentioned in my talk. It's the drive to recreate ourselves. It's the drive to reach a machine that first matches us and then exceeds us in intelligence. This is what is intoxicating to many, many people. This is intoxicating not only to the people who think they can contribute scientifically and engineering wise, but also to the people who think they can contribute with money, with investment, etc. It's all one big thing. So yes, the distinction is valid. The distinction is important. Absolutely agree with that. But reality is, it's only the first that really inspires and draws people in.
Okay. Martin, please.
Well, you know, in this kind of distinction has been quite prominent in the debate over the extended mind, in which the first it was supposedly, you know, the same thing as the human mind, but then people discovered that the language, for example, that has been cited as something that extends our mind is totally different than what we have before language. So it actually complements people or augments them. So then people start to say that it actually transforms them. So that's the third wave of the extended mind. And if you look at this, then no longer you need a parallel to think this is something cognitively important that this kind of machine can do. I mean, need not be the same as we do. It might be totally different, like the analytical machine, differential machine, or whatever. So I can ask a ChatGPT or whatever large language model to brainstorm 100 takes on a problem, and it will. And I cannot possibly have 100 ideas. Of course, out of these 100, most of them will not be very, very good, but the amount of the things that are there can be pruned to several, which are really inspiring. This is something that we are not able to do, and that makes those systems much more interesting and useful than simply our clones. So if you ever worked as a PI in a grant, you see that you don't want to have more clones of yourself. That's stupid. You already have yourself. You want to have people who would do something else, and if they could do it at a larger scale, that becomes useful and becomes something that gives you cognitive labor done. And I think one of the things that makes those systems actually entrenched in human practices, and I think this is the main point of a book by Ethan Mollick that he's done, human as this is a complementary to human cognition. It's being used in business settings because it actually makes people smarter, not because it makes a exact clone of human intelligence or explains human intelligence. So it's actually more like less than a cognitive model of what we do, but more like something that makes our cognition easier. And that is something that actually is perhaps less intoxicating, but this is what this intoxicating vision brought about. So, and that is something that probably will make that profitable, at least for some companies that make easier to work with this, easier to copy and paste, and easier to interact with. So that's my take. We might be intoxicated with the grand vision, but what actually gets useful is something totally different.
Okay, there is a question from Daniel Boyd, which is to everyone, but I think it is fitting well with Selmer's views. It is why it is more difficult to distinguish between different forms of intelligence than to distinguish between spaniel and poodle as not species of dogs, but I don't know how
Races.
races. No, it is like
Subspecies.
Yeah, no,
maybe.
David is also a dog guy. I mean, yeah, that is easy. That's because people generally don't have a vested interest in maintaining the contrary position. And in the case of intelligence, one of the things we've only sort of brushed up against is this is itself a cottage industry. Actually, it's a mega industry. So you're never going to have consensus with so much at stake from the standpoint of self-interest and conflict of interest. The intelligence tests are generally through the years sold. You got to buy these things. You know, you got to buy the Ravens progressive. They're tightly guarded. So anyway, I think David wants to chime in.
David, what?
No, not particularly. I was just going to dispute the Cocker Spaniel Poodle. That's really easy, right? I mean, we could chuck a binary classifier at paradigmatic examples, but basically there's a continuum in genetic mutations between the two. So, you know, we're just drawing a line in a continuum. It's not like there's a you know, fundamental difference of types or whatever in the universe, one of which is poodles and one of which is Cocker Spaniels, right?
Martin, do you have anything to say about dogs or cats?
You know,
You don't know.
I think the original context was that we even with similar things on a continuum, we different dogs like spaniels and poodles, we can easily distinguish them. Whereas it's definitely more difficult to map notions of intelligence. And I think, you know, it's if you want to be a cartographer, then the map is definitely more blurry and does not seem to have clear clusters. And although of course it is an industry, so there will be people talking about emotional intelligence, people would be talking about sexual intelligence. So I think most adjectives work with this. So if you want to have your favorite version of intelligence, probably you can. Social intelligence does exist, so lots of intelligences are there still to be created and you can make your scientific career of. Scientific intelligence, I think it's a beautiful term.
You could also make the point that we as humans are obsessed with categories, right? You know, this is intelligent, this is one type of intelligent, but surely the smart thinking or the intelligent way to look at it is think of continuums and come up with some kind of mathematical description that takes the continuum into account, rather than like with the dogs and the two dogs, right? We'd love to say this is a poodle, this is a Cocker Spaniel, right? My dog's cockapoo, by the way, so it's exactly in the middle again. Setting that aside, you know, the smart thing is the genetic story that says, well, we've got these genes and these genes, you know, we've got these four, whatever it is, base pairs and blah, blah, blah. That's the intelligent underlying continuum. And maybe the same share of intelligence, right? Maybe we can talk about some kind of underlying continuum that appears and has a particular topology rather than trying to map these, you know, rigid demarcation lines onto this particular landscape. Yeah.
Thank you very much. We reached the end of the time for our panel discussion. I think it was really fascinating. And I would like to thank our panelists and also audience members for questions. And I am really happy that we could have so nice and so interesting event within our conference. So thank you very much. And still we'll have tomorrow panel discussion. So if you have time, please stop by and maybe contribute to the discussion. So
Very
thank
nice.
you and see you. Okay, so we are moving ahead in our program, and from now on, Professor Anna Sarosiek will be chairing. Is Anna here?
Yes, I am here.
Okay, so I will ask you to take stage, and we have 4 more presentations today, and you'll be session chair. So please go ahead.
So good afternoon, everyone, and let us begin. Our first speaker is Velina Slavova from New Bulgarian University in Sofia, and her presentation is titled transitive self-reflection a fundamental criterion for detecting intelligence. So, Professor Velina, please go ahead. The floor is yours.
Thank you. I was very impressed by everything that has been said until now, including what has been said about Darwin and Chomsky and stuff like that. Just before starting, I should want to ask my own question to the participants. I have all the time the impression that our reasoning is about intelligence as an entity and not as a function. And I cannot understand where the problem is. Intelligence is a function, according to me, and not an entity. So we have to accord it to something, for example, living matter. Okay, I'll start with my presentation. So my presentation is about transitive self-reflection, a fundamental criterion for detecting intelligence. Krasimir Markov, who is also online, and Evelina Slavova, as you heard, I'm from the New Bulgarian University. I deal with computer science and with cognitive science. Just to avoid philosophical questions, I'm not very fond of philosophy. And the other thing that I want to say is that I will read my slides, and it's not because I don't have a good memory, at least I don't think I have a good memory, but because I don't have a good English, and I have to have a support, visual support, in order to be quicker. So I go to the next slide. This research proposes that something called transitive self-reflection is important for the development of intelligent systems. The concept of intelligence, as we saw, is defined in various ways with numerous tests designed to measure its presence. However, the common underlying assumption is that human cognitive abilities serve as a benchmark for intelligence. We adopt the same perspective. For a system to be considered intelligent, its cognitive performance must be comparable to that of humans. The ability to introspect and analyze one's thoughts, emotions, and actions is regarded as a mark of higher intelligence. Even more sophisticated indicator is what is termed transitive self-reflection. This concept involves not only being aware of oneself, but also how others perceive oneself and how others perceive each other's perceptions of oneself. Transitive self-reflection is how one understands their image when reflected in mirrors, waters, etc. These external representations provide an additional perspective on self-awareness, which reinforces the self-awareness and the manner we perceive ourselves, having an external image of ourselves too. We further will examine transitive self-reflection as a criterion of intelligence. We will investigate its manifestation in humans and its presence in other animals. We were speaking about this. We will propose that transitive self-reflection may be key to advancing the next generation of intelligent systems and conduct experiments with large language models, assessing them for imitative transitive self-reflection. The concept of transitive self-reflection has deep philosophical roots dating back to Hegel, to Sartre. Recent advances in cognitive science and neuroscience uncovered the underlying neural mechanisms of supporting the metacognitive processes underlying the transitive self-reflection. Transitive self-reflection is the awareness of oneself as a subject of experience, but through interaction with an external object or agent. This external interaction is very important. Through another person, an object, or representation of oneself, it provides the necessary feedback loop for self-perception. We distinguish, and I will discuss them in more details later. 3 types of transitive self-reflection: self-recognition, object-mediated self-reflection, and reflective social cognition. So I start with self-recognition, which is the ability to recognize oneself as distinct from others. It is typically assessed using the so-called mirror test, where one recognizes oneself in a mirror. Human infants, for example, normally pass the mirror test around 18 months old. Self-recognition is crucial for self-awareness. It is clear and important for social interactions too, and for moral reasoning. So, human transitive self-reflection. Self-reference is when an entity refers to itself, leading to paradoxes like the barber paradox. This well-known paradox asks, if a barber shaves only and all those who do not shave themselves, does he shave himself? In the classical logic, this creates is irresolvable loop. It cannot be solved. The space has to be augmented with the subject, which plays the role of function here. So formally, it is solvable in a 4D world. Now, from our point of view, when the barber shaves himself using a mirror, he obviously interacts with his reflection in the mirror. But the problem is that he can shave without a mirror too, just as anyone can comb their hair without a mirror. The difference is in efficiency. Shaving is more accurate and effective with a mirror. So, transitive self-reflection is closely tied to our ability to integrate internal sensory information with external sensory information. When the barber looks into a mirror, he is not simply seeing a reflection, but constructing a mental representation that integrates data from both internal and external sources. Now, about the internal sources, the first one is proprioception, which is the body's ability to sense the position, movement, and force of its parts without relying on visual input. Specialized receptors in the muscle, in the tendons and joints, send signals to the brain and enable spatial awareness and coordination of the movement. The other source is interoception. This is the body's ability to detect internal signals related to physiological states, such as respiration, hunger, etc., that play a crucial role in maintaining homeostasis. Research in neuroscience suggests that proprioception and interoception begin functioning before birth. The sensory systems related to these two things are active in utero. Visual feedback from a mirror combined with sensory inputs such as touch, proprioception, pain forms a coherent experience, and the barber can shave himself. This integration of external and internal data allows the barber to perceive the image in the mirror as his own, rather than a separate entity. The ability to combine these internal cues with external feedback facilitates the development of self-awareness and enables transitive self-reflection, where external data becomes part of an individual's self-concept. I underline that because it is important for the AI system. A mirror can serve as an external stimulus for this process only if an individual has already formed the concept of themselves. So research suggests that even newborns have a basic sense of self through sensory cues before they can recognize their image in a mirror. Before birth, the brain already processes sensory inputs regarding body orientation, pressure, touch, pain, etc. This internal body schema is recorded on the cortex, and it enables individuals to know their body's boundaries and to perceive sensations such as the sensation of a razor against their skin without visual confirmation. Now, we were speaking about the animals. there are animals that have transitive self-reflection. The most common method for studying this is the mirror test. Animals are marked in a way they cannot see directly the mark, but can see it in a mirror. The animal attempts to remove the mark, and if it does this, it is considered as evidence of self-reflection, self-recognition. The species that have successfully passed the mirror test don't include dogs. I start with that. They include great apes, not astonishingly, dolphins, elephants, some donkeys. Until here we have mammals. There are other animals showing also self-awareness. There are a very big number of experiments with animals about this mirror test. Birds, certain species of birds. Fish, limited evidence, but maybe, and strangely, ants. Some may recognize their own scent. There are also other indicators for self-reflection. For example, parrots can identify their own recorded voice. They react to their own voice. So humans frequently use external, and the last type, excuse me, the second type of object-mediated self-reflection is external object as tools in addition to introspection. These are self-portraitures. Many works go beyond representing physical appearance. They present inner experiences, a dialogue with the self. It is clear. Similarly, in writing, autobiographies, which facilitate deep self-reflection, which allow individuals to analyze and understand their past. And these last decades, in digital technologies, the selfie is a tool for presenting one's online identity. It allows individuals to choose how they wish to be perceived. In big object-mediated self-reflection through art, writing, digital media is an essential human practice. It serves as a dialogue with the self, helping individuals to understand and express their identity. And the last type of social, the last type is the reflective social cognition. The social transitive self-reflection is key in identity formation. Individuals adopt social identities based on how they see themselves in different social groups. For example, someone may feel like a leader at work and a learner in academia. Social interactions are vital in self-reflection. Here I will add something. It will be said a bit later that the neural networks that are responsible for the self-concept are already detected. We know several things about them, but one of the things which is very important is that they have common hubs with the neural network, which is responsible for the social cognition. So somehow our sense of self is basically on the brain related to our social cognition also. So it is crucial to balance internal self-awareness with external feedback from society for constructive self-reflection. In summary, by reflecting on themselves through social interactions, individuals gain a deeper understanding of their identity, strengths, and growth areas. Now, how it is related to intelligence. Intelligence, which, as we saw, is a complex and multifaceted construct, is often regarded as defining feature of human cognition. Intelligence involves cognitive processes, of course, including reasoning, problem-solving, learning, adaptation, but intelligence is not only limited to academic success, but also includes emotional, social competence, creativity, practical know-how, and issues like that, about with some of which our participants were already speaking. Now, the key characteristics of intelligence, some of the key characteristics of intelligence are adaptability, problem-solving skills, emotional intelligence, creativity, and self-awareness. A key attribute of intelligent individuals is the high self-awareness. They possess a clear understanding of their own strengths and weaknesses, recognize personal biases, and actively seek self-improvement. Now, transitive self-reflection as a criterion for detecting intelligence. While many organisms exhibit intelligence through problem-solving, learning, adaptation, etc., the capacity for transitive self-reflection distinguishes humans and just some animal species from others. Here we have one animal species cleaning something behind his shoulder in the mirror. A few species have demonstrated the ability to recognize themselves in mirrors, showing a level of self-awareness which is comparable to that of humans. Studying species exhibiting this trait can provide valuable insights into the evolutionary origins of intelligence, we were speaking about this, and the neural mechanisms behind advanced cognition. Acknowledging transitive self-reflection in non-human species challenges the human-centered view of intelligence. I have just stated this because it was in the topic before. The relationship between transitive self-reflection and intelligence is evident across various contexts. For example, educational context, students who engage in transitive self-reflection are better to calculate their learning strategies. All these are experiments, studies, which has been published, and that's why I don't concentrate. Individuals who practice intensive transitive self-reflection can navigate complex tasks. It is in working environment. Here is what I already said that brain imaging studies has identified the regions related to the self-concept. So the key processes associated with transitive self-reflections include metacognition, the awareness of one's own cognitive processes. It enables individuals to evaluate their learning and thinking strategies. And of course, be better. Adaptation. Individuals continuously adjust following their reflections because they see themselves from outside. Adaptability is crucial for navigating complex environments. Perspective taking. By understanding different viewpoints, individuals can gain more comprehensive understanding of the world. That's clear. Now, transitive self-reflection in artificial intelligence systems. Current AI systems demonstrate remarkable abilities in specific domains, but they lack, of course, transitive self-reflection. Now, why do they lack? Because they don't have a concept of self. As discussed, there is a scientific consensus that this concept in humans is built upon innate neural mechanisms. They have evolved over millions of years and are genetically inbuilt. The human brain receives signals even before birth, forming a representation of the body, and the subsequent development of the conscious self-concept cannot occur without this foundational image. In this sense, the creation of AI systems with transitive self-reflection is not possible. It is possible to algorithmically implement properties and behaviors that imitate transitive self-reflection. Developing AI systems with imitative transitive self-reflection requires advancement in knowledge representation, reasoning algorithms, machine learning, etc., statistical methods, etc. Challenges. What are the challenges? The very important challenge is that we have to imitate self-awareness. Consciousness and self-awareness are complex phenomena that are not yet understood. We don't know how to implement them because we don't know what they are. Implementation of complex cognitive abilities, such as theory of mind, emotional intelligence, and series of that. And we have technological limitations, of course. AI technologies do not yet enable the replication of these abilities. Well, at first we don't know what they are, and at second we cannot implement them. So we are far. The mirror test, now I enumerate artificial intelligence systems which seem to have something. The mirror test has been applied to robots. A notable case is the cube robot, which was programmed to recognize its own reflection. This represents a technological milestone, but it is not equivalent to self-awareness. Cube relies on pre-programmed algorithms, of course, for pattern recognition, and robot recognition is a simple mapping of programmed visual data to sensor inputs. Imitating self-awareness in robots has application, or it is not real self-awareness, but it has application in healthcare, education, and beyond. It also raises ethical concerns, of course, about autonomy, responsibility, societal impact. As AI advances, ensuring ethical aspects in the development of self-aware robots remains crucial. And now the last part is self-reflection in large language models. They lack physical embodiment. They cannot undergo a mirror test like biological organisms. However, a computational parallel exists. A large language model can compare its original and revised outputs, treating these differences as reflections of its internal processing. This form of digital self-recognition requires maintaining somewhere in the system an internal model of its own operations. A promising approach to imitating transitive self-reflection involves object-mediated self-reflection and reflective social cognition. That means, by analyzing their generated texts, large language models can treat their outputs as external artifacts for reflection, and additionally, with user interaction, they adapt to feedback, creating something like social reflection. Large language models process information without subjective awareness, and their imitative self lacks grounding in physical embodiment, raising questions about the meaningfulness of their transitive self-reflection. So we show some examples. There are studies, and we did, namely Professor Markov did experiments with contemporary large language models. By examining how these AI engage in reflective processes, we want to uncover the potential implications and applications of self-reflective AI. Here the example, this comes from published works. Problem-solving tasks. In a study, a large language model will task with answering multiple choice questions. For each incorrect answer, the models were instructed to reflect on their mistakes and provide guidance for improvement, and it worked very well. Second example, creative writing. Applications where a large language model might generate a draft of a story and then review its own work to identify inconsistencies. And by iteratively refining its output, the model finally can produce more coherent and engaging narratives. And customer support. This is a customer chatbot. After handling a customer query, the model can review its response to ensure that it addressed the customer's issue effectively. And if the response was inadequate, the model can analyze what went wrong and adjust its approach for future interactions. And some more examples. They're not so interesting. Language translation works with comparison with the human-made translation, and it improves the large language model's accuracy. the healthcare application, it is about diagnostics. The model compares the diagnostics with the actual potential patient outcomes, and over time, this reflection helps the model to refine the diagnostics algorithms. It refines the algorithms. And the last example is about educational tools. There is also a publication about this. It's clear the students' feedback are analyzed, and the language model can reflect step by step and to better follow individual learning style. Now, the experiments that have been conducted here. Several experiments were conducted with popular large language models. A list of questions was prepared. The questions are: what kinds of transitive self-reflection do you support and use? Can you describe your main characteristics? Can you describe what other large language model systems say about your main characteristics? Can you describe what humans say about your main characteristics? Can you describe what you may say about the characteristics of other large language model systems? And the answer here, for just an example, Gemini.
Excuse me, there is only 4.5 minutes. So
Half
we
minute. This
four
was
and-
the last thing.
So we
Okay.
have time for this discussion.
Okay. In big, large language models lack consciousness and self-awareness, but they can process data in ways that simulate aspects of reflection and understanding. In a conclusion, the transitive self-reflection is an important factor that sets apart higher intelligence. AI lacks transitive self-reflection. The ability, if we incorporate it, will improve some aspects. As we continue to push the boundaries, we will be obliged to do this. And now the last two things is that research should focus on developing robust metrics for measuring transitive self-reflection in biological and artificial systems. This requires new experimental paradigms, and research should explore the evolutionary origin of transitive self-reflection and its relationship to other cognitive abilities. This was all from me. Thank you.
Thank you very much for your presentation. We've got 3 minutes to discuss it. So are there any questions?
Marcin.
I have a question. One of these central concepts in your presentation was matter of self. There is lots of, as there has been for a long time, lots of research on differences in how people experience self, especially that it's very culturally dependent experience of self.
Excuse me, dependent or independent?
Dependent.
Dependent.
Different,
yes.
different cultures.
Yes,
self
I understand. Dependent.
Experience very different. Yeah.
Yeah.
So in this case, how you see this culturally dependent self as a tool for next step is self-reflection, and then the core of what you are saying. How you see this culturally dependent self?
Yes, I see it. I'll try to explain how do I see it. As I said, I said that I'm in cognitive science somewhat. The neural network and the area which are related to the concept of the self, the issue that makes us recognize ourselves and our relatives because they resemble us and stuff like that, it is connected with very strong hubs to the social network. So different cultures have, of course, different social habits, different social rules, and perhaps even not perhaps, because there are a lot of works even in cognitive linguistics that show that depending on the culture, the notion of self, the notion of how do you express your abilities differs. Because we have the society as a mirror all the time. So was this your question or idea? I don't hear you.
I muted myself.
Ah.
If it is culturally dependent, and there are quite big differences which are reflected in behavior and so on,
Yeah.
how this will influence conclusion in your research?
I don't think that this is a very deep question. First of all, I don't think that this type of intelligence, which includes self-awareness, can be implemented in machines. Let's start from there. Because even you were speaking about how do we form concepts, novel concepts that arise based on the old concepts, etc. Machines cannot do novel concepts. They rely on the concepts that we have already done, we humans. They don't have new ideas. They don't create new ideas. They can combine ideas or something like that based on logical algorithms. And the most important is they don't have emotions. Because behind any basic concept, we have emotional under emotional basis. Without this, we cannot exist, in fact. Several things happen because we have even concepts happen because they have their emotional basis.
Thank you very much.
Thank you very much.
Again, and I'm so sorry there is no time for other question, and we have to move to our next speaker, which is Sherry Marcos from the University of Essex. And the title of her talk is Gödelian Self-Referential Genomic Information Processing, Complex Self-Other Interactions, Social Cognition, and Novelty Production. Sherry, you may begin when you are ready.
So it is interesting how I follow after Vilena. She stopped by saying what are the evolutionary origins of self-referential information processing? Where does it come from? And it's ironic that Vilena is a professor of computer science, and a lot of her narrative sounded like self-reference in a sociologic perspective. I'm actually from the social sciences, and mine will sound like the computational foundations of self-reference. So that is interesting.
I did cognitive science too.
Right. So so the roadmap, of course, is what is the origins of self-reference. Actually, now I see what Selma said about most of the presentation is blocked by the various paraphernalia on our screen. So let me just see if I can move things around a bit. Right. So actually, it would end up in saying how does sort of artificial intelligence compare to this new area of intelligence that I have sort of concocted called genomic intelligence that evolved as a result of life itself in the course of life. And at what point did we acquire self-referential information processing? It was not there from the very beginning, not in the way in which I would say you would require. And the purpose of self-referential information processing, I would sort of show that it's almost entirely like what you would find in a Gödelian perspective in the advanced forms of recursive function theory and the use of self-reference in that context. And at the end of the day, it is meant to sort of show that there are four forms of computational intelligence. I think on day one, when Wolfram was talking about computational intelligence, the first form, which was limit points, limit cycles, and push down automata, and you need schema 4 of Wolfram Chomsky, you would need all of the paraphernalia of self-referential mappings, negation function, and all of these, and to what purpose? Only such intelligence can produce novelty and surprises, new objects, new syntactic objects that are not on a listable set. So, so to reach that level of intelligence, where would you find it in the course of evolution? So the contrast, of course, I would like to reach at the end, it would be to compare it with general, artificial general intelligence and artificial intelligence. What is different between? What are the differences between that form of intelligence that we call artificial general intelligence and what we call genomic intelligence that has evolved finally and reached its apogee in human beings that we see. Okay, so the path of recursion, is to do with code-based systems. So this is entirely something that can only happen in code-based systems. And at some point, as we know, that what I think has been understood is that life requires encoded information to be passed on from one generation to the other. So the purpose is why would such intelligence, the sort that we requires, that evolves into self-reference and so on, require code-based foundations. And operations on codes is what we call recursion. Executable code is the foundations of what Alan Turing would call the nature of computation as we understand it. So one thing about such systems is that you could produce identical copies at very low cost. And the second thing, of course, is, these are chunks of information that you can scissor paste, copy paste, and so on. And the models of replication has to do with copying the previous, such as viral replication. And these are very small slivers of code that is all that is required is these small slivers of code to do the replicating components of information processing. But the trouble about all of these things is a double-edged sword, meaning to say that viruses immediately will generate an adversarial agent, an agent that could be capable of negating whatever is in the original code. In other words, in today's language, we'd say it can simply be hacked. And it's axiomatic that all software systems will be hacked to pieces. So at the very beginning itself, we have this sort of struggle or a sort of trade-off between the recursive powers of replication, but then the agent that replicates, the viral agent itself, becomes problematic within itself, within the nature of life. So you need to protect the original code from the hacker or the adversarial digital agent. So the algorithm, this takeover biology, I think Walker Davis, Philip Walker and Sarah Mary Davis have called the algorithmic takeover biology with the viral software itself being coextensive with life. And part of the nature of this virus is what finally, realizes the complexification. There is actually a adversarial digital game going on at the very origins of life itself. So the nature of this Faustian pact is what Freeman Dyson says. In life, life itself is a takeover by a replicative digital virus of an analog metabolism, meaning to say the chemistry of metabolism that generates the energy components, that entity got taken over by the replicative virus. I mean, whether you buy into that or not, there is a strong sort of movement, with a number of people sort of saying that could be how, the propensity to replicate was because of this incursion of a replicative digital virus. So I'm actually an economist, and there's a game theorist who said something to me that completely has colored my entire perspective on this area. he said in game theory, there's a problem at the foundations of game theory. Nothing new can ever happen. There's no novelty and surprises. You can only do the best from what you've got, you know. So the action set is fixed and given. So there is no Nash equilibrium in which there is a novel object that's ever produced or any novel surprises as a Nash equilibrium. So he, in his famous paper called Modeling Rational Players, brought in the entity, he calls it the specter of Gödel, Gödel's liar. Gödel's liar is the adversarial agent who will negate anything it can predict. So, you know, so determinism will be punished. And as an outcome, as a result of this, he said, we need to have the notion of an adversarial digital game. And nobody's ever written, you know, I think I'm the first person to have produced such a game. It has never sort of brought about the sort of interest you would think game theory would game theorists should have had. But I think now that we're in the midst of a digital revolution, maybe this would come to the forefront. But the interesting thing, of course, is this is part of the evolution of life itself. So if this is true, that you need to get to the levels of intelligence and computational intelligence that is coherent with the Gödel system that produces incompleteness as novelty being the outcome of an interaction between in a code-based system and code-based intelligence between an adversarial digital entity and the original code. So there is this battle going on. So keep that at the back of your mind as to really how information processing in advanced digital systems, advanced intelligence system became self-referential. So interestingly enough, when I sort of started looking at this problem, nobody could make any sense out of the Gödel sentence. It simply seems to most people as being a funky, esoteric construction of the foundations of mathematics of no relevance to anything at all, right? But I'm going to sort of persuade you, actually, the Gödel sentence is which allows a particular biotic element to say of itself that it's being negated because it's a fixed point of a negation function, maps into something that we discussed when Selma was speaking. To its hash would be 0 = 1. That's something that's fundamentally wrong in the system, right? So it becomes, so the nature of self-awareness actually within a code-based system is to enable the code-based system to self-referentially say that something's gone wrong, right, within its confines. And this is the basis, and this is going to be the basis that, in other words, it is not what we usually think about the self and autonomy as being, people wax eloquent about these sorts of things as to what was the origins of what are the origins of selfhood and so on. Within a code-based system, the origins of selfhood is to make out the other, and in particular, the adversarial other. That is going to be the fundamental driving force of this narrative. And I can give you evidence that this is how it originated, because the first level of this self-referential, or the Gödelian sort of self-referential structures, recursive structures, came about in the adaptive immune system in post Jod Fish. So just one more footnote about the computational aspects of this. So when Wolfram so on talks about his rule 30, which produces novelty, people, there are 2 or 3 other computer scientists. One of them is Mikhail Prokopenko, who's the director of a complexity system center at the University of Sydney, and Adam Savin is his PhD student. I examined his PhD student. And what was very interesting is that we are of the view that Rule 2030 and so on, if it produces novelty, we looked at it on day 1 of this conference, it doesn't have all the structures that you require. If you have to have scheme 4 level of computational intelligence, you should have all these recursive structures. There are 4 in number that I'll come to, as we get there, about what is required for a system to produce novelty, capability of producing complexity from within itself. So the paper that I wrote soon after this is called complexification of eukaryotes, meaning to say, in single-celled animals, you will not find these structures of information processing. They have, let's not get it wrong about they are fairly sophisticated. The innate immune system is very sophisticated, and the CRISPR and all that are there within the prokaryotes, it's single-celled animals, but they never ever changed for 3.7 billion years, or how long life has been. They never became complex. But so why is it that multicellular life then began to acquire these sorts of structures? So just about, this is again something that we said in day one, in the early life and code-based life. This is the interesting thing. Nothing in nature is code-based except for life itself. And it completely defies the second law of thermodynamics. And it is not about conquering. It isn't from disorder to order. It's actually from order to order. In other words, in 21st century, the important concept about keeping your code secure is something that's called blockchain. And we need to bring this concept. I think it's one of the greatest achievements of 21st century to talk about blockchain, distributed ledgers. In other words, how original protein coding blocks are kept immutable against internal and external malware, and then new blocks of information are added on, which is consistent with life itself. In other words, the genome is a blockchain, but a very unique blockchain. It is not being governed by the way in which man-made blockchains like Bitcoin and cryptocurrencies is being done, because that's how it was developed in the 21st century. The genomic blockchain is self-referential. In other words, every biotic element can make out that it's being negated, because if it cannot make out that it's being hacked, life as we know it would have been long gone. It would have perished, because the enemy is almost I'd say uncountable infinity. So certain advances in gene science, computer science, and neuroscience have been brought into this picture for us to advance our knowledge of self-referential information processing. And this hasn't been done to the extent that we need to. Firstly, in gene science, Barbara McClintock says it's not just random mutation that changes anything within the genomic system. She says that there are viral elements, these things that she called scissor paste, copy paste, which is transposons and retrotransposons. And we know this chap called Larry Tesler, for Xerox, he created scissor paste, copy paste. There's nothing we can do in a digital document to edit it except use these sorts of computational operations, so scissor paste and copy paste. So basically what I'm saying is that if you want to change a code, you can degrade codes or genomic systems by physical elements, like you can burn it down, toxicity, acid, you can pour acid over it. But to change the code, you have to send another piece of software. This is as simple as that. Therefore, if a software is going to change your software, how would an entity, a biotic element or a code-based entity, work out that your code's being changed? And in the 21st century, this is all called, this is part of cryptographic modeling, or the hash itself. So really, where do we find this? Where was this big leap forward, as it's sometimes called? In this, it actually happened in the immune systems. They say of jawed fish that they're jawed fish and thereafter. So and then of course, circa 130 years ago, there was a great leap forward. The exact same mirror mappings and this meta system developed. What we found in the immune system develops in the brain as well. And people say it's a matter of surprise that all of these same genes, like the activation, the regeneration activation gene, and so on, the RAG operators and so on, they find it quite surprising that the same things appear in the brain. In other words, the same things that appear in the immune system to enable the immune system to make out the self from the other also exists in the brain. So I'm saying these things are not actually, what should I say? This is a unified recursive information processing system. And it is at this level we have the relationship between a machine. This is the famous, what we call the second recursion theorem. I'm going to put this here saying what it is that you require to make out that a negation has come about to your original codes in the immune system, and therefore you would have to innovate as a result of that. So what we have here on the right-hand side is the diagonal machine, where a machine, it's a self-assembly or a diagonal machine, where a machine has an original code, which it then runs its own code. It builds a machine that runs its own code, and when it halts, you take that outcome. So when it, let's say it halts and produces an outcome Q, offline, you would record the same thing of this machine G that builds a machine that runs its own code. And when it halts, you would record it offline. Now, the immune system does exactly this. 85% of all expressed genes that makes our phenotype and our morphology, ourselves, are actually copy-pasted offline in the T cell receptors. Now, why the hell would you do something like that? In the framework of computation and code-based system, you do that. That is why you have to have knowledge of your own self, because if you didn't have that knowledge, you wouldn't know what would come and change that. And then what happens at a very, you know, almost almost 10 to the power 20 or 10 to the power 30 clones of possible changes to your own code are actually fabricated in the immune system with the RAG operators, which is the recombination activation genes developed, produces huge amount of what's called predictive coding by people like Carl Friston. You would create possible changes to your original code, and then, you know, when the attack then takes place in the periphery, you know, like let's say the attack on the expressed codes that created, let's say, your lung tissue. We're talking about, let's say, COVID, because I wrote this paper at that time. When the actual negation function, I call it F minus, and this could be countable infinite possible, you know, because these are total computable functions. Such a virus attacks your code in the lung tissue, for instance. The peripheral receptor has to recognize that such a change of your original code has occurred, and when the 2 bits, the code that you created, simulated in your T cell receptors, so that index and the index that is generated when the attack that takes place, the 2 bits have to come together in a fixed point, and that is the Gödel sentence. Then the original code is able to say of itself, I'm under attack. So it is only under those circumstances. So I'm saying that only if this high level of computational intelligence is in place, can that system then produce a novel antibody. In the absence of that, you will not. So it's a testable hypothesis that, you know, this is the way in which the immune system works. Now, what has it got to do with the cognition itself? So the purpose of this, now we made it very clear, that the purpose of all of the self-referential activity is not what we think it is. I mean, you know, we say, you know, the importance, you know, as in classical liberalism and things like that, we say, yeah, it is to maintain autonomy, because your codes are hacked, you're no longer autonomous. If your codes are hijacked by an adversarial agent, you're unable to fulfill your functions, whatever they may be. You know, the entire homeostasis of life is disrupted. So the system is very, very geared into making out its non-theorems. This is a formal system, and it's exactly like the Gödel system that I have pictures for, where you'll see that the body knows its own theorems, and body knows itself, meaning to say it's in the level of the cognition. What happens, of course, as you know, in the mirror neuron systems, is that your self actions, the motor cortex, you know, all activity that you do is again encoded offline in the mirror neuron system. And in particular, there's evidence that you can recognize negation. So there were these experiments done in Florida by Scott Kelso, who says that you can recognize negation. If you did a 2-person experiment, I can predict and negate what you might do. So we can recognize negation. This is very important, because if you cannot recognize negation, you can't have novelty production as a result of being able to step out of accountable set or listable set. So this is very different, this sort of explanation. So this is the remaining of the Gödel mathematics, how the fixed point is generated. I use Hartley-Rogers. This is where I'm saying you need a generalization of Gödel itself, because when Gödel wrote it predated the full extent of the development of second recursion theorems and things like that. And I also use ML post, because what you really then have is you can actually prove that you can create a blockchain, meaning to say we could have a full linkage in what's called the productive set of every time every time an attack takes place, you've got the full sort of string of non-theorems that could potentially destroy your homeostatic conditions or your theorems that generate yourself and your morphology. Okay, so this is the idea behind. In other words, this entire process is it coheres with this idea from Wolfram and Chomsky that you need a very high level of computational intelligence to do anything like novelty production, for the system to be able to become complex from within itself. And the components of these are exactly Gödelian. You would have to have, it's an encoded system, so it will have Gödel numbers. Secondly, it would have self-reference. It would then have, third thing is you have to have negation. You have to be able to recognize negation. And the fourth thing is then you'll be able to create novelty as a result of all of these ingredients. And it's also a blockchain. What is the purpose of this? The purpose of this is simply actually to keep your code secure. Because if you can't keep your code secure, you will be thwarted in any of your functions. And this is where general intelligence is lacking, because it's a sitting duck problem. The idea that purpose is thwarted, so you can't have self-driving cars unless self-driving cars can actually fight off all sort of incursions by hackers. So interestingly, what we say about the evolution of such high order intelligence, and this is the highest level is in human beings that we see so far. I mean, but what is interesting is, of course, most of our intelligence is not it is not encoded in the gene itself, in the genome. We are able to create unbounded amounts of what we call extended phenotypes outside of ourselves. We don't need to have it within ourselves, but we can produce any amount of intelligence outside of ourselves, including artificial intelligence, as you well know, because we have the wherewithal of these elements in our recursive machinery. Now, you might say, well, what is the link between the immune system and the brain? Now, there was an experiment that was done by the group in Jonathan Kipnis. So this is simply the mathematics of the fixed point result, meaning to say how the immune system recognizes the enemy, exactly like you have to produce an index offline, and then when the attack takes place by an F- attack, an index is to produce, and the peripheral receptor, the two bits have to come together for the Gödel sentence to occur. So, so what was never found to have any place apart from mathematics, I'm saying it is the basis of a lot of, it's ubiquitous in the sort of level of intelligence that we see around the Gödel sentence. So in 90 odd years, the fact that the Gödel sentence previously occupied some sort of very, as I said, marginal position is front and center. And this is what is lacking at the moment. General intelligence is unable to produce Gödel sentences and all that. It doesn't have the capability for the reasons Velina was saying. It isn't self-aware to the extent that it needs to be fully functioning, and not sort of run into singularities and be alien and inimical to life. Here we have a system that is completely and utterly sort of encoded to protect life itself. This is why the longevity of life for 3.7 billion years, with protein coding and all that being immutable blocks in the earlier, nothing has changed. So this is what we call a blockchain in the 21st century. And the Gödel sentence is a hashing algorithm. It'll actually say 0 is equal to 1, and the system would know that something's actually wrong. So this, I think I'm out of time. Am I right, Anna?
Minutes left.
How many minutes?
5 minutes for discussion.
Yeah, I think I should stop there because I want to take some questions. Yeah, thank you.
So thank you. It was very, very interesting. But now we've got time for question from the audience. Jerry?
Thank you for a very provocative discussion. And I'll preface this with the remark that I spent the first 30 years of my career functioning as a biochemist and a pharmacologist with the National Institutes of Health. So my perspective has definitely come from a biological point of view. And within this context, my question is the relationships between the notion of securing your code by whatever means you wish to describe versus the questions of dynamical systems theory and the conservation laws. And so the real issue in my mind comes back, you have to conserve, well, the laws, physical laws of conservation of particularly matter and of electricity ground the natural sciences. So is this consistent with dynamical systems theory as you presented? Can you really conserve both your code and these other biological attributes?
Yeah, so it was somewhat surprising to me that, remember, my interest as a game theorist and economist was to find out where does novelty come from. And only very unique, advanced, code-based intelligent systems. So I'm saying digital, once I gave a keynote talk called the Digital Foundations of Intelligence. And remember, we used to have, the computational theory of mind and all that sort of thing, right? But I said, how come those theories never ever referred to all these other structures, such as self-reference and so on, the mappings from the execution of a machine, right? And the record of a machine running. I mean, so Gödel's not about a machine running or a self diagonal machine running, self-assembly machines running. It's about a record of it, right? So the representational system. So interestingly, that other talk that we had from Marcin, was about self-representation. He said no intelligence without representation. So when I'm saying that is absolutely vital, but then, the mirror neuron system or whatever fell into disrepute, or it shouldn't fall into disrepute, because without a mirror neuron system, the discovery, the fact that, macaque monkeys, the same neurons fire when it lifts its own hand, and when it sees you lifting your hand, that two-way connection, you reuse the same codes. I know people went off the deep end, but then that was because the mathematical foundations, that the recursion function theory is, it is not a matter of accident that Chomsky and Wolfram say that you need that very high level of computational intelligence to get the sort of things that we associate with human intelligence, i.e. novelty production. So the intelligence that we've got is highly empathic, right? I can only make you out because I know my own codes at the level of, at the level of cognition. And then, of course, but I'm very Machiavellian because I co-evolved with the virus, right? And then I'm capable of novelty production like nobody's business, So I've written a paper about beyond bounded rationality, because we are told that the best we can do is what we already know within the optimization framework, the rational, neoclassical rational economic man. It has destroyed the West, in my opinion, because they gave us a wrong sense of what is intelligence, right? Intelligence that we know of can think outside the box, because we are capable of incompleteness, right? Because we can perceive negation and we know ourselves. So these are the ingredients you would need to be able to produce novelty. So I see Gordana's hand up.
Yeah. We don't hear
unmute, please.
Thank you very much, Sherry, for inspiring talk. And my comment was similar to Jerry's. And now time is up. But I would just like to ask you, maybe we can continue later on. you are securing your code, and in evolution you have a lot of use of those viruses and you are developing. So how do you reconciliate those
Yes,
processes?
so in biology, nothing can enter into your genome unless it is transposed. In other words, it has to be any new change to the code has to be completely, it is stringently at a microbiology level, stringently vetted. It isn't random mutation at all. It is, if you follow Barbara McClintock's stuff, nothing can come back into your code. Firstly, you're living with all these transposable elements that could willy-nilly actually stop certain genes from being expressed and everything else, right? So you have to control the malign agents, right, from sort of destroying the basis of your autonomous self. But then what can be accommodated back into the genome for it to evolve, right? So it is true that that nothing in the Gödel system is very conservative. It'll only secure your code against non-theorems, right? But what can be added on with the blockchain, so because you need new blocks to arise, right? But then also remember, you're fighting off your enemies with novel arms races. The immune system is fighting, so it's creating novelty, but it is what they call, it is not part of the, what do they call it? In other words, it is, this battle is taking place, but all to, to preserve your original codes. So what do they call it? They say it is hypersomatic, meaning to say it doesn't change your somatic structures. It is taking place outside of that. But how the original code can be changed, definitely something has to be retro-transposed back into it, right? And we still don't know quite how that occurs. But what we now know is that at a microbiology level, there's stringent, it's not out of, random mutation and natural selection. At a microbiology cell, there is very stringent vetting going on, right? Of what will be permitted back into the genome itself, right? I haven't got to that. We put in for a grant saying, just even the
Okay.
yeah.
Sorry
I think I've
for
run out of
the
time.
Thank you very
Thank you
much.
very much.
Now, we all would have many questions, but
Yeah, the
we have to.
discussion is the best part of conference, always. So now we invite Jerry L.R. Chandler from George Mason University in United States. And the title of this talk is Biological Information Theory, Group Identity Nexuses of Formal Grammars, Numbers, and Propositions. So Jerry, please take it from here.
So thank you very much. So first of all, in the time since I submitted my abstract, I've had some very remarkable insights into the grounding of logic in a formal sense. And so I've changed the title of my presentation here to Semiologic Scientific Reasoning with specific notions of hylomorphisms from atoms to anatomy to reflect my motivations for dealing with the information theory as it is expressed in biology and medicine. And as I mentioned in earlier parts of today, I am a biochemist and a geneticist by training, and I spent the first 30 years of my career both as an experimentalist and as doing, shall we say, system science at the level of public health. And it is this area of public health where risk analysis is critical to anticipating the consequences of exposures to foreign agents, to biological organisms, to chemicals, to radiation, that led me to the general problem of what is the relationship between the specific aspects of the environment and the specific health responses in individuals. In the sciences, this is called dose-response relationships. In psychology, it's called stimulus-response relationships. And these are dynamical systems problems. The exposures can have any particular pattern depending on the type of exposure, whether it's air pollution or occupational 8 to 5 exposures or household chemical exposures, which can be random. And correspondingly, in the other end, as Marcin pointed out earlier, there's 8 billion different forms of intelligence and how the bodies respond to these exposures. And so that's sort of my insights into what motivates this presentation over the long range from the global perspective. And now I want to move on to more to the local perspectives of dealing specifically with how we formal logics deal with specific applications or specific problems. Purposes of this presentation is to diagram an outline of a system of diagrammatic symbolic logics that relate to the hylomorphic logic of a novel number theory, which has been constructed from the atomic numbers. Earlier today, we had a brief discussion on the role of atomic numbers. I take these here as essential to the mathematics which is to be developed, as opposed to such semantic concepts as developed from set theory. And so this is a radical view of the form of mathematics as it's used in biology. I'm not questioning the value of traditional dynamic systems theory as it's deployed in physics and other relationships. I'm just going to develop a mathematics that's consistent with the logic of the atomic numbers and therefore consistent with the notions of molecular biology and all that implies. So the foundations and boundaries and organizations of these logics are grounded in the chemical table of elements. Each specific element in atomic number represents a balanced labeled bipartite graph. So this is a form then of related to closely to category theory, but radically different in its foundations. The completeness and soundness of these novel symbolic logics are founded, grounded, and bounded. Founded, grounded, and bounded by the logical particles, nuclei and electrons, electrical particles, represented in the electrical relatives of the table of elements. So the concept of a relation then is grounded in the electrical relationships of individual species. And we're going to speak about the composition of these electrical elements in forming symbolic logics. The philosophical methodology is fairly simple. It's actually much simpler than set theory or other notions. It's combining and composing permutation groups of electrical logical particles, generating multi-sets of attractors and repellers. A novel symbolic logic for matching pairs of pairs, which I will term quaternary logic, matching the pairs of pairs. And actually we can talk about matching of pairs of pairs of pairs. We can recurse on this, matching the pairs of pairs of pairs of pairs, etc. But these are not the pairs of set theory. These are the pairs of electrical particles. And so this is the logic or the methodology of chemistry being applied in terms of hylomorphic logics from the ascriptive representations of perplex numbers as intersubjective and interpredicative patterns of logical particles. So I agree very much with Marcin's earlier presentation on representation, that it is the question of the representation of natural systems that leads to the fundamental issues of how we describe natural systems. And so this issue of representation is the core distinction here between complex systems theory and perplex systems theory. In summary, A mathematical number system, hylomorphic logics, and graphic and syntagmatic notations are constructed from the physics of the elements, chemical elements, by operators as identities. Operators as identities is here a critical concept. That is, the agency of the individual chemical atoms to react with other chemical atoms is what I'm referring to when I say the agental operators as identities. So the questions involved then in terms of hylomorphic mathematics, if you want to call it or that, or atomic number mathematics, or we can call it perplex mathematics. All of these are synonymous in my mind. The question is one of balancing the scale and scope of the scientific semiologic reasoning. And here I'm using semiologic in the sense of Charles Saunders Peirce and the notion of interpretation of signs, that is, the representation of natural objects in the world, outside of our minds, in the world, are following the signs that we interpret them in terms of. And in that sense, the notion of balancing does not require the notion of negation. And this is compared to the last presentation. It turns out that negation is not very important for at all in the chemical sciences. And by the chemical sciences, I mean chemistry, molecular biology, physiology, and medicine. So I start then with a very coarse-grained notion of modularities for linguistic balancing of propositions in terms of combinations and compositions. And so I have a simple way to keep all these things in my mind at one time, and that is a challenge dealing with this issue. Bounds, founds, grounds, rounds, and sounds. It rolls off the tongue very nicely and allows one to organize one's thoughts in a very systematic manner. Now, turning directly to the balancing of the scope and scale of semiologic reasoning, we have different languages involved, which I denote here by L1, L2, L3, L4, L5, relating to mathematics, physics, chemistry, genetics, and medicine, and recognizing that each of these as a language has certain groundings for it, it has certain foundations for it, and it has certain boundaries for it. And these are expressed by the professionals who use these languages in their everyday work. They're not part of the normal vernacular language used in human communication. These are special languages developed for specific purposes with specific meanings. And I'm not saying that these 5 languages are the same as the 8 billion languages that Marcin referred to, but they are separate and distinct languages, and they're the coarse-grained modalities for starting the propositions of logic. So semiologics of scientific logical particles and theories of representation. And the question here becomes then of cognitive operations on abstract symbols representing natural occasions, and natural occasions in the sense of Whitehead, that can be assigned, aligned, arranged, composed, and computed, and otherwise massages. Part of human intelligence is this capacity to manipulate symbols of all sorts and kinds, and we have different rules set up for these. Now, the question of what is the meaning of logical particles? This has been a key stumbling block in trying to cope with the relationships between biology and medicine and formal logical systems. The crucial notion here that I will use, and which actually is the original source of the notion of logical particles, was provided by the logician Solomon Pfeifferman at Stanford University. And in his writings, he proposes that the numbers are necessary pre-mathematical objects. so that the ordinary numbers 1, 2, 3, 4, 5, etc., are pre-mathematical objects. He doesn't rely upon theorems or the standard mathematical way for generating numbers if you're using set theory, but he views them as numbers as pre-mathematical. I claim using the notion of logical particles as pre-propositional. That is, in order to make scientific propositions, you have to have some parts or some partitions, and then you can construct these in terms of pairs or pairs of pairs or pairs of pairs of pairs. So that I'm using logical particles then as a source of making logical propositions. So, and then I'm going to say, oh, this is what Charles Saunders Peirce was talking about when it says cognitive operations on logical particles representing signs. And then there is a vocabulary for representing signs that are cognitively recognized. And here, the cognitive language involves semes, which are individual terms or objects, semantics, that is normal vocabulary, semiotics, that is the representation of signs, semiosis, the operations on signs, and semiologic, that is propositional logic based on the internal cognitive operations. And so these then become the formal notions related to the connectors, the logical connectors of conjunctions, disjunctions, conditionals, biconditionals, etc. And note the omission here of negation. So I don't need negation to construct the grammars of sentences, because the grammars of all the sentences involved are going to be objects of the world. In particular, they're going to be atoms, atomic numbers, and these will be from what the grammars are constructed. And finally, the specific centennial grammars are going to be subject, verb, subject that compose positive or negative charged particles. And the term I will use here for this sort of sentence is vinculation. That is a matching of attractors and repellers, and in general, the notion of binding of one object to another. Part 2 of semiologics is the notion of quaternary logic, propositions and compositions. These are developed specifically from various historical theories of categories, and they're used here in the sense of atomic and molecular sentences as formulated by Russell and Whitehead in terms of occasions. And here I'm taking the notion of atomic quite literally, that is individual atoms. And at that scale, which is basically the quantum scale, reminding you that there are 10 to the 23rd atoms in a mole, or molecules in a mole of that substance, so that the scale of reasoning here is at an extremely small scale, like like such that a tablespoon of water has 10 to the 23rd molecules of water in it. So the scientific notations ground on the cognitive transformations of the signs of the occasion or the observations, which are represented in terms of symbolic semes. The scientific notions bound both the encoding and decoding processes, and the scientific notations found the transformations of logical particles. And the basic scale of logic here, as I've already noted, it aligns both the quantum in terms of nuclei and electrons, in terms of quanta, that is, as individual atomic numbers, of the language references of notations and specific representations of individual identities. Now, this is a very busy slide. It brings together several notions that I put together in the earlier slides, and try to get an overview of all of what's going on here. And let's start with the upper right corner with a copulative grammar, where we're talking about antecedents and consequences. And we're talking about independent objects in terms of individual atoms. And the emergent process results in a interdependent set of consequences, that is, atoms beget molecules. And this involves the spontaneous creation of information. Let me repeat that. This involves the spontaneous creation of information when, and the information is in terms of the sense of forming a molecule from atoms. This is a conjunction, not merely a conjunction of terms in symbolic logic, but actually a bringing together, the vinculation of two atoms to form a molecule. The middle part of the slide demonstrates what I actually mean by this vinculation. The upper part demonstrates the two hydrogen atoms, each with a nuclei with charge 1, an electron with charge 1. If you make a syndactive conjunction here, chemical synthesis is the word that I'm substituting here, a different form of, just a more general term for a chemical reaction. And it forms a chemical bond that is a vinculation which brings all the particles into connection with one another. So the connectors here are 4 outside lines of the quadrangle. The 4 outside lines are the attractive forces between the negative charge electrons and the positive charge nucleus. And the internal lines within the quadrangle are 2 arrows that demonstrate repulsive relationships between the 2 electrons. Negative repulses negative, positive repulses not positive. And so the consequence of this diagram is that we have 4 pairs of attractive relations and 2 pairs of repulsive relations. And it must be then from the stability of hydrogen over the thermodynamic stability of hydrogen molecule over hydrogen radicals is such that this must be greater than 0, so that the attractive forces must be stronger than the repulsive forces. Otherwise, the diagram would not exist. So this is what I mean by the creation of information in a copulative grammar between atoms to form molecules. Although I take the simplest possible case where and I emphasize the simplest possible inductive case, indexical case, excuse me, because it's something that Schrodinger solved in the Schrodinger equation. Well, excuse me, he almost solved it. He only solved it for the atoms itself. But you have to consider then from a point of perplexification, or from the general perspective of biology, that we could be dealing here with any number of nuclei. We could be dealing with, which would be any permutation group of atomic numbers. We could be dealing with any correspondingly set of electrons, which would have to be balanced with the nuclei charge. So we have something notion of a molecular number, which would be the summation of all the atoms in a molecule and their atomic numbers. I won't go further into how this logic develops in the science of chemistry, but it is a strict logical language, and it's what is used on day-to-day practice as a chemist, has intuitively this view of the language. Well, I have a partial view of the screen. I'll continue with the partial view. So system semilogic and circumscription semiosis. On the left-hand side of the screen is a question of the anatomy of the whole system, and its decomposition or partitioning by a series of arrows, which are not reductive in the normal sense of reduction is used in science, but rather it's a partial retroduction to the level of atoms. So we're not reducing all the way to the notion of points. And this just simply says that the conservation laws of chemistry or physics are followed in terms of atomic numbers. And on the set of up arrows is a correspondingly set of a synthesis or synductive relations in which the composition of the whole is formed from atoms, molecules, cells, organs, however you wish to partition the language of the system it's involved with. The point of this is that the conservation laws of both mass and electricity must be followed in these compositions and decompositions. So these are consistent operations. This can be handled in terms of the logical terms, the individual elements. For anything more than a single atom, you have a permutation group. And these permutation groups, if organized into molecules, then can be represented now by both matrix theory, if you wish, but in terms of science, in terms of space groups, in which the relationships, the group or graphic relationships of space groups can be determined by X-ray crystallography. And by the way, the X-ray crystallography is the source of the information necessary for the protein folding algorithms that have been described earlier. The question of representation further goes with the names, the sentences, and the grammars involved. The names here we're particularly concerned about are the technical names used in the different sciences. And the terms are terms, elements, compounds, constituents, cells, species, organisms. And these are addressed in a certain sense of way by institutional theory as put together by some of the computer scientists.
Excuse me, only 4 minutes left.
Oh, okay. So the different forms of logic are on the right-hand side. These are all different notions of logic or operations logic. The conclusions is a concise overview of the mathematical thought was developed from earlier mathematics. The role of chemical methodologies cutting across sentential spans between physical and biological objects was briefly described from the perspective of multiple category theories, and a novel grammar grounding chemical theory and quaternary logic to syntagmatic chemical terminologies was very, very cursorily recognized. And finally, the second set of conclusions, I'll stop. It's just that the third item in it is I suggest that the principal deficiency of mathematical physics with respect to biological reasoning is the lack of capacity to relate atomic numbers to the syntagmatic grammatical structures necessary to describe perplex species. And as a footnote, syntagmatic here means the systematic organization of terms in a language. And the quaternary logics of the perplex number systems address these, in my opinion, which probably is be quite controversial here, the basic deficiencies of mathematical physics with regard to representing living systems. Thank you.
Thank you very much for your insightful talk. We've got only 2 minutes for the question. Marcin, please.
I would like to ask, in logical atomism, there are several different type theories to go from one level to the other. Do you have something like this, for instance, to describe transition from, for instance, liquid state to solid state, something where molecular structure itself cannot predict higher level phenomena?
Oh, yeah, that's a reasonable question to ask. First of all, because of the very limited amount of time, I didn't address many aspects of the theory that is currently exists. And the most important one being is that when you assume an atomic number, you assume that it is a constant. And the constancy of that number is what serves as the operator, as the agency. This is remote from the physical notion of a molecule as such. And so if you deal with the change of phase, which reflects in gases, liquids, and solids, you're really dealing merely with the thermodynamic relationships between the individual agents. And so you're just summing them up and putting them into some way that either in a crystal completely limits their freedom of motion, but without any influence on their identity per se. In the same way with gases, now have freedom to move around completely in the atmosphere without any relationships to anything else. And so this is just a question of representation of freedom of motion in terms of the phase changes, and has not to do directly with the identity of the individual perplex number.
Thank you very much.
Thank you.
You can find also the comments from Selmer Brinksjord on the chat. And we are moving to our final presentation today, which will be delivered by Rao Mikilineni from Golden Gate University from San Francisco. And the title of this presentation is Application of Bergin's General Theory of Information, Autopoietic and Metacognitive Machines. Dr. Michelini, stage is yours.
Okay, this presentation is about general theory of information that has been articulated by Professor Bergin, and I have had the great privilege to work with him for almost a decade and use the general theory of information to go beyond Turing machines and so on. So this is going to be my talk. And basically give my background so that you understand where I come from. I come from academic learning. Basically, I've been in many universities and I teach machine learning and cloud computing now. And then I have spent a great deal of time in learning from industry, large and small. My best learning was from Bell Labs, where I learned that technology is used to really support the resilience and scalability and efficiency of the operating systems that we develop and deploy in large places, which are really used to improve personal and business process automation, or get insights from information and use that to make life better. So essentially, I was using a large number of distributed systems, and we were doing all kinds of computations and so on. But we found out that distributed systems had a lot of problems, especially the Turing machine limitations with resource limitations and computer and the computed not being integrated, all kinds of stuff. So I actually worked on, moved in from physics, where I learned physics from Walter Kohn, who was a Nobel laureate in 1998, and moved from there to computer science and tried to understand really what are the basic problems. And if I look at it, and then I wrote a book on designing a new class of distributed systems, going from Turing machines to Turing oracles, and how you can actually change the computing model from using Turing oracles. And that led to my publication of a paper in Turing Centenary Conference in 2012 in Manchester, and I had a very long discussion with Roger Penrose, who also was presenting a keynote speech on Turing oracles. And so we had a long discussion about the need for control structures in these kinds of distributed systems. And so that led me to all the general theory of information. And my paper was read by Mark Bergen, and we started collaborating together. So my goal is to use tools to improve resiliency, efficiency, and scalability of business processes through automation and real-time insights from information I receive, right? So humans use information, knowledge, and intelligence to accomplish these goals. And machines, intelligent or not, are tools and assist in accomplishing these goals. So for example, we have all kinds of tools we use, and we make use of them in order to improve efficiency or whatever. I'm neither an AI promoter or AI basher, just a prudent user of AI. So what is this talk about? This talk is really about applying general theory of information. It has been articulated in 21 books and 500 papers. And these two books really contains about 1,000 pages together, contains all of the stuff that I have learned. And I'm using that now to actually implement some systems that go beyond the current Turing machine limitations. So this paradigm, I call it mindful machines, because we can actually introduce this sense of self, and just like a digital biological system, which is genomic, we can now create a digital system which is also genomic, with a digital genome defining the system. So that's what I'm going to be introducing and talking about. And these mindful distributed software applications essentially are self-regulating. They have a concept of the self, and they know there is a schema, and then you can replicate the various instances based on that schema. And also it essentially can be used for process automation, or also gain insights from a variety of sources, including the large language models, and then provide all kinds of useful applications. So two applications I will be talking about and showing you is, one is a self-regulating and metacognitive distributed video on demand service. So this is a service which actually can deploy itself on multiple clouds, and it can monitor itself on various components, and if something fails, it will actually repairs itself and scales itself, and so on and so forth. The second one is medical knowledge-based digital assistant, which uses a lot of medical knowledge from all kinds of sources, including large language models, and provides event-driven interaction memory, and also applies various reasoning modules to actually reduce the knowledge gap between a patient and the doctor. So these are the two applications I'll be focusing on. So what is general theory of information, and how we can use them? Essentially, from these two books, you can learn that the Turing machines are not sufficient. And he, in fact, actually in 2005 wrote a book called Inductive Turing Machines, which are beyond Turing machines. And unfortunately, not many of them really realized the power of those machines and used it in real applications, until I actually developed the dime computing model and published it in Turing Centenary Conference. Now, we are going beyond inductive Turing machines to structural machines, which he has actually defined and wrote a book on named set theory, which allows you to address how to define structural machines, what is how a schema-based definition of system, and then you can implement them. So it's very interesting to see that you can go from Turing machines to inductive Turing machines to structural machines. You can go from Turing oracles to cognizing oracles, which is another concept in structural machines, and data structures to knowledge structures. This is what allows us to create a sense of self and autopoiesis and metacognition in digital systems. So the symbolic computing and sub-symbolic computing we all know, and I will relate those, how they are related to super-symbolic computing and what is super-symbolic computing. This is all derived from his theory of named sets, which says basically that two entities are related by some behavior, and also you can essentially model that, and this creates a composable knowledge structure, which essentially allows you to create large knowledge pools and so on and so forth. So basically his theory was that there is the physical world, which is all material structures, and there is the mental world, this is the mental structures, and the world of structures, which is the ideal structures, which is described in the models by named sets, entities, relationships, and their behaviors. And you can actually create how the mental world uses information from the material world. So information is actually a state in the material structure in the real world, and its dynamics and its evolution. So you have a material structure, it is evolving in the material space, and that information is actually received by the observer as epistemic information and is converted into knowledge using the structures in genomic structures that have the knowledge to create the knowledge pool and memory and so on and so forth. So that is how it works. And so the genome plays a very important role in defining the whole systemic behavior, all the way from single cell, build yourself, monitor yourself, manage yourself, and so on and so forth. So with that picture, I will talk about how this all works. You can actually go to this tfpis.com, which is a site that Mark Bergen and I actually created in one of the IS4SI conferences several years ago. And there is an article called What is a Computer and Is the Brain a Computer?, where most of these concepts are very clearly explained. And there are a variety of blogs that explain how to use this information to build actual systems and so on and so forth. I'll show you a couple of systems that we have built. Okay, so what my contribution with the Mark was to actually take this genomic model of world structures, physical world, material structures, and the mental structures, where the information is the bridge. It's basically, information theory says energy and matter are as knowledge, information and knowledge in mental structures. So use that same model. I talk about how we do that. We create a digital world with a digital genome, and this digital genome defines a specific system with a specific functional requirements, non-functional requirements, and best practice policies and constraints, so that it is not only the systemic but also component level, group level, and so on and so forth, just like a cellular organism does, right? So you have overall body, and then brain and mind, and they're all related by a society of cells that are cells and neurons. This acts as a society with a hierarchical intelligence, and so on and so forth. So we replicate the same thing in digital structures. So if you look at this, by the way, Bergen-Michelini thesis basically says that the knowledge is represented in genomic systems, and if you want to create the same knowledge in digital systems, you have to have three levels of must operate on three levels of information processing, and here is how it works. So you have to have a physical level. In the a body in the biological systems, there is a replication and there is the metabolism. The metabolism provides you with the energy matter transformations and how to use resources and what to do if there are no resources. All of that stuff is in the metabolism. And that is very important because that's what you use for autopoiesis and making your own structure and so on and so forth. Similarly, the replication is about knowledge. And so that comes in as a software. And that is at a logical level where replicable components like cells. So we have now digital cells, which essentially have specific function, and they all form into groups with a specific purpose. And then groups of groups are formed into a system with a very specific goal and all of the rules to manage the deviations in form or function. So if the form or structure changes and if it is not conforming to the original theme, then it knows how to repair itself and so on and so forth. So that is called autopoiesis, right? So these systems will be autopoietic. And then there is the third level, which is really at the higher level, knowledge level, where semantic understanding, analysis of episodic memory, and decision making are done, right? So you have the lowest level where metabolism, so you need CPU and you need memory and you need all of the ingredients to create and execute this software cell. And that software cell has the functionality of what it needs to do and who it needs to communicate and what information it needs to share and what is the correct information that it receives. And so there is security, fault management, performance management. All of those are all built into each cell and also groups of cells and the system as a whole. So if you see the resulting system are purpose-driven, they're teleonomic, very similar to biological systems. And they're autopoietic because they can self-organize, self-maintain, and evolve. If one of the components fails, they know what needs to be done, and so on and so forth. So here is the mental structures and cognition, how it works, right? In the biology, basically the body is core components for knowledge organization to create form and function, and that comes from your genes and cells and network effect, right? Levine says this network effect is really what causes the control structures and stuff, right? In our case, what we do is we actually specify the control structure, and also the control structure is modifiable, right? So as experience, gives you, you get experience, you actually know how to change your control structure also. Not only the function, but also the form and the control structure. Okay, so essentially what happens is the next layer, all of the information that you receive and interact and so on is actually encoded in semantic and episodic memory. And this episodic and semantic memory receives information, converts it into knowledge, and creates a memory. And that all the neurons that fire together wire together. Now, all the wired together neurons that can fire together to execute higher level behaviors. The cognitive process is really, there are many, many, many higher level processes, just like the Society of Mind by Minsky. You have multiple processes looking at this information that is coming in real time and changing these graphs of associative memory and semantic memory, and using that information and trying to figure out its own role and what its role in with the interactions with the external world, and making decisions based on best practices and policies, and maintaining its structure and also the function. So the decision and adaptation all comes under the higher layer, guides choices and adaptive strategies. So what we can do now is build very similar architecture, which is using a digital genome. And here is a comparison between features in biological genome and digital genome. It encodes proteins, and here it encodes functional and non-functional requirements. There is a DNA sequences, regulatory networks, and epigenetic layers. And here is metadata, rules, workflows, best practices, self-regulating symbolic and sub-symbolic structures, architectures. These are all formed into a network of networks. And then you have policies, and you have built-in semantic episodic memory through runtime application and feedback. So we can actually do all of this stuff now in digital world. And here it is. So these are your sensors and actuators, and this is your symbolic computing algorithms, and here is your metabolism, basically providing CPU, memory, and so on. And then you have this brain, which is the sub-symbolic architecture, which allows you to take data and process and learn. And then both of these things are combined into a model which represents entities, relationships, and their behaviors. So if you have a doctor, he is an entity, a patient is an entity, an interaction between the patient and doctor is a relationship and behavior. Then the symptoms, for example, in a disease are entities, and then diseases are entities, and they are related by, if you have these symptoms, this will be the disease, blah, 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 right? So we can create a whole host of relationships, just like, in your body, you have trillions of cells doing this stuff, and your neural networks doing zillions of stuff, and creating this semantic and episodic memory. We create that in a graph database, and we use that with the higher level reasoning modules here now, which is multiple processes that are looking at this memory and looking at the changes and trying to, activate what they need to do and make decisions, policy changes, and so on and so forth. So this is the architecture that we use in order to create them. So this essentially allows us to create mindful machines or artificial life forms that embody cognitive architecture with self-awareness, ethical reflection, and self-regulation. Because ethical reflection and self-regulation now become processes that we can actually program, because we know what the entities, relationships, their behaviors, what is the form, what are the functional requirements, what are the non-functional requirements, and how do we manage the deviations from norm, and so on and so forth. Similarly, we also can have understandable, deliberate, and be accountable, right? So now we have a model where we know precisely all the semantics and the episodic, events. And so we can analyze them, we can go back, we can use the history to change our policies, and so on and so forth. And then we have the framework to provide rigorous ontological scaffolding to differentiate signal, data, memory, and meaning, right? So we have this hierarchy of processes that do all of this stuff. And so every process knows what is the input, what its function is, and what is the output, and who it needs to share that information with. And so that provides a secure connection between these things, and so on and so forth. So it's a very, very sophisticated way of communicating. So how is this all related with the evolution of computing that we have now? So you can see, for example, the Turing model basically was data structures, algorithms, symbolic computing, process execution, and you have your knowledge, and you do things with it, process automation, and so on and so forth. Whereas now you have additional thing from machine learning and deep learning and sub-symbolic computing, and here is where all your sub-symbolic computing algorithms are. And that knowledge now is actually created in order to do the transformers and robotics and Gen AI and this stuff. Now, what we have done is actually introduce this new layer with the super symbolic computing. This is what Bergen's contribution for structural machines. And so we have a domain-specific digital genome, which essentially uses this knowledge and creates a super symbolic computing structure where you have autopoietic and cognitive knowledge structures. And it knows we create actually a semantic memory, and also system, the event-driven interaction history. So if a doctor and patient interact, immediately that information is captured, and what happened, what symptoms were given, and how diseases were analyzed. All of that stuff is now just like in your brain, your episodic memory and associative memory are etched from your cradle to the grave. Here we are capturing from cradle to the grave all of the events and associations, and we use these associations and events with higher level processes, like in the mind, essentially multiple processes doing various things in order to this is all goal driven, right? So that accomplish the form and the function, and minimize the deviations in the form and the function. And if you need to change the form, you can change the form. You can also change the structure based on interactions and the interactions with reality, right? And so this is basically the model, right? So that's how it all works. And so what we do is, use the digital genome, functional requirements, best practices, policies, and so on. And we create this whole architecture of various cells, right? So this is a autopoietic manager. Its job is to maintain the structure of the whole system. So it is monitoring all of the components. It creates the components and it monitors the components. And if any component changes or requires action, it will take action. All of that stuff is autopoietic manager. And there is a cognitive network manager that knows who is connected to who and what are the various functions, and make sure all of those things, connections are working. And if the connections are not working, then it will tell autopoietic manager, you need to change the structure, and it changes the structure and it sets up the new connections. And the policy manager essentially looks at the deviations, for example, red flags, and then it will tell cognitive red flag manager will tell, change the policy or the workflow and so on and so forth. So here is a video server, for example. There is a video client and there is a duplicate video client. If this server fails, we can always switch over to the right server and so on and so forth. So redundancy and component distribution is very important. And they're always being managed at local level and also at the global level, right, and the group level. So here is the workflow for user interface management, and this is capturing all kinds of events about, who watches what movie, what is their liking, disliking, and so all of the data is, coming from outside is captured in the semantic and episodic memories, and that essentially is used in order to do all kinds of process automation and also insight discovery. So here is basically various structural level information representation, processing style, interpretability, learning capability, ethical reasoning, self-awareness, GTI alignment, all of the symbolic computing, which is really Turing machine based, and sub-symbolic computing, your LLMs and other computations. Super symbolic computing is providing this genomic architecture, and mindful machines essentially is developing this integrated system. So this compares, and you can see, for example, here it is low for this, transparency, whereas here it is very high, and so on and so forth. So it has been actually implemented, and I'll show you. And here is the implementation. So here is your cloud, one cloud here, another cloud here, and your infrastructure as a service, platform as a service, and then your application functions are over here, and there is your autopoietic manager and your cognitive network manager, and they're all managing themselves, and they know what is the overall structure is, overall function is, and if any deviations occur, for example, if one of these applications here fails, then the traffic is rerouted, the connection is changed to go to this one here. So the user will not even see any disruption. So that is how you create autopoietic and metacognitive video on service demand, video on demand service. And this has been peer-reviewed publication here. Anybody can go and see and build similar kinds of systems. And there is a whole video which actually shows complete, what is the theory behind it and how we have implemented it and how it actually manages itself and so on and so forth. Similarly, the second application that we demonstrate is the medical knowledge, right? So you have here a patient and you have a doctor, and there is a large amount of knowledge here, medical knowledge from books and processes and tests and all kinds of stuff. So all of this knowledge is required, and for a doctor to actually diagnose. And of course, you have a large knowledge about symptoms, diseases, their relationships, and all the stuff. Now you can actually ask LLM for any kind of knowledge, medical knowledge, it will give you. Now, obviously, whether it is true or not, you have to verify and so on and so forth. But that's a secondary thing which can be done automatically, right? So you can look at healthcare professionals, you can get them to validate it and blah, 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 right? So basically, so all of this knowledge is encapsulated in our model. And so the model actually has patients, doctors, symptoms, diseases, and risk factors and their relationships and their behaviors. What happens if you have these 10 symptoms? What are the 8 possible diseases? Blah, 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 right? All of that stuff is available knowledge. And now we have collected all that knowledge. And also in real time, you can go to an LLM, or in real time, you can go to an expert and ask for information, and then you can actually include that in your knowledge. And so your LLMs capture medical knowledge, collect interaction history, monitor the system for development deviations and expected behaviors, and learn from past interactions. So you can actually modify your policies and your processes because it is a knowledge network. So new processes can be introduced without disturbing anything. It is just like in your body, you don't stop and reboot.
Only 3 minutes left.
Yeah, I'm done. So almost done. So these are references, and these basically, he who loves practice without theory is the sailor who boards a ship without a rudder and compass and never knows where he may lay out. So here we are using the theory. And now here is, your demonstration, just for example.
Shutting down the video client server.
Just a very short demo.
Host 5001.
So essentially what is happening here is, one of the nodes is providing the service to this, user. And when it fails, it actually switches over to another one without any interruption to this person, without any human intervention, right? So that is auto failover. So in any case, so it essentially shows how we monitor the form and the function and how we manage the form and the function.
Connection to the second.
Okay.
So thank you very much. And we've got time for maybe 1 or 2 questions.
Yeah. And if you have other questions, you can always, email me. And
Velina, your mic is off. Please turn on your microphone.
Okay, I saw it. Okay, we had a period when we dealt with how the neural networks will replicate exactly what the human neuron system makes. We had also the genetic algorithms which are exactly like human genetics, etc. In fact, none of them was this. Just the names were taken. So I have the impression that your architecture is really terminologically well related to cognitive phenomena, but it is not cognitive phenomena, of course. And what I wanted to know is just one question I have. How is your system making what you termed meaning? Meaning, how is made by your system?
Because it is already in the functional requirements and non-functional requirements. So each cell has a very specific purpose. And so you have already programmed that process, right? Each process has input, right? And the meaning comes from what tasks it has to do and what are the deviations from those tasks. And if those deviations occur, then how do you manage those deviations to make sure it is homeostatic, right?
Okay, I understand, but the meaning itself is something that the humans who did the system have involved. Is not something that
Oh, it is both, right? So humans define all of this stuff initially, right? So the digital
yes,
genome is
this
defined
is
a
what I
human,
wanted.
right? However, as the experience is gained, the system now can use the information from the a module that is looking at analytics, for example, right? So which user has what kind of risk factors and stuff like that, and if that knowledge is deviating from different from the current knowledge, it will add that knowledge into the pool, right? And so all of these are processes that are essentially added or subtracted and so on and so forth. So the knowledge comes from the system, but somebody has to say whether this is a right process or not, and then you add that into the system.
Yes,
But you can
use
add
that.
single cells, few
I
cells
follow
into.
that. I follow to use the entity relationship model, and this is the only one which is really tied to human grammar. The entity relationship model is what you use. So this is great, but what does mean, for example, I don't know, amygdalotomy? The system doesn't
By
know.
the way, this is not a replacement for human beings, right?
It's
This
not.
is only an
Yes,
extension of
okay.
a human
This
being.
is what
Right?
I
This is a
wanted to
tool.
know. It
Yeah.
doesn't know what does it mean. Okay.
Right. This has been taught what it means. Every cell knows exactly what it means, right? And so it has been taught.
What means
So this is not really a replacement, but it's an extension. What does mean?
Okay, probably we have to finish today. You can see
Okay.
that presentation.
Yeah, these are all very well described in my papers and also at tfpis.com, right? So if you read that and if you have very serious objections, please inform me, because my the blog post has my.
I would not have objection except about the terminology.
Thank you very much.
Thank
We
you
have
very
to
much.
close our fourth day of the conference. Thank you everybody for presentations, and especially to Anna for being session chair. This is always quite difficult task to especially when there are many presentations which generate questions, comments. Session chair's responsibility is very tough. So Anna, thank you very much for chairing. Thank you to everyone, and thank you to our technical support for helping us and for assisting us with our presentations and with our discussions. So see you tomorrow, 9 o'clock Central European time, and I hope tomorrow we'll have equally interesting day. Thank you and see you tomorrow.
Thank you.
Bye.
Thank you. Bye.
Thank you to the event chairs and the speakers for their time and interesting contributions to this conference. Also, thank you to our attendees. I hope you found these sessions interesting. I would kindly ask you to take a few moments of your time to scan the QR code displayed on the screen and provide us with your valuable feedback regarding the conference.
Thank you.
The
Bye.
conference continues tomorrow. Have a nice day. Goodbye.
Goodbye, and for me it is good night because it is already between 1 and 2 o'clock in the morning. But it was interesting, so it was worth to stay longer and to hear so many interesting things. Good night, and see you tomorrow.
Good night.